Hi guys, this is Pradeep Raj. I would like to welcome you all to the fresh new course on PCB design. This particular PCB design course is designed for freshers as well as the candidates who are looking for a great career in PCB design as well as hardware design. If anybody wants to switch their domain to PCB design, or the PCB designers who are already working and they want to explore or enhance their skill set, I just want to recommend them to go for this Udemy course, which is PCB design using OrCAD or Allegro from basics to expert level. So this particular course has nearly around 3000 students enrolled and more than 500 plus ratings with a 4.3. It has now got 83% off on its base price. The overview of this course is it has got more than 30 plus hour on-demand video and 128 downloadable resources. Along with that, it has got more than 130 plus classes, and everyday classes are getting uploaded. And in this particular course, you can check it out for learning from basics to expert level. So coming back to our course, we will discuss about what are the things we are going to learn in the entire course in this session. Overall, in this session, we will be having around 15 different lessons. In the first 5 lessons, we will be having introduction to the PCB, where we will know about the detail about what is PCB, what are the material which we use, what is the involvement of designers as well as manufacturers. In this lesson 2, we will discuss about how to do the circuit designing. Circuit designing is an essential part in the PCB design. If you are not doing the circuit designing, that's fine, but at least you should understand what is the circuit is all about, or application circuit is all about. And in the lesson 3, we will understand the software, which is in this particular course we are using OrCAD and Allegro 17.4 version. We will understand the environment, how to create new projects, how to create a pad stack editor, how to create a PCB boards. So in the lesson 4, we will also discuss about IEEE standard symbol creations. We have already seen many of electronic symbols in our textbooks. So now it's the time to design those symbols in the software according to the IEEE standards. In the lesson 5, we will discuss about the bill of material. We call it as BOM. The bill of material will be having all the information related to the component which will sit on the PCB. So this is first 5 lessons. We will discuss about introduction to bill of material, and in the next 5 sessions or 5 lessons we will discuss about the footprint design. In the footprint design, we will discuss about SMT footprint design, through hole footprint design, BGA footprint design. There are many types of footprint designs we will discuss in the lesson 6. Whereas come to lesson 7, the designed footprints we will attach to the schematic, and then we will try to switch from the schematic level to board level, so to design the PCB board. In the lesson 8, we will go for the outline and board shapes, where we discuss about what will be the board shape, what is the size of the board shapes, all related informations. In the lesson number 9 and 10, we will discuss about the layer stack up, which is initially we will discuss about 2 layer stack ups, how to arrange the layer stack up, how to arrange the dielectric material, how to arrange the copper section, what will be the thickness of the copper and what is the thickness of the core layer. We will all discuss in lesson 9, and in the lesson 10 we will discuss the rules and regulations which we apply on our PCB. That is all about the constraint settings. In the lesson 11, we will work on the artwork. Artwork are the files which is required by the manufacturer. So first we will discuss what is artwork, how to create artwork files, and what are the necessary files we need to add inside the artwork folder. In the lesson number 12, we will discuss about the component placement. So this is completely a planning. So we will get a 2-side placement, we may get 1-side placement. We will plan according to the circuit and according to our requirement, and we will start doing the component placement. While before routing, we will also define if any wires are required. If wires are required, we will create how to create wire, what are the types of wire, all the details we will discuss in the lesson number 13. And then in the lesson number 14 is a very important topic where we will discuss about how to do the routing, rules and regulations related to routing, and ground planing and power planing related things we will discuss in lesson number 14. And finally, in the 15th lesson, we will release the Gerber. So Gerber release is the one part which is required by the manufacturer. We will create the Gerber or artwork files and we will send it to the manufacturer for manufacturing purpose. These are the 15 different lessons we will discuss in the entire course. And what will be the outcome of this particular course, we will say. So what skills we were going to have after completing this course? The first thing, you will be having a strong knowledge on electronic parts, because each and every circuits will be having an electronic components involved in it, and eventually we will study about those parts and what are the behavior of that particular part. So you will be having a strong knowledge on electronic parts, and also you will be able to prepare few circuits related to power supply circuits and some small application related circuit designing also you will be able to do, or you will be able to prepare. Otherwise, at least you will be able to understand if any circuit is provided to you, you will be able to understand the circuit. And then when it comes to tool, so we will create IEEE standard symbols. So you will be now having a knowledge once you complete this course, how to create the IEEE standard symbols, what will be the symbol drawing, what is the symbol pins, what are the symbol pin properties. Those detail about IEEE standard symbols, you will have a complete knowledge. So once you prepare some schematics, so we will give many schematics for your assignment. So once you are working on that, so you'll be mastering in creating the schematic design using this particular tool, and you will be able to understand the technical data sheets. So once we prepare that BOM, that is bill of material, along with that we will also download the data sheets of the particular components, and you will read and understand what are the technical related things about the components. So and then you will be able to design the 2D layout or footprints of each and every component, and also board design, board shapes. We will discuss about a board, how to export the board, how to design the board shape, how to import the board shape. All details you will be knowing after completion of this course. And then finally you will be able to calculate the design standards, and you can design the board independently. Calculation is very important. There are certain rules and regulations we need to apply and then calculate it with a few formulas I'm going to explain in the sessions. And once you finish entire course, you will be able to design this entire from schematic to Gerber release without any help. That means independently you will be able to design a PCB board. So this is all about the skill sets. You will get it once you finish this course. I hope you will get all the details. I hope you understood all the details. So I wish you all the best for this course. Okay guys, we will continue the PCB design course as we discussed earlier. So we will have the 15 different lessons. Now we will discuss the lesson number 1, that is an introduction to printed circuit board. To remind you that if you wanted to learn the entire PCB, I would recommend this Udemy course, which is PCB design using OrCAD or Allegro from basics to expert level. This course will start from the basics, and it will also cover the expert level of the PCB. So this course has 30 plus hours on demand video as well as 128 downloadable resources, and it has got more than 15 sections and 130 plus lecturers involved, and every day lecturers are getting updated according to the requirement. So this is the best one of the best PCB design course. I recommend you to check out this one. So if you are preparing for an interview, so I would recommend this Mastering PCB Design, an interview preparation guide from the Amazon Kindle. So I just leave the link in the description, both of the link in the descriptions. Please do check with this. Coming back to the course, in this we will discuss about the first lesson, that is an introduction to PCB, that is printed circuit board. So we'll go to the first slide here, an introduction to printed circuit board. We will define what is PCB. So the PCB stands for printed circuit board. So the platform, so printed circuit board is a platform where all the application circuit lands on top of it. For example, there is a PCB, so if you have a application circuit and that applications will be having some components, all the application circuit will be landed on the PCB or on the board. So this is a basic building block, or you can also say a proper platform where all your application circuits will land. So you can also define the PCB in the 4 points. The first point is the platform where all the application circuit lands, and the second point here is the board that is hazard in nature, that gives a mechanical support to electronic components. So here you can see the 2-layer PCB. So here we can also see the core. So the core is actually the board which is hazard in nature. Hazard in the nature means which is very tough or very strong dielectric material or non-conductive material. So due to that strong nature, it will allow electronic components to place on top of it or on bottom side of this PCB. So it will handle entire weight of the component, and it will give the mechanical support to the electronic components. So this is the second point where you can define that the PCB is which gives a mechanical support to electronic components. And the third point, if we say, so it will also give a electrical connection between the electronic components. You can see here we have got the components on the PCB, and all the components are connected on the PCB. So there are 2 points here. The first point we can say which gives a mechanical support to electronic component, and it will also connect all the components electrically. So we can define now with the 2 to 3 different points. If the question comes in an interview about defining the PCB, so you can just abbreviate it. First, the PCB stands for printed circuit board, and then you can say this is a platform where all application circuits lands. And the second and the third point is a very important point, which gives a mechanical support to the electronic components, and it connects components electrically. So we have the technical words like in the first point we have the application circuits which lands on this is a platform where all application circuit lands. In second, it gives a mechanical support to the electronic components, and the third point is which gives the electrical connectivity between the two components or between the components, but that is according to the circuit. So the connections will be done according to the circuits. So this is all about the printed circuit board definitions. So now we'll go to the type of PCB. So there are many types of PCB where depending upon their form factor, their applications, and their behavior also. So the first thing is the single-sided PCB. In the single-sided PCB, it says it is a type of PCB that has conductive traces and components on only one side of the PCB. For example, if we have a PCB, so we do have the components and the electrical connections or traces only on one side of the PCB, and these are all called as single-sided PCB. The second type of the PCB is a double-sided PCB, where you will have a component on both sides of the PCB, as well as the electrical connection will be also on both sides of the PCB, top as well as bottom side also. So that comes under dual-sided PCB. And multi-layer PCB, this PCB can be either single-sided or double-sided, but we have the multi-layer for electrical connections. For example, you'll be having internal layers apart from the top and bottom, so we will be also having an internal layers. So this is called multi-layer PCB. So these are the 3 types according to the placement and traces. So the first one is single-sided PCB, second one is dual-sided PCB, and the third one is multi-layer PCB. The fourth one is the rigid PCB. The rigid, in the sense, the rigid PCBs are commonly used in electronic devices and systems where the board is not subject to bending. So if you are not bending your PCB, for example, if you don't want to bend your PCB, so then you can go for the rigid PCB. So these are strong. It may be single-sided, double-sided, or multi-layer, whatever the type. First 3 types we have seen, it may be anything, but this particular material is very strong, so will not be able to bend that particular PCB. And those type of PCBs are called rigid PCBs. The next one is a flex PCB, flexible printed circuit boards, also known as flex circuit or flexible PCBs. This is a type of printed circuit board which is only designed to designed to be flexible and bendable. So you can see the picture here. So these are all the flexible PCBs. This is another type of PCBs which will mostly give a connection between the two different PCBs or rigid PCBs. The final type here is the rigid flex PCB. It is a combination of rigid PCB as well as flexible PCB, so which is used to connect different PCBs, and it will establish a connection between the different PCBs or rigid PCBs. So these are the other three types. One is rigid PCB, second one is flex PCB, and the third one is rigid flex PCB, which is a combination of rigid as well as flexible PCBs. So these are the types of the PCBs. I will share in the description box or in the link, I will share you the interview related questions, so you can go through that, and that will be very helpful for you to attend any kind of PCB related interviews. The next is the classes of PCB. So we are divided into three different classes. We can also say class A, or they call it as class 1. So like class A or class 1, or class B or class 2, or class 3 or class C. So this is also named as class 1, class 2, class 3, or class A, class B, class C. These are the three different classes of PCB. So we will see what is the difference between the class. So in class A, you can see we use it in general electronics, and its life cycle is very short. So we can say this life cycle is very short. That means it has got no warranty, no standard warranty. So it may run on 1 day, 2 day, 1 week, 2 week, or 1 month or 2 months. We can't say anything. So anytime it will work and anytime it will stop working. So it is the build quality will be the cheap, and which most widely used in toys and flashlights. So these are all class A PCBs where we do not have any life cycle, like any warranty, and the quality is also very cheap and price is also cheap. The examples like we use toys and flashlights. The class B, if you say, it is a dedicated service in the electronics. For example, if you are buying a PC, so you will get a PC or laptop, you will get a warranty of 1 year warranty, 2 year warranty, and some people give 5-year warranty, and after sales warranty also they will give. The life cycle, of course, if you purchase any laptop, the fresh new laptops, of course they will have a life cycle, very good life cycle, like 3 to 4 years you can run without any issues. And you can also, if you are maintaining it's very good, you can run it for a long time also. And the service provider will also give you the proper warranty for these kind of electronics. So PC electronics, PC laptops and mobiles, and any other like consumer electronics, good electronics, they all comes under the class B. Quality, of course, it is a good quality PCB, which that's why it will run for longer time. So we have taken an example here as laptops as well as microwaves. So many other consumer electronic products will come under class B. And class C is a very special, and it is the high reliability electronics. So the warranty, we can say the life cycle is like very long. We can also say it is lifetime warranty. So that means it is a fail proof. These kind of PCBs are fail proof, class C. So we use that in aerospace, military, and as well as medical. For example, they may use in satellites, they may use in aeroplanes, they may use in any missile technologies, in defense technology they will use it, or in medical technology also they will use it. So it will long last. So they may give warranty like 25 years warranty, 15 years warranty, 30 years warranty, 49 years warranty, or 50 years warranty. These kind of products are all comes under class C PCBs. So these are the differences between class A, class B, and class C. Just recall, class A is general electronics and have no warranty. In class B will be a dedicated electronic service and has got very good and a long life cycle or warranty. And class C is a fail proof. It's a high reliability electronics, and the warranty will be more than like 20, 25 years, 30 years. You can also say it is for lifetime. So this is all about the classes of PCB. Then next we have a levels of PCB. So there are three levels. One is a low density PCB. The low density in the given, we'll just discuss with the low density. The first one is low density in the given PCB. So we will be having enough space is left on the PCB and we have only few components placed on the PCB. So these are all called low density PCB. So in the low density PCB, we have few components and most of the space either on top of the PCB or bottom of the PCB is free, so that we can apply any kind of rules, and it is easy to design. So we don't need to do any kind of plannings for routing and placement, so we can do without any effort, and it is also not a time consuming design. So if you start it, you can quickly finish because it has got enough space on the PCB. So these are all called as the level 1 or low density PCBs. In the moderate density PCB, if you compare with the low density, moderate density will be having more number of components compared with the low density. It has got some extra components. Yes, it needs some planning to do the placement on PCB, to do the routing. So we need a proper planning, and also it takes some time. If you compare with the low density PCB, it will take time to do the designing, so it will not quickly finish. So yes, it needs some times, and also multi-layer designing will be involved in moderate density PCB. Till 4-layer PCB design can be involved into the moderate density PCB. If you compare with the low density, so in moderate density we will be having more number of components and more number of routing connections if you compare with the low density, and also there is a space restrictions. Space will have a limited space. Inside the limited space you have to place the all components and routing. So yes, we need a lot of planning as well as planning for routing as well as placement, component placement. So the next it comes to the high density PCB. In the high density PCB, yes, there are n number of components. So if you compare low density and moderate density, we have very critical component placement here. So we have enough components on the PCB, so we need to do a lot of planning for component placement. It is also called as critical component placement. And yes, of course, the routing is also a difficult task. We need to do the planning for routing also. If you compare with the low and moderate density, high densities will be having a lot of component in the same PCB space, and for routing is also it is very critical. So this is all about the levels of PCB. So in the low density we have a less number of component. Moderate, if you compare with low, moderate will have more components than low density PCB. And high density, of course, it is having more number of components in the given PCB size. Yes, so that needs a lot of planning, a lot of planning for routing as well as placement. So we call that as critical routing and critical placement on the PCB. Yes, this high density will almost, it includes the internal layers, that is multi-layer PCB. So this is all about levels of PCB, the classes of PCB, and the types of PCB. So we have already discussed about the definition of PCB. I hope you understood about definition of PCB, types of PCB, classes of PCB, and the levels of PCB. Okay, now we are going to discuss about how to initialize the fresh new project in OrCAD. So before initializing a project, we should have a proper foldering systems. So I'll create some required folders to create your PCB schematic project. Just right click on your desktop or wherever you want in C drive, D drive, E drive. You can just right click and create a folder, and I would name this as the project 1. I say project 1. So inside the project 1, initially we are going to create about the schematic. So we will create a folder called schematic. I'll just right click here and then go to new and then click on folder. I say it is schematic. So inside this we will initialize a fresh new schematic, and I will also create some more folder code. If any symbols are required, we will create the symbols, and we will be having a symbol folder. Apart from this, we need to have a footprint creation. Once you finish your schematic, we need footprint folder, and if you want to get the data sheets, you will also need a data sheet folder. we can create a data sheet and we will collect all the data sheet into that particular folder. And finally we need another folder called the board folder or PCB folder. We can say PCB or the board folder. So these are the minimum folders required. If anything else if you need, we will create and we will initialize the project. So apart from this, you can also make one more folder called documentations or documents, you can make it, or reports. So we will get all the document related things inside this about this particular project. So this way we can create a subfolders. Now we are going to initialize a fresh new project inside the schematic. So we will discuss about the flow of the PCB. The flow will be, so we will start creating the schematic first. In general, as a schematic, once you're done with the schematic, we will go for a bill of material creations. So once the bill of material is finalized, we will start creating the footprints of each and every component which is available in the schematic. Once the footprint is done, we will go for a board design, and then we will also go for the Gerber files, Gerber release or Gerber creation, we can say. So this is a brief flow, it's not in depth, just we will start it from the schematic level, and then we'll make a BOM, and then we'll make a footprint, and then we'll switch to PCB, and then we'll go for a board design, and finally once you're done with the entire thing, then we'll go for Gerber creations. We will also have one more folder called Gerber here, we will create that. So this is a flow, the basic flow from schematic to Gerber release. So we will create one more folder, that is right click new, and we say this as Gerber file. So Gerber file. So these are the folders which we required. So now we are going to start a fresh new project. So if you are creating some other project, like for example if you are creating project 2, I'll just copy the same thing. So but before making, just show you the project 2. So this will be your project 2, and if you go inside, and you can see you should also have the same kind of folders, but make sure before creating any project, you make sure copy paste for the next project also. I just delete this. So open the first project. So inside the schematic we need to initialize a fresh new project. Okay, so now we will open OrCAD. Once you install the OrCAD, we will just click on capture. So capture CIS we will select, so click on capture CIS. So the first option will be here, OrCAD capture. So just click on OrCAD capture, click OK. So this is how we are initializing the fresh new project. So initially we will create the folders required, and inside that particular folder we will initialize the fresh new schematic from the OrCAD capture. So now we'll go to file. So this is the environment of OrCAD 17.4. I will just click on file, go to new, and click on project. So this is file, go to new, and file, go to new, and click on projects. File, new, project. So now we have got some pop-ups here. Inside this pop-up, the first is the name of the project, and the second one is the location where you want to save your schematic project. So first I am going to give the name for this project. I would say that power supply. We will discuss the circuit designing of the power supply, and the next is we need to assign the location. I'll click on the browse button. So our location is on the desktop. I will select the desktop. Inside the desktop we have got project 1. Inside that we are creating the schematic. I will open the schematic folder and click on select the folder. So now you can observe here is the name of the project, and this is the location where I want to create a schematic. So I'll choose a schematic folder which we have created earlier, and then click OK. The fresh new project will be generated here. So it will take some time, and then it will generate a fresh new project, and then we will save this, and then we will go back to the folder and we will cross check. Okay, I'll just click on file, save, Now go to the location where we have created already. So project 1, inside the project 1, so we have so many folders. We have created the schematic. Double click on the schematic. Now you can see there is a DSN file, so which is your actual project file. So the DSN is an actual project file. So this is created. So we'll go back to OrCAD capture. So now you can observe here there are two tabs here. One is, this is the first tab, which is file hierarchy. We call this as file hierarchy or file system. We can also say file system, where you will have the project related information. On the right side we got the start page and the schematic page. Okay, so this is about the file system, and this is the start page, and this is the schematic page. So now we will discuss about the file system. I'll just click on this center line and I can increase and decrease this. So we'll come to this point here, which is, this is the project which we have created, that is .dsn project. And if you open this plus button, click on this plus button and we'll get the schematic, and if you click on the schematic we'll get the page 1. I'll just zoom in now. So this is your main project. This is the type of the project, which is schematic, and this is the page where inside this page, so this is what the page is open now. Here we are going to create the schematic preparation. So this is all about file hierarchy. The .dsn file is your actual project. Inside that, this is the type of the project, which is schematic project. The page 1, if I double click on the page 1, so if I double click on the page 1, the page 1 is opened here. You can see the tab of the tab, which is page 1. So the same page 1 is opened here. So I'll just click on this one. So this is a page where we have the space for creating your circuit. Here we can create your circuit inside this particular sheet or inside this particular page. So this is how we initialize a fresh new project. So you just go to file and click on new and then project. So this will ask you the name. So the name will be whatever the name which we give here, the same name will come and sit here. So that will be the .dsm name, and whatever the location is there inside the particular location, your project will be saved. So we can cross check. You can go back to the folders and you can cross check whether your project schematic is saved or not, or created or not. This is about schematic fresh project initialization. So you can go to file and save whenever it is required. You can go to file or save or click on the save button. Here you can see this is the save button. Otherwise you can also right click on the DSN. You can also right click on the DSN file here. Right click on the DSN file and you have the save option. So here we have the save option. So once you save this, it will not, you can see here, you can right click and you can click on save button. Otherwise you can also right click the page and you can save the page. So you can go to tab here. So this is a start tab. It is a start tab where you can create a new design, you can create a new project, you can create an open design and open project. So you can also go to the next page, which is page 1. So on the right click, you can also do the right click on the tab and you can close, you can save. So here also in schematic, I can right click, I can save, I can right click and I can close the tabs also. So make sure this is one environment, tool environment. Inside that we will have the sub tabs. So if I have multiple pages, the multiple tabs will be opened here. For example, if I open something else, so I have just double clicked on the title block. So here inside the sheet, I just double clicked on title block. The title block related information is opened on the new tab here, the property editor. If you just go here, we can see the detail about the title block. So how to close? You just right click on this and you can close it. Otherwise we have the close button here. So we can see the close button. So you can click on the close button and you can close it. Right click close also, you can do that. Otherwise normal close button also you can create. So once you create any project, so we'll check how to reopen that one. So we'll just close this DSN file. So just click on this small icon here, you can click on close that. So your project will be closed. Now we'll only have the start page. Start page is the website of that design software designers. So we'll go back and we'll cross check here. Our tool is, our schematic project is saved here in the DSN file. We will open that. We'll go back to the schematic or OrCAD, go to file, open, and you just use the design option, file, open, design, and then go to the location where you have your project. So this is under project 1, this is under schematic. Select the DSN file, that is design file, and then click on open. So this is the procedure of how to create a fresh new project. Make sure before creating your project, create the folder system, files and folder system. Inside the schematic folder, you just create your fresh schematic. Now I opened it here, so double click on this, double click and click on the page 1. The page 1 will be opened here. Inside this sheet 1, we will create the circuit. Okay, so now we will discuss about schematic page as well as the schematic page properties. So as soon as you create a fresh new project, so we will see the project pages here, the schematic pages. When you double click here, we can open the schematic page where you can create a schematic circuit. So before that, you can do the changes here. You can right click on this page and you can rename it, whatever name if you want you can give. For example, here I'll give the power supply unit, and that is, we are creating around 24 VDC to 5 VDC. So this circuit we will create, I will show you the circuit, the same circuit will replicate, and then click on OK here. So now you can see the name has got changed. You can also see here the small star, that means your circuit or your project is edited but you have not done any save. Just click on save, that particular asterisk or star mark will go up, that means it is saved. So when you come back inside the sheet, so we can see here the sheet, I'll just zoom in. So it is A4 size sheet. So if you want to change the A4 side, you can go to options, schematic page property. Inside the schematic page property, you have an options here on inches as well as in millimeters. So now it is in millimeters and A4 sheet is selected. So that is what you can see in the title bar. If you want to change in inches, you can change. If you choose A3, the size of the page is different. If you choose A2, the size of the page is different. Similarly, whichever size is assigned to you, or if whichever size you want to, you can select that particular size and click OK. So to zoom, just press Ctrl and bring the mouse pointer wherever you want to zoom and the scroll mouse button. So now this particular area will be zoomed in. So the title, we can give the title of this particular page. You can double click on this and you can give the title of the page. Whatever the circuit if you are preparing inside this particular page, you can create that particular title here. So you can also add the document number, which will be given by the client or which is given by the company. You can add the document number. Along with that, we can also add the revision code. So whenever your circuit goes for a review, and if they have any review changes required, so they will come up with a review code, so you can update the review code. The next thing is you can add multiple pages here. So according to your schematic, if the schematic is complex, you can add multiple pages or multiple sheets, and you can segregate your schematic according to your applications, and that reduces the complexity of your circuit preparations. So to add the pages, right click on the schematic and add new page. So here I will give the name, that is page 2, and whichever circuit you are creating inside that. For example, if I am creating a microcontroller unit, I will select microcontroller unit and then click OK. So now you can observe here we got the second page, so which is microcontroller unit. I just don't want to mix up all the circuit in one page only, so I will create a separate pages first, separate application circuit. In one page I will create a different circuit, in second page I will create a different circuit. This is a better option. Don't mix all the circuits in single page only. So make sure you have proper A4 sheet page, and inside that A4 sheet page try to add the different circuit in different pages. So now you can also see here the star mark is coming up. I'll just select it. You can also do right click in the DSN and click on the save. The entire project will be saved. So you have to save until this star mark goes off. So this is how you are creating the second page. So you can double click on the second page, and now you can see this title block. So this is the title block of the sheet. So you can see this is size A, so which is different. If you want to change it, you can go to options, page schematic page property, and you can go to millimeters and A4 sheet. In inches also you can see A, B, C, D, different page sizes, and you can choose whichever you want. So here I will choose A4 sheet and then click OK. Once you select A4 sheet, you can see now the sheet got changed to size got changed to A4. So this is about how to add multiple pages in your one schematic. So this is all the part of same schematic. Yes, you can add a number of pages and you can create a separate application circuits, and this is all one this is all part of one project only. It doesn't mean that if you create a page 1, this is separate project, and page 2 is separate project. It is not like that. So this is a part of the power supply unit, and but we have got different sheets, and that categorizes the different circuits. So if you want to delete, you just right click and delete. So if you are deleting, if it is open, so you will not be able to delete it. Just it says cannot delete an open page, so that's why you just have to close that. For example, here is the page 2, here is the page 2 which is open here. So if you want to close, just if you want to delete it, you just close it first, and then you can go here and then you can delete that particular page. So this is the way you can add the page and rename the page, and if you want to delete, you can delete the page also. And also we have set up whichever size of the page you want. We have set up by going options, schematic page property, and then you can select whichever size of the page you want. You can select and create the select and open the sheet or page. So now we will discuss about the circuit preparation. So I will just open the circuit. So this is the circuit which we are going to develop it here. So the input of this particular circuit is 24 VDC is an input, and the output of the circuit is 5 VDC. So we will work on with this. So we will also create the symbol of each and every component. How to create a symbol we will look, and then also we will do the wiring between the components, and we'll do the net naming. So this is the procedure. First thing we will be having two options. One is we already have the symbol library, so we can use the existing symbol library inside OrCAD. It will provide you one library. So from that library we'll get the symbols. You can get the connector, you can get the diode, you can get the regulators. So this is, you can take it from the existing library. Otherwise you can create your own library. So we will do the both option. So some component I will show you how to create, and some component we will take it from the existing library. So both operation we will do it. So this is a circuit. You can just remember this, or you can take the screenshot of this particular circuit, or you can draw this particular circuit, and we will create each and every component. Either we will create or we will select it from the existing library, and we will prepare the circuit, and we will also see how to make the proper circuit in OrCAD Capture, inside this particular OrCAD Capture. Okay, so now we are going to discuss about how to create the schematic. So I'll just open the schematic which we have the document. So this is the schematic. We need to create this schematic inside the page 1. So there are two types of collecting the components or designing the components. The first thing is we need to use the existing library symbol. So the software will already give you a library. Inside that library we will have the symbols. We will use those symbols for our schematic preparation. Second one is we will create our own symbols, or we will create library. Inside the library we will create our own symbols, and then we will use those symbols into your schematic. So in this particular class we will see the both, how to use the existing library and how to create and use the created library. So here the components which we require, this is the power supply circuit which is 24 VDC is an input, and the output is 5 VDC. It's a simple circuit. So we'll see how to create symbols. For example, this is DC jack, that is 24 VDC input connector. Either you can use DC jack, or here for just understanding purpose, I am using 2-pin connector, that is header connector. And then we have the diode, that is 1N4004 diode and 100 microfarad capacitor. And there is a regulator which is 78L05Z regulator. And then output of the regulator, there is a capacitor which is used to block the unwanted signal. And there is a resistor which is 1K resistor to protect your LED, which is in red color. And finally at the output side, we have again 2-pin connector, header connector we can say. So that is used to connect the output. So this is simple circuit, and we will use the existing library and collect all the components. That is one way. And the second way is we will create the symbols. So you will learn how to create a symbol in OrCAD and Allegro. So accordingly we will work on this particular schematic. We'll go back to our OrCAD capture. The first thing we will discuss about the existing library. Use the symbols. Use symbols from existing library. So we'll go to place option and then click on the part. Shortcut key you can use P. So these are the commands. If you want to know the shortcut key of that, you just go to the right side, you will find the shortcut keys. These are the shortcut keys. If you don't find any shortcut keys here, that means that particular operations will not be having any kind of shortcut keys. So we'll go to place PCB place and click on part. On the right side panel, you can observe here on the right side panel, you can see the library options. So library panel is open. Now in this panel, the first option is, I'll just zoom in here. So the first panel is part, and here we are searching the component. So inside the search box we are searching the component, and whatever component we search, so that will appear inside the part list. Okay, the part list commodities are all coming from the library. So if you have a library here, for example we have an amplifier library. So if you are looking for anything from the amplifier, so inside this amplifier library we will have all types of or few types of amplifiers which will be appeared here. So if I search for amplifier here, so you will get amplifier related search results here, but those results are coming from this amplifier library. So this is a library unit. So if you don't have library, you will not be able to search any components, because library file folder will have all the components inside it. So any components you are searching in the search box will appear inside the part list. This will happen only if you have a library files. So initially you don't find any kind of library here, so we need to add the library. To add the library, so we have the three options here. First one option is load the library or reload. Second option is add the library. Third option is delete the library. I will click on add library and it will take you to the default location. For example, so this, if I click on add library, so it will go to the library section, so which is there inside the C drive. So if you go to library, here we can see this is C drive, cadence, SPB, tools, capture and library. If you open the library, you can see these are the libraries. Inside this you will be having components. For example, this is a transistor library. Inside the transistor, so you will be having all types of transistors, NPN transistor, PNP transistors and many other transistors. Components are inside this OLB file. OLB refers to OrCAD library. Inside the library you will have all types of components. So similarly, if you have a shift register, so inside the OLB of shift register you will have a shift register related components. So inside the regulator you will have a regulator related components. So we need to choose all the libraries here. So whatever library we have here, we just click on select all click inside and click on select all, or Control A, then click on open. As soon as you click on open, the all libraries will load into the library section here. So this is the library section, everything will be loaded inside this library. So I'll click open. Now this will be refreshed, and also make sure that this library is also selected all. For example, if I want only regulator, click on regulator. Now you can observe here the only regulator is selected. Here the only regulator is selected. That means now in the part list, if you observe in the part list here, so you have the scroll up and scroll down button here, so you will find only regulator related components. So only regulator related components will be displayed here. If you search something like regulator, it will only give regulator outputs. If you search register here, so you don't find registers because the only library selected was regulator here. Similarly, if you want only transistors, click on transistors. Now you can see inside this library, you can only see the transistor related output. If I select here, I can see only the transistor here. So this is the first option. So second, this is another transistor, third one is another transistor. So similarly, so we'll get only transistor related details here. For example, if you go scroll up and scroll down, you can see the connector. Select connector, we can only see the connector related part list here. So either you can search for connector here. If I say connector here, like CON, I can find the connectors here. So this part list will get only components related to connector. So if I want to search a resistor now, first, for example, if I want to search resistor, so you don't find anything here. So I just say resistors. So you don't find any resistor because the category or the library which we have selected is connector here. So if you want resistor, you can select the resistor library. So just go to come down, and if you find any resistor related library, you can select the register library. If you don't find register, at least you can find out passive components. So otherwise, I will select all here. Press Ctrl A, click anyone and press Ctrl A. Now you can see the register. I selected register here, the register is selected, and you can see the register. So if you select all here, so if you select all here by pressing Ctrl A, all components will be loaded inside the part list. You can search accordingly and you can show the result here. So this is all about the existing library. For example, if you need a 2-pin connector, if you go back and check it out, the first thing what we need here is the J1, that is 2-pin connector. To get the 2-pin connector, so here we will search CON, that refers to connector, and if I want 2, I'll press 2. CON2, I got CON2, and there is a CON2, that is connector 2. So if I double click on this, so if you double click, so the component will come sit inside. Otherwise you can press enter. You can see there is a connector, that is 2-pin connector is inside the sheet. So I zoom out, so you can observe here carefully. So the connector should not go outside the sheet, so it is always inside the sheet only, so it will not go beyond the sheet. So I'll place inside it. So this is how we use the existing library which is provided by the software manufacturer or software designer. So we can use it if you want. So otherwise you can create on your own. So for example, the next component is the diode. So we can't exactly get the 1N400 diode, but at least we'll get some diodes here. If you can see here, there is a diode which is selected, and you can also see the picture, and the component which is selected is diode. So you can double click also here inside this library. You can double click also, or you can press enter also. We get the diode. So you can observe here, diode does not have any proper value. You can change the value. So we will see that how to change the reference and values later. So now the next thing is required is capacitor. So we'll search for capacitor. Now I got the capacitor which I am looking for. If you don't get it, you just come up and down here. So for example, I'll just come up. This is, you can see this is a non-polarized discrete capacitor. So you can just click down. You can see different types of capacitor. I'll just press down arrow key from the keyboard. So you'll get the different shapes of capacitors. Whichever capacitor you want, you can select that particular capacitor. So this is how we search for the proper components. So press enter, it will come inside, and then you can place wherever you want inside the schematic sheet. If I want 2 capacitors, I will click 2 times, one click and bring somewhere up or down, so just click another click. So 2 capacitors. You can observe the references also getting changed here. So first, when you do the first click, you will get capacitor, that is C1, and when you do the second click, automatically it changes to C2. If you again click it, it will come C3. So references will increment automatically. I'll press escape, and your component is placed inside the schematic. So these are the minimum components which we required, and then we need a regulator. So you can look for a regulator. If you don't find the regulator, so I got the regulator which is 2-pin. If you don't find the components, so we will create it. So I will show you both. Here we are just collecting the existing library, and later we will discuss about how to create the library. So the next thing is required as a register. Press enter, place it, and then we need an LED. Search for an LED, place it here, and if you can even do the copy paste, because again we need 2-pin connector here, J2. So already we have J1. You can just right click and you can do the copy, and right click, you can do the paste. So this way also you can copy and paste it, or otherwise you just Control C and Control V and just click here. If you click, you can observe again. So this is J1 and it is incremented, and this will be +1, that is J2. So references will be incremented automatically. So this is about how to collect from the existing library. So these are the components which we have collected from the existing library. So now we will see how to create the library and how to create the parts inside the library. Okay, so now you can come back to the file system panel, which is the left side. So you can observe here inside this particular project, you can also find a library folder. So that library folder is currently empty because we have not created any libraries inside this particular project. So to create that, click on the .dsn file, go to files, and then go to new, and then select the library. So once you select the library, you can observe here inside the library. So we have one more library is created, that is .olb is created. So now we have created a library folder. So we need to save this particular library. So I'll just right click on this library.olb. I'll click on save. So it will ask you the location where you want to save. So if you want, you can save inside this library location so that it will be accessible to each and every project. So otherwise you can also save that wherever you want. For example, I have created a project 1. Inside the project 1, I have a symbol library. So inside the symbol library, I am going to create this particular library folder. So library file, OLB file, that is OrCAD library file. So I'll give the project name here. So I would say this is power supply library. So this is power supply library. So that I will be understanding whenever I am creating the power supply circuit, I will open only this particular library and I will use the required parts. So that means this particular library I am creating only for this particular project. So I will only create the components which are required for this particular project. So that's why I went to the project 1. Inside the symbol folder, I am creating a power supply related library. So click on save. Now you can observe here inside this library, so you got the symbols, that is power supply .olb. So we have got the power supply .olb, that is OrCAD library file is created inside that. So now it's just I will remove this because it is we have taken it from the existing library. Now what we need to do is we will create our own library. We will create our own symbols and then we will use those symbols. So we have already created the library and also we have saved this particular library inside the project location. I will save this. And how to create a new symbols. So if you come on this .olb inside the library .olb, just right click on this olb file and click on new part. I'll just right click here, click on new part. So it will ask you the name of the part. So we'll give the name of the component. So for example, I need a 2-pin connector. I will give the different names. Like otherwise you can give the same name also. I just say connector 2, that means 2-pin connector. You can give any name, at least it should be a proper understandable name you can give. The part of preferences is the preferences, that is the reference of the component. Part reference prefix is the reference of the components. If you are creating a 2-pin connector, so you have seen there is a J1, that means J is our prefix, reference prefix. So I will just say J here. J is used for connector purpose. So there are 4 types. So one is U star. For all kind of ICs we use U as a prefix. For resistors we use R as a prefix. For capacitor we use C as a prefix. For J we use J as a prefix. Here the star means the variable number. It can be R1, R2, R3. That star can be 1, 2, 3, 4. That is variable, numerical variable. So here I'll just type J so that the part references is J. Sorry, the references is J. So we have not created any footprint, so we will leave it blank. Later we will show you how to create footprint and how to apply here. So rest options you keep it as it is, because we are creating a homogeneous component, so it is by default it is homogeneous, so we don't want to touch any other related setups. So just click on OK. So if you click on OK, it will provide you the platform to create the symbol. So if I click on OK, now the new window will open, or new tab will open. Inside the new tab, this is a platform where we can create our component. Now you can see this tab here on the top side, so the extra tab is opened. So initially we have the start page, and then we have the page 1 where we are creating the symbol, sorry, where we are creating the schematic, and here we are creating the symbol. So here inside the schematic, whatever thing we have opened, it is in second page. And now inside the library we have the resistor, sorry, 2-pin connector, so that is opened here. So now we are inside this. For example, if I open this, you can see there is a connector 2 is opened here. So here we need to create the connector. This is schematic. Under schematic we have page 1. The page 1 is opened here, and this is under this library we are creating the connector 2. The connector 2 is opened here. So now we will create the connector 2. So before creating, we will understand what is the component. So what is the component? So what is the part has different things. So first thing, the dotted line, you can see this dotted line is working area. We can also say this is working area or drawing area. I just write it as working area. That means inside this working area, we are drawing symbols. Inside the working area we are drawing drawings. Symbol drawing, that means if there is a register, so this will be the zigzag line, will be this drawing. If the capacitor, the 2 plates of the capacitor are drawing. If it is a transformer or inductor, so that zigzag, the arcs are the symbols. So symbols must be inside, and pins must be outside the dotted line. Pins must be outside the dotted line, either top or bottom, wherever you want to keep it. So outside, what we keep? Outside we keep the pins. So this is the rule. So if you see the dotted line, so inside the dotted line you will draw the symbol drawing. Outside the dotted line we will keep the pins. So this is what the dotted line represents, and the dotted line you can increase and decrease also. It is flexible. If you click on this dotted line, we'll get the 4 points here. Using these 4 points we can drag it. You can drag it to right side, you can drag it to left side, top side, bottom side, and also you can drag it to diagonal wise also. So in all 8 directions you can drag this and you can increase it and decrease it. So it can be applied to all four corners wherever you find this circle dot. So here click, hold and move. So now it is increasing. So if you just leave it here, so the working area got increased. Similarly, if you want to come back, you can come back. You can make it short also. Similarly, if I want to increase diagonally, we can increase it diagonally also. So this is how it works. So if you want to come down, click, hold down, bring it down. So this way we can increase and decrease the working area. Here also on the right side, on the left side also we can do the same thing. On the bottom, on the right side bottom also we can do the same thing. So this is all about this working area. The working area inside this dotted line we'll create the symbols, outside this dotted line we'll add the pins, and all using all four corners you can click, hold and drag it to increase or to enlarge or to decrease the working area. So and then apart from that we have the two things. The first one, J question mark, that refers to a reference of the component. So this is the reference and this is the value of the component. So both we have here, reference and value. So if you want you can move it, click, hold and move it, click, hold and drag and leave it. Similarly this also, click, hold and drag, you can move it, and wherever you want you can drag it, leave it. So this is about the existing platform which is already having a working area, a reference and a value. So now we will draw the 2-pin connectors. So 2-pin connector, the action plan is, so we will have to draw a rectangular box and then we can add 2 pins. So that is our motive. So now we will understand the grids now. So the grid is, the minimum grid here will be 2.54 mm. The size of the grid is 2.54 mm on x-axis as well as y-axis. This is IEEE standard. Each pin have at least 2.54 mm distance or spacing, or 0.1 inches spacing. It has to be always. That's why the grids are exactly 0.1 mm, 1 inches or 2.54 mm spacing. So our action plan is, so pins must be always placed on the grid. So if you want to place the pin, it must be placed on top of the grid only. It should not be outside the grid, or it should not be off grid. So you start it on the grid and you end it on the grid. That is what the pin requirement is. And also drawing, you can draw anything, but make sure you should not exceed the dotted area. If you exceed the dotted area will automatically extend according to your drawing. So this is our action plan. So inside that, whatever you see is the symbol, that is connector symbol. Outside we see the pins. The pin size is also matters here. Pin size, there are two types of pin size. One is short pin, which is only one grid size, that is 2.54 mm, or there is a long grid which is 3 grid length, and one more is a nil, that is zero grid length, zero length. That means you will have access to connect the pins, but you don't find the pin size. So there are three types of pins. One is short pin, long pin, or line, we also call it as a line, and then the zero length pin. Zero length pin does not have a pin, but it has the connection ability. So this is our action plan. So we will draw inside the dotted line and we will put the pins outside the dotted line. So you can do anything, but we don't want to waste the space. So first thing, I'll go to place and I will add the pins here. So come down here and you can see the pin option here. You can use the shortcut key, that is, we'll just close this, go to place and the pin. The shortcut key is shift G to add the pins. So we will go to place and then pin. So now it will ask you the pin related properties. So I want to add the 2 pins. So first, pin name, I will give pin number 1 because I don't know the name of the pin, because it is just a passive connector. We might not have the pin name. So similarly we have the pin number. This is pin number 1. As I told you, the line means 3 grid, and you have the short, which is 1 grid. And one more thing we have here is zero length. So we have so many pin properties. The first one is clock. Whenever you are creating the ICs, so we find the clock pins. So when you find the clock pins, you can use this property for the pin. Similarly, dot pins for inverter pins, we can use this. So clock inverter, we can use dot clock. So line is, as I told you, that line means 3 grid length. This is 1 grid, 2 grid and 3 grid. The length of the pin is this much big. Short pin, as I told you, the short pin, the length of the pin is only 1 grid. So this is the size of the pin. And short clock, so it comes along with the clock. The pin comes along with the clock. Short dot, the pins comes along with the not symbol. The short dot clock, so you will also have the clock along with it. Short dot clock, it is a short and dot and then clock. Okay, and finally we have the zero length. So zero length, that means yes, you will have a connection, but there is no pin, visible pin. So this directly you can connect wire here. So this is all the types of the pin. So here I am going to use line, which is 3 grid in length. So again, there are some more types, that is input pin. So if you use the input pin, so it looks like this. So there is an arrow inside that represents it is an input pin. Then we have an output pin. We don't find any arrow for output, for even the bidirectional. So output pin means only used to send the output from the component or IC. Bidirectional, you can use these pins as input as well as output pin. So this is all about, this is input pin, this is output pin, and the third one is bidirectional. Any pin, IO pin, we can say. Bidirectional means you can use it as input as well as output pins. So open collector, in transistors we can use open connector, 3 state, open emitter and power related pins. Likewise passive, it will accept all types of properties. So this is connector, I will use passive type. Width, we keep it scalar or bus. Scalar means the pin width is quite small, it looks like this, and bus means the pin width is a little bit thicker. This is how the pin looks like. So whichever you are comfortable in, you can use that width of the pin. So I will use scalar, though the bus looks very thick in on the sheet, so I will prefer scalar options. So these are the options we use. And next we have additional pins. So pin number increment for the next pin. If I click first pin, it will take it as 1. Here if I give 1 increment, the second pin will be the pin number 2. If I increment it by 2, the second pin will be 3. So if I increment by 1, it is 1 plus 1. If I increment by 2, it is 1 plus 2. The second pin will be 3. So this way we can use the pin number increment for the next section. Next section I will explain that in the whole heterogeneous component creation. So this is all about the pin properties. So I am using pin number 1. So I am using pin number 1, pin name 1, shape line, type passive, width scalar and increment by 1. So click OK now. As soon as you click OK, you can see the pin here. So the 3 grid length, you can also observe the 3 grid length. Okay, so now I want 2 pins. So click on 1 and click second, so automatically it will increase to 2. So right click and end mode. So this is how you added the 2 pins inside the particular design. So now we need a rectangular box. So I will always prefer, after one pin, at least give 1 grid spacing on the top as well as bottom, so that you can draw a proper box and make it look like 2 pin connector. So here also don't get into 1 grid only, so it looks very awkward. Just take at least 2 grid rectangular box. So to draw the rectangle, we can go to place and come down here and we can see the rectangular tool here. So I will just click on this rectangular tool, place, rectangle, and from this corner I will start clicking. You can see a small dot now, that means it is not connected to the grid line. So if you bring your mouse pointer near to the grid line or on top of the grid line, the circle size getting increased. That means it is on the grid. If you click now, it will click on the grid. So I just click on the grid and come down. So 2 grid and 3 grid, one extra grid I will leave it. And now come left side, don't drag it, just simply move the mouse, one click and then move the mouse and come left side. So it looks awkward, I'll just come one more grid and then here I will click. So right click and then done. So this is all about the 2-pin connector. So now I will reduce the working area because I don't want to waste this much space. I'll reduce the working area, click, hold and drag down to down on the design. So now click outside. Now you can see your 2-pin connector is ready. So I'll just drag the reference on top of the component and drag the value below the component. So this is how we create the 2-pin connector. So I will right click on the tab here and save this and then close it. So here we have created a 2-pin connector and we will make it save. Just click on save. Inside the library we have created the connector too. So now we will see how to use this connector inside this page 1. So we'll go to page 1 now. So page 1 is open. I will go to place and then click on the part. Now on the right side we don't have a library. That library is not yet added here inside the library folder because we just created in our project location. We will go and add the library. So click on add the library, click on add library, and now we don't have that library inside this, but we have that library on the project file. So go to the project file, go to the symbol library, and this is the power supply library. Click open. So now we have only one that is selected, and inside that we have only one component just now we created, that is connector 2. You can double click that. That connector is now inside the sheet. Right click, done. So now you can see here connector 2 is created and we are using it in the schematic. Now we are going to create a second component, which is diode. The second component here is the diode D1, that is 1N4004. Okay, so we'll go to the OLB file on the left side panel here and then right click, and we will add another component here. Just right click on this and click on the new part, and we say the part name is diode, and the prefix we will give as D. So it will be D1, D2 and D3. So click OK on this, and again we will get the working area where we are going to create the diode part. So now to create the diode, and this is a filled shape you can see here. So this is the filled shape. We have created the diode and inside that we got the fill. So that fill we need to create. So to create the fill shape, we need to create a shape, not a proper line. So we should go to place here and then we will take the polyline. Here you can see in the bottom side we can select the polyline. So go to place and click on polyline. Now we will draw this circle. I'll click here and then click till here. So if you want to get the 45-degree bending here, press shift and then you can go for a 45-degree bending. Click here and again join here. So keep pressing the shift button. So click. Now just do escape and we will recreate this. Go to place, polyline. So click 2 grids and I'll press the shift so that I'll get bending here. Here also if you come back here, just press the shift, so we will get the 45-degree bending. So now right click here, click on end mode. So the triangular is ready. So just select the triangular. I want to fill the shape. So if you want to fill the shape, select the triangular or the shape, come towards the left side, and I'll just increase the panel here. So here inside the panel we can add the part property as well as the symbol properties. So we can go to the property here and we can see this fill style here. So click on the fill style, so we'll make it solid, and now you can see that's, so the particular shape is got filled. So now we need one more proper line here in front of this, that is the cathode line. We will take place and then click on the line, and we will draw the two grid line. It's from here to here, we will draw the two grid line, right click and more. So if you want to increase the width of this particular line, select the line on the left side. So we have the line width and line style. So inside the line width, I will select it and increase the line width, and now it, that line width is a little bit increased. So this is how we create the symbol inside the dotted line. So now we will adjust the dotted line and add the pins. So what I'm going to do is I will add the pins first. Right click on the place, click on the pin. There are two pins here. One is cathode pin, that is pin number 1, which is I can use C or K, and then pin number is 1. It is line, I will make it short because the component is a small one, and we will make it passive and let it keep scalar. Click OK. So I'll place the first pin here and then press escape. I will adjust the cathode. I'll just keep it outside. Later I will show you how to hide that particular component, particular pin name. So next I will take a place pin, and the second one is anode, and the pin number 2 is anode. I'll keep it short and click OK and bring it on the left side. So I'll just click the name and drag it. Okay, so now we will reduce the working area. I'll just select the working area and bring it towards the left side. Now the pin got joined here, and the second one is also bring it towards the right side. The pin is attached to the symbol. So now extra we have on top, I'll just reduce it to bottom, and here also we have extra and reduce it to top. So if you see, for example, if your pin is shifted, just click hold and bring it up. So now the diode is ready. So here I don't want pin numbers to be visible, because symbol itself is more than enough to understand which pin is anode, which pin is cathode. So this side is cathode and this side is anode. So here the assembler or the designer, if I am the designer, I know which one is cathode, which one is anode. If you are okay, you can hide the pin numbers and pin names. So don't delete the pin names and numbers, but just hide the pin names and numbers. If you want to hide the pin names and numbers, you just come down towards the right side. You can see the pin name visibility, which is on. If you make it off, it will be hidden. Again, pin number visibility, if you make it off, it will be hidden. So first I will make the numbers off. Now you can see numbers are hidden now. And then go to pin name visibility, click on the pin name visibility. The pins will also got hidden. So you can adjust your name on top, reference on top, and value on bottom. So this is how you create the diode. I'll just right click here, click on save, and then close it. So we will see how to use it in this schematic. So select save this, and we'll go to page 1. So now click on the part. You can also use place part, or you can press the shortcut key, that is P. So you will get the right side panel. If I press P from the shortcut key, I got the library. Otherwise, on the left panel here you can see the small icon. So this icon is also a place icon. Second icon is the place icon, place part icon. You can choose that also. You can click on that also. So now we got in our library. So you can see inside the library section, the power supply library is selected. This is what we created the library, and that library has got two components. Now we have created connector as well as diode. So now we also get the diode here. So if you want diode, just double click on the diode. So diode is now inside the sheet. So if you don't want that, you can see the cathode pin, we have increased the width, but it is very big in size. So if you want to reduce it, you can still reduce. You just go to the library here. So now what we did is we have created the part, and if you want to do some changes here, so yes, you can do the changes. We'll go to the library, open this component, and if you want to update, you can do the updates. So to do the updates, we will first move the references and then you move the working area. Just select this pin and I'll close this. I will extend the left side panel, and line width I will make it first one because it looks very big in very thick in the design. So I just update it and I'll reduce the working area, and I'll attach the pin to the symbol. So then we'll bring back the value on top of it. So just right click here, save, and then close it. So by doing this will not change, but what we need to do is we just should go to the design cache as we expected in the last session about the design cache. Just click on the design cache. So we have the diode. So this diode, so we know this is the diode. Okay, so not, this is not the diode. First what we will do, we'll right click and clean up the cache, click yes. So now we have the diode here, right click, you can update the cache. If I update the cache, so say yes, and your symbol will be updated. So now you got your symbol. Now the cathode pin has got updated. So this way we can utilize the design cache. I just removed which we have added earlier. We have added from the existing library. So what I did is just right clicked and clean up the unwanted components. So all unwanted components removed. Now we have only three things. There are two components, one title block. The same thing we can see here. There are two components, that is connector 2 and diode and title block. So diode, I just wanted to update the size, update the size. Just right click on top of it and update the cache. If you update the cache, so any updates on that particular component will be updated, and it is now the latest file is in the schematic page. So this is how we create the component. Once you add it, if you looks, it needs some changes, you do the changes inside the library, and then if you want to update in your schematic, either you delete and add it, otherwise you can go to design cache and update the file. So this is about how do we create the diode. Next we will create capacitor, and we will add the capacitor. So to create the capacitor, we'll go to again library, right click on top of it, click on new part. So we say the capacitor, I just say cap, and this is C, prefix is C. So now again we got the same thing. So you can create on your own. So I will make the curved capacitor. One plate is normal plate and another plate is curved plate. We will create, either you can create vertically or you can create horizontal also. So it's up to you. Anyways, in schematic level we will going to rotate it whenever you want. So anyone you can create it, otherwise non-polarized you want, you just normal non-polarized you can create it. So two plates, normal plates of capacitor, and two pins you can add it. Otherwise you can also create this in horizontally also. Okay, so to create this we will go to the place and click on the line. So I'll just take one normal line, so which should contain two grids. So at least two grids, because in the center grid I'm going to add the pins. So here we are going to add the pin 1, the other side we are going to add the pin 2. So here will be the two plates. So this is what my plan is. So the next one is I wanted to do the curve. So if you want to do the curve, we need to use Bezier symbol. So Bezier curve, we have an option called Bezier curve, or shift Q will be the shortcut key. So Bezier curve, how does it works, we will see. So whenever first click if you do here, second click at which side you want to bend, that side you should click. So I will click the second click here, and the third click I will double click here. So what happens now, this Bezier will create an arc like this. I'll show you. Just go to place, Bezier curve, first click, and second click I will come left side, do one click, and then third click you come to bottom side. Again you double click here, the operation is done. Right click and done, end mode. So this is how we create the Bezier curve. So otherwise you can reduce the working area, sorry, not working area, the grids. So you can see the grids here. There is an icon. So now whatever design we do, that particular design will have snap to grid option. So when I draw something, it will snap to the next grid only, directly it will snap to the next grid. So if you want in between, so because I wanted to move here, I wanted to decrease and increase this particular curve. If I move this particular point towards right side, the curve will reduce. So if you want to move towards left side, the curve will be increased. So if you want to do that control, so you need to use the smooth page. What happens if I, for example, if I select this, I got two pins. So if I move on top, so I can increase this. So otherwise, if I move towards right side, the curve will be increased. If I move towards right side, the curve will be decreased. So this way also you can make it, but you can observe this, it is snapping to the next grid. So I'm unable to do a smooth changes. To make it smooth changes, make the page smooth. So this is the option where snap to grid, we just make it off. So if I make it off, now the page is smooth. So now you click and hold, select the component, click, hold, and slowly you move towards right side. You can see the curve is decreasing in a short space. So earlier it is just directly jumping to the next grid. It was directly jumping to the next grid. Now using this, you can move up and down, right and left, wherever you want you can move it. So I want this much is fine, and I'll bring back this towards the left side. So make sure whenever you have the big circle only, just leave it. That means it is placed exactly on top of the grid point. Now we need to draw the small grid line here, because otherwise you will find the air gap here. So we'll go to place and draw the line from this grid to this point. That is enough. Escape. Now you can see that is more than enough. So now we will just go back and uncheck the check the snap to grid option, so that now our design will be snap to grid. Select the point and come towards the left and come down and make it arrange the working area properly. Okay, so now we will draw the pins. We will add the pins where I arranged the reference as well as values. So we'll go to place and then click on the pin. So now the pin name, so first pin will be plus in the capacitor for polarized capacitor. Second, and the name will be 1. Instead of line, I will use the short because it's a small component. I'll just keep it all passive. Click OK. Click on the left side. Okay, so now I don't want this particular pin number visibility. Just come towards the right side. This is pin number and name. I will be disabling this because I don't want the curve itself. This denotes the next pin is positive, the curve pin is the negative pin. Similarly, I'll add another pin. Go to place and pin. So pin name is minus, pin number is 2. It is short. I'll just keep it here. So it is also the name and number visibility are false, or we have hidden it. So this is the capacitor which we have created. We'll just save this, right click and save, and then close it. Now we will see how to add inside the schematic. Double click on top of this, go to place and part, or press P from the keyboard. Go to cap which we have created, double click on the capacitor. So we created the capacitor 1, and I want 2 capacitors. I will just place 2 capacitors, right click and then end mode. So now we have created few components. We have created 2 pin connector, so we can use it for 2 for J1 and J2. Diode which we created, capacitor also which we created, so both capacitor will use the same symbol. Now we will create the regulator. So now we'll go to right click on this new part and select the name, that is regulator, and this is a transistor based component, so we use IU as a prefix. So click OK. So now we will add the properties here. We just close this. Okay, so now what we need to do is I will take the place and then pin. I'll add the pin first. The pin name is VIN. I would say this is VIN. The number is 1. So this shape, I'll just keep it line, and the type is input. So then click OK. So I'll keep the input pin on the left side. So what is our motive here is, so we will draw the regulator. We will draw the regulator pin. So this will be the input pin, that is V in, it is pin number 1. So pin number 1 and 2 just check out with the data sheet. So here I'll take first pin is input, second pin will be V out, that is second pin, and sorry, this third pin it will be usually, and the ground will be second pin. So this will be the ground. So there are 3 pins we need to create. So we have already added V in, and just increase the working area. So now I will take another pin, which is pin number 2, which is ground. So we say pin number 2, which is ground. So ground, we'll just keep it passive. We'll keep it passive and click OK and keep it on the bottom. So we'll reduce it working area. Okay, we'll maintain the uniform. So you can reduce the name here. Just I'll press select this ground name, press R from the keyboard, it will rotate, and now you can drag it down and keep it here. So now we can reduce the working area here too. So now it is V in. If you want to change the name, come towards right side. If you want to change the pin number 1, select the pin number 1. Now you can see the options here. We can change the other properties also. So here what I'm going to do is I'll just make it all caps P in, that is pin number 1, it is line, it is input pin, that's all. So now we will add another pin. So go to place and then pin, that's third pin. I just say V out, third pin, and it is an output pin. I will choose output pin. So click OK. We will keep it on the right side. So this is how we create V in, V out, and ground pins. So I'll just move the value towards either on the upside or on the bottom side. Make sure wherever it is, it has free space. I'll reduce it. So now we will draw the rectangular box. You know how to draw that. Go to place and click on the rectangle. Click on this and draw the proper rectangular box. So this is how we create the regulator ICs. We have created the symbol, which is rectangular symbol. We have added 3 pins, that is first pin, second pin, and third pin. Along with that, the very important thing is we have added the pin properties. The first pin property here is, it is an input pin. We added it as an input pin, and this is an output pin. We added it as an output pin. And the third one here is the ground, which is we kept it passive so that we can define the properties whenever it is required. So this is about how to create a symbol of regulator. I'll just save it and then close it. Now we will add in this inside the schematic. We will save this particular project, and we will go to place part, click inside the page, so it will be activated. So regulator, just select the regulator, double click on it, and you will get the regulator. So regulator is created, and now we can use the regulator. So now you observe each and every part here is we are creating the symbols and we are using it in your schematic. So the next component here we have is a register. So what I'm going to do is I'll just make a combination of it. So I'm going to use register and LED from the existing library. So now I hope you understand how to create the symbols and how to add into the schematic. So what I did is, so we have created some symbols and used it, and now we will also use from the existing library. So you can also create it. So I'll just show you how to create the symbols now. To save the time, we just take the register and LED from the existing library. So that J2 2-pin connector is already created. We will use the same thing. So if you have any questions or any doubts, just let me know in the comment box so that we can create these parts. If you are unable to create the register and LEDs, let me know in the comment box. Then we will be able to create, and I will make a video on how to create the symbols, the special symbols. So what I'm going to do here is I will just add from the existing library. So to add the existing library here, only the power supply related library is activated. Now I just want to activate all. Just select inside and press Ctrl A, so everything is activated. Now you can go for resistor. I'll use the resistor and also LED. I'll take the LED. So these two are I've saved. So I just close the place part tab. Now we got all the components which is required. The first thing is connector. I'll just copy and paste it. On the output side we get one more connector, and then we have a diode, and then we have the regulators. We have the regulator, and then we have the capacitor, and then we have the resistor, another capacitor, and then we have the indicator, that is LED indicator, and then we have the output connector. So we have all the components inside this. We know how to create, and we have created a few components. Okay, so these are the component which is created by the designer, and these two are which is already available and we have used it. This is a combination of existing library components as well as created library components. So this is the combination. You can use it whenever you have a time and you have the proper component, you can use it. Otherwise, if you don't find the components, you can create it. Most of the time ICs are not available in the library, so you get passive components like resistor, diode, LED, capacitors, inductors, regulators, and connectors. You will find in the library. You can utilize them. And ICs, most of the time ICs and driver ICs and some special connectors, you don't find it. So according to the client requirement, you just have to create those components. Now you know how to create those components and you can use it. So you also know how to use those components. So always make sure, so whenever you added or deleted, so make sure your design library is catched up, and then click OK. And if you have done any changes, you just go to that particular component. For example, so here we have diode, so that we had some changes. So you can just right click on the diode and you can update the cache if you have done manually, if you have done any changes. So here also any component, if you want to change it manually inside the library, if you have changed it, make sure come back to the design cache and select that particular component and update the cache. So this is all about how to create the symbols, how to use the existing symbols, how to how to use the created symbols inside your schematic. Okay, now we will continue the schematic preparations. As of now, we know how to get the components from the place part, which is existing library. And also we came to know about how to create the symbol and how to use the created symbol here. And now for an example, here we have used a created symbol as well as already existing symbols inside our schematic. So now our the first procedure is to prepare a schematic, which we have here. So example, we have on the project one, and you can go to the documents. So this circuit we are preparing, so just keep it open here. We are creating this particular circuit. So we collected all the components, so we will discuss about procedure. First procedure is to collect required parts or symbols, if say. This is procedure of preparation of circuit schematic. And then we need to rearrange all the component, rearrange all parts, and then we need to update the references. First thing, we will do these two things. So we will collect all the components that I think we have already done. We need to rearrange now, so we are going to rearrange this. So we'll go back to our OrCAD schematic. So now here we have collected all the required components and we will rearrange. So this is just component. I'll just keep it here on the same pane. So this is the diode. I'll bring it a little bit up so that Okay, we'll discuss about how to move, how to rotate, and how to mirror. So if you want to select the component, click on the component first. So once you click on the component, the entire component will be selected. So this is called component selection. So I'll just zoom it a little bit. If you by mistakenly click on J1, only the reference is selected. If you click on only this particular value, only value will be selected. If you want to move it, you can move only value, but the component or the part will not move. If you want to move the parts, you have to click exactly on the center of the body or the symbol. Then the entire component is selected. See now, because of the value is very far from the component, so this is the total area which is covered by this particular component. If I want to reduce that, I'll just move value just below the component and select the component. Now you can see the minimum area it is covering now. So to select the component, always make sure you should click on the symbol of the component so that it will completely select, including the reference as well as value. All three it is going to select. So if you click on the pin, only the pin is getting selected. So if you click on the component, the entire component is getting selected. Okay, now we will see the components of part. I mean the objects of the part. So here we have the first thing here we have is the reference. So this is called reference of the component. J1, R1, T1 are all called reference of the component. While creating the component, you know about the references, and this is the value of the component. These two can be editable, so you can edit it. So you can give any reference like J1, J2, J3, you can change it, or simply like CON1, CON2, connect 1, connected 2 also you can prefer it. The prefix always you try to make it single spelling so that it will be understandable. So and here whatever you see, this number is the pin number. This two in the black color, that is pin number, and inside that what you can see is the pin name, that is the pin name. And this box, the blue color box, is the symbol that is the component symbol, or you can also say it is a drawing of the symbol. And the last one here is, this is the pin. This particular thing is the pin, actual pin, which is electrical pin. And this is connective element. The box, you can see the small box, that is the connective element. So once you connect the wire, that element will be hidden, or the element will disappear. That means the connection is properly established. So these are these objects of the component or part. The J1 is reference, the black color number is pin number, and blue color number is pin name, and the red color line is the pin, and the box which you can see is the connective element. Once you connect the wire to this particular pin, the box will be disappeared. That means if the box disappeared means the connection has established properly. If the connection is not established, that means the box will not disappear. So here is the reference, and the below we have the value. So and this is symbol. The blue color is box is the symbol of the component, and inside we have the pin names. So if you want to move the component, as I told you, we just have to select on the center of the symbol, so entire thing will be selected. If you want to move it, select the component, click, hold and drag right side, top side, up side, wherever you want to drag it. If you want to leave it, just leave the mouse click, and that particular component will come and sit there. And the next thing is, how do we rotate this? So to rotate this component, first you need to select the component, not the reference, not the value. Select the component, so it should select completely, and then press R from the keyboard. That is a keyboard shortcut. This keyboard shortcut to rotate. So you have to press R from the keyboard shortcut to rotate it, or otherwise you can do the right click. You can do the right click and you have option to rotate. But and if you do right click and rotate it, every time you should do right click and rotate. So every time you need to do right click and rotate. So it is quite time consuming, so just press shortcut key, that is R. I will select the component, press R from the keyboard. So as soon as possible you can rotate. So this is how we are going to rotate the component. So the next thing is copy. So just right click and you can take the copy of the component, and outside you just right click and paste if you want one more copy of the component. So now it is showing J3, it is incremented by 2 because there is a J2 is also available in the sheet. You can see at the last we have the J2. So it will increase, it will do increment from the previous reference number. The latest reference number is J2. Now once you copy you will get the J3. So this is how you are going to copy and paste it. And if you want to delete it, right click and you can do the delete option, or otherwise select the component and press delete from the keyboard. So this is about to delete the component. The next one is to mirror. That means I want to make it flip. So if you want to make it flip, so for example I want the pins to be on the left side. So if you want to do the pins on the left side, you can rotate the component. If you rotate, the pin will come left side, but you can see the pin order, it is coming from bottom to top. I want pin number 1 up and pin number 2 down. So to do that, you need to flip the component, or you also call it as mirror the component. If you mirror the component, so its mirror symbol will be saved. I just right click here and click mirror horizontally and mirror vertically. We have two options. So mirror horizontally, that means the component will be flipped from top to bottom. Horizontally means component will be flipped from left to right. So this is mirror horizontal and this is mirror vertical. So we will do both. First, if I mirror vertically, what happens? So this reference will come down and value will go up. Pin number 1 will come down and pin number 2 will go up. So just select, right click and flip vertical. So now you can see everything is mirrored. Now top to bottom it is mirrored. So J1 was upside and connector was downside. It is mirrored from bottom to up to bottom. See one similar pin number also, top pin 1 came down and second pin goes up. So this is how mirror vertical. If you want to do it again, just right click and do again mirror vertical. It will come back to the original position. If you want to flip right side to left side, you can use flip horizontal. So select the component, it is very important thing, and right click mirror horizontally, so it will come the other side. So just right click and mirror horizontal because I want my circuit to from left to right. So if you want connection from this is how we need to connect it inside this. So you need to make it right click and flip horizontally so that we can connect the connections this way. So this is about mirror vertical and mirror horizontal. And if you want to do the both, you can right click and select mirror both option. It will mirror horizontally once and vertically once. So this is all about component selection. So you can do this also by right clicking and you can delete, you can rotate. Okay, you can also press R to rotate the references also. So this is all about the basic tools which we use. The first thing which we are using here is the selection. Selection is very important. You have to select the entire part to make any action or any command. And then second one is rotate option. So we got the two different rotate options. So one is right click, you can do the rotate. So other one is you just press the shortcut key R to rotate the component. Next one is to copy and paste the component. You can do right click and copy, otherwise you can also use Control C and Control B. Control C and Control V, if you do, you can do the copy and paste option. The next option is mirror vertical, and you can also do mirror horizontal. According to your requirement you can do this. And the main thing here we forgot is that is move option. So you can move the component by click, hold and then drag. So how do we move is to select the component first, click, hold and you can drag. So wherever you want you can drag it and then leave it. So if you leave it, it will place on that particular area. So this is all about move the component. So first you need to select. After selection you can do the move option. So to move you need to just click, hold and drag it, and then wherever you want you just leave there and select the component, and you can do press R to rotate, or right click, you can go for rotate options. So select the component and copy for control C, control V for pasting the component, or you can do right click copy, right click paste. Mirror vertical and mirror horizontal. So but before that you have to select the component first. So this is all about the basics tools. You can click, hold and drag and leave it. So this is to move. So select the component, press R to rotate, otherwise you can right click and you can use the rotate option. So the next one is select, right click, and you can do mirror vertical, mirror horizontal and mirror both options. So if you want to take a copy of it, you can right click, you can do the copy, otherwise I will select the component, control C, click outside and control V, again you can keep it. And if you want to delete it, right click on delete, otherwise select the component and delete from the keyboard. So these are all the basic tools which we need to prepare a proper schematic. To prepare a proper schematic, we will follow few steps now. The first step will be collection of the parts, which we have already done. So we say collection of symbols or parts, which we have already done. Second one is we will do rearrangements of all the symbols or all the parts properly. We will do the rearrangements. And then we go for component reference arrangement and component references. So we will do the second option here is component rearrangement. So we will take the component, I'll just zoom in. So make sure you have you should keep the component properly. Now you know the tool about how to move, select, click, drag and then leave it. So similarly I will take this on the upper plane, so I don't want to place on the same alignment, so I just make it a little bit upside here. So don't make 3 to 4, just make 3 to 4 rows kind of things, just make it one row only. I'll just open the schematic, we just follow. You can see here the center part, so we have all the components are aligned here properly on the bottom pane, and the second one is on the top pane. So we got two panes here, so this is the top, this is the second row kind of things. So don't keep the component in between, so don't keep the component here. So just make a proper component placement or symbol placement with a proper alignment, so that looks good also. And while doing the annotations, that will be very helpful. I will show you how to do annotations and what happens if you arrange the component in a different fashion and if you arrange the component in proper fashion. So we will just follow this our circuit. This is the next diode and capacitor. So we'll take the diode and the capacitor, just click on the body, just click, drag, hold and drag it. So on this pane just will take the alignment. Okay, so now we will bring the regulator. So alignment, that means so pin to pin it should connect directly like on the grid pane only. So similarly here also, so here from here to here we'll take on the top side. So this is one line and this is another line. So similarly we will bring the other components, so select, click, hold and then drag it. So on the same alignment we will do that. So go to right side again, you bring the component. Now you know how to rotate the component. You can just press R from the keyboard, because I have selected the component, press R from the keyboard. So now it is rotated, so we can keep it here. So similarly we'll bring the LED, so rotate, press R from the keyboard, rotate it, and with respect to this component we aligned it here. And we will also have the connector in the output side, we will also connect that output side here. So here one pin we will connect it to the output voltage and another pin we will connect it to the ground. So this way we can make the simple circuit. So zoom in, zoom out, so just press Ctrl and scroll from the mouse wherever the mouse pointer is there, so that area will be zoomed in. So here if I keep the mouse pointer on top of the J1, so if I click Ctrl and scroll the mouse, so the J1 component will come in center and it will start zooming in. Now if you want to move the if you want to zoom from the D2, so bring the mouse pointer on D2 component and press Ctrl and scroll from the key mouse, so that D2 component will be zoomed in. So this is how we can zoom it using the mouse and keyboard combination. So and also we have got a few zoom buttons here, so using these zoom buttons also you can do the zooming in. So first one option here is the plus, that means zoom in. Second one is zoom out, and the shortcut key we can observe here, the shortcut key is I. You can see the shortcut key is O for zoom out, I for zoom in. So here you can see that is I for zoom in and O for zoom out. So we'll just click on the plus button here, so it will zoom in from the center of the sheet. So it will zoom in from the center of the sheet. If you zoom out, it will zoom out from the center of the sheet. Similarly, if you want to use the keyboard shortcut, I'll press I, so it will zoom from the center of the screen. If you press O, it will zoom out from the center of the screen. And otherwise you can bring the mouse pointer on top of the particular component, and I'll keep the mouse pointer on J2, then I'll press I from the keyboard, so that particular component will be zoomed in. It will come in front and zoom in. Similarly, if you want to zoom out, press O from the keyboard, it will be zoomed out. For example, if I want to see the diode, bring the mouse pointer on top of the diode and press I from the keyboard, so that particular component is getting zoomed in. So I just press O for zooming out. So these are the two options you can use, zoom in to zoom out. And the third option is zoom to region. So zoom to region, if I select this, I will choose the area. So for example, I want to only zoom J1, just select the J1 component and that particular area will be zoomed in. So here what I did is I just selected click and select the area and leave it, that particular component is zooming in. If you want to still zoom in, so you can zoom in like this way, so 1 and 2 will be zoomed in. So I just click on zoom out or O from the keyboard. So similarly, so we can go this two parts. If you want to see, select that only two parts, only two parts will be zoomed in properly. So this is all about zoom in, zoom out. So and you have the last option inside the zoom in is zoom to all. So if you click on zoom to all, the area where all the components are placed along with the title bar will be zoomed in. So our top side area is neglected here. Here we don't have anything, so it will be neglected. This is all about zooming in and zooming out. So now we will do the rearrangement. So rearrangement is already done, and the second part is we can go for reference update. So for example, if you see this is J1, so if you want to make it J2, you can make it J2, you can make it J3. According to the schematic, you can do the component updates, component reference updates. So just select the particular component reference, double click on it, and here instead of J1, any name you can, if you want, you can give. For example, if I want to give that as a connector CON1, so you can give that CON1. So as soon as you select that CON, the underline will come. That underline says this particular reference is generated by the user, that is designer. Okay, it is not a computer generated, it is generated by the designer or user. So if you want to make it computer set, just select the component, right click and make sure it should be user assigned reference and unset it. So now click outside, so this particular underline will be removed. And now, so this is just like it is manipulating, it is just like a computer generated reference now. So we will change it to J1 back. So this way you can change your name. So once you change it to J1, there is an underline, so just right click here, user assigned reference, unset it. Sometimes underlined components will not be identified by the PCB board, so sometimes it will not accept the footprints. So there are few options, few disadvantages of whenever you have underlined, so make sure you make it unset. So if you are okay with that, you can continue. So if no errors and no warnings, you can continue. So it's diode D1, that is enough. D1 is enough, and C1 I'll just make it C2. So I'll show you about the annotations. So I'll just make it C2, and this one I'll make it C1. Okay, so just make it under user assigned different and unset, and this user assigned difference is unset. So this is U1. Some people use as IC1 also. If you are okay with that, it's just leave it. So you don't have to change. That is the very important thing here. Just R1, double click on the reference, you can change the reference. So similarly for D2, that is LED2, some people use LED1, LED2, so you can use LED also, otherwise you can use D1, D2 also. So J2 is also available. Okay, fine. Next what we will do is, so we will update. We have done the reference arrangement. So you can do the reference arrangement. For example, if you want to keep the arrangement here, you can keep it. Some people uses on the right side and left side method, so you can do that also. So for vertical components, we usually keep top and bottom. For horizontal components like this, so we'll keep it right and left side. So you can see this capacitor top and bottom, we can arrange the reference as well as value. So it's just come towards right side, you can see the regulator is horizontal component, right, and right side we left side we have a reference, and right side we have a part or value. So this is also R1 is horizontal component. If vertical component, I'll keep reference on top, and the value will be on the bottom side. So this is all about component reference arrangement and component value arrangement. So the next thing what we need to do is update the update value. So updating value has got a few techniques or tips I will give you. First thing, you update with a unit value. So unit value, for example, if we have a register, so if you have a register, you know the register unit value. For example, it is 1 kilo ohms, 1 kilo ohms, or it will be at 500 ohms. Okay, so ohms is an unit. So first priority is give it to the unit value of the component. If you know the unit value, just give the unit value. If you don't know the unit value of the component, at least you know the working voltage. So that is working voltage. That is working voltage. Okay, so if you still don't know about the working voltage, at least you know about the component part number. Part number, you can update it. If you are not done any part number or bill of material, if you are not aware of it, at least you should give the component name or the part name. These are the priorities we will give. So most of the component will have the unit value, so we will provide the unit value. If there is no unit value, you know at least the voltage range, how much voltage is flowing inside that particular component. Even if the component is not not associated with any voltage, you can give the part number. If you don't know the part number, at least you know the part name. For example, for diode, you don't know unit value, you don't know working voltage, you don't know part number, and finally at least you will put it the part name as diode. So this is how we update the value of the component. So first thing, connector 2. So I'll just double click on the values to change or update the value. Double click on this value. Instead of connector 2, we'll give 24 VDC. So this is what the voltage across this particular component we are transferring. So diode, we don't know voltage, we don't know unit value, we don't know the part number, then you can keep it diode. Here I know the part number, that is double click on that, and you can choose 1N4004. If you know it, you can update it. So meanwhile, I'll update this part number. And capacitor, so you know this capacitor value, so you can see this is 100 microfarad, so we'll assign it 100 microfarad here. So 100 microfarad per center. So this is about the value of the capacitor. And also if you know the voltage across this particular capacitor, we can also mention 24 volts and 100 microfarad. So regulator also, we know the voltage, that is 5 voltage. So if we have the part number, we can go for part number. 78L05Z, that is 78L05Z. So this is the part number of the regulators. So capacitor 2 here, it is 0.1 microfarad. So double click on it, so we can go for 0.1 microfarad. And resistor value is also given here, it is 1 kilo ohm resistor. So I just say 1 kilo, and that is the registration. So register value of the register. So next thing is the LED, which required a red LED. So the name you can change it to red. So double click on LED, we just make it red LED. So finally we have the output. So we have got two outputs here. So I would say this as output, or you can also say V out along with the ground. So you can separately, you can do the ground and V out, or you can give connector 2 also. So better I'll give connector 2, CON2. So why? Because so in this pin I'll give the 5 volt output, in this pin I will give the ground net. So there is no common net here, so we have the distributed net. So I'll just give connector 2 here. So but here if you see, it is 24 volts. This is also 24. This is minus, but this is plus. So this is about component reference arrangement. So what we have done, we just recall it here. So we have done, first thing, we have collected the components. First thing, we collected all the parts. Second thing we did, arrange all the components, arrange all parts. And the third thing here is arrange references. Fourth thing here is we have updated the references, updated the reference. Fifth thing here is arrange value, component value. And the sixth thing here is update the value, component value. So these are the things which we have done. So first we collected the components, successfully understood. If you have any question, just let me know in the comment box. So next one is arrange the parts. We have arranged the component properly. The next third one is arrange the references, update the references. So arranging the references, so if you have a horizontal component, so on the left and right side you can give the arrangement, reference arrangement. If you have vertical component, so if you are placing this vertically, on top I'll keep the reference and bottom I'll keep the numbers. This is how arrange the reference and arrange the value will be done. Update the references, if you want R1 R2 you can change it. Once you change it, it'll give the underline. So you just set it to the unset the computer generated names, user generated names, and then update the value also. And update the value, we got 4 priorities. The first priority is unit value. So if you have a capacitance like 100 microfarad, picofarad, those are all unit values. If you have a resistor 100 ohm, 200 ohms is a unit value. So first priority is unit value. Second priority is the working voltage. So for example, this DC jack works under 24 volts, so that is for second priority. Third priority will be of the part number. So part number, if we have done the bill of material, the part number can be used as a value of the component. If you don't have all three, at least you give the component name itself as a value of the component. So this is all about we have arranged and make a proper and try to make the proper schematic. So now we will discuss about annotations. Annotation is the process of applying the references automatically here. For example, if you have a C2 and C1, so it will remove that, and in order wise it will in either in increment order or in any other order, whichever you select it, in that particular fashion, that annotation will annotate or give the references to your components. So to apply this, we should go to the file hierarchy system on the left side. So you know this DSN file, first make it, save it, and then you right click on the DSN file, and the first option you find here is an annotate options. Click on the annotate option. So now it will take you to the annotate pop-up. So now here what we need to do here is just select action. Under the action, you just reset the part references to question mark. So first we will remove it, all the numbers. For example, if you have R1, so that will change it to R question mark. So if you have a C1, that will change it to C question mark. Later what we need to do is we need to again come back and do the annotate with the incremental reference update. So now our question mark will change it to R1, R2, R3, C1, C2, C3. This way that annotation will give the number. So the annotation has got some inbuilt rules or some attributes. So annotation, so if the components are in the same aligned order, so for example if the components are in aligned order, so first thing it will give, if it find the same two components, first one is C2 and second one is C1, so this will make this as an incremental order, that is C1, and the second one will be C2 if it is an incremental order. Similarly, if you observe, there is a D1 on top and the D2 is on the bottom. So these are not on the same aligned order. One is on the top, another one is on the bottom. So in this fashion, whichever is on the top, the first it will assign the references to that. So D1, and the second it will be D2. So even though if the D1, for example, if the diode from, for example, I'll keep the diode 1 here, D1, and I'll keep the diode 2, second diode, somewhere in the left side. So on the horizontally it is from left to right, so it should first D1, D2 should be D1 and D1 should be D2. No, it is not like, it will not happen like this. So whichever is on the top side, so that the component will get the first references, and whichever is bottom, that component will get the second references. For example, what we do, we will change this D2 to D1 and then we will check it. So we will change the D2 to D1 and D1 to D2. So double click on it and we'll make this as D2. Okay, so this is D1 and this is D2. So as I told you, on the horizontally from left to right, if I want an incremental order, so the left component will be given first name and the right component should be given D2 option. But here before that, if the components are on top and top to bottom, the top component will be named first, that is D1, and second component that will be a D2. So here in this case D1 and D2 are vertically arranged, so this will be D1, it will change it to D1, and D1 will be changed to D2. So but in horizontal order, if both are on the same aligned order, so first will be C1 and second will be C2. This way the annotation will work on. So we will see our expectation here. So if you have done random component placement, and if you want to change all the component references and make it order, annotation will help you to make it in an order way. So our expectation is here it will come C1, this component should be C1, and the second component which is aligned, that must be C2. So what if the C1 is little bit up, so it will not change its order, we will see the both. Okay, and similarly if the D1 is on above the D2, if it is above the D2, this D1 will not change. So if it is below only, it will change. Just I'll right click here, unset the user assigned reference, and here also right click the component and unset the user references, right click, unset the user references. Okay, so annotation, our expectation is D2 must change to D1 and here D1 must change to D2. So here C2 must be C1, C1 must be C2. So first what we need to do, we should go to the DSN, first save the file on the left side panel. In the file hierarchy, right click on the component, annotate it, and first what I am going to do is I will reset the part reference to question mark and then click OK. So then again click OK. So you can see now each and every components are question marked. J question mark, D question mark, C question mark, everything has got changed to question mark. So now we will do it again, right click, annotate, and now we are going to select incremental reference update. So click on incremental reference update, click on OK. So our expectation is, now you can see the expectation we have achieved. So here there is a D1, it is updated because it is one step up. So here the D2. So in the same alignment order, C1 and C2 got aligned. So we will change this to C1 again, and we will change this to C2. Okay, so now what we do is Lancet. So we will bring this C1 little bit up. So now what happens, if we expect this should be C1 and this should be C2, it was not going to happen because this component is little bit on the height, it is on top, it is not aligned to the C2. So now this will reference first, the reference will be given to this component first, and the second the reference will be given to the another component. So we'll bring it up and we'll try to make it, right click, annotate, and question mark it, click OK, and then click OK. So now you can see all are question mark now, and go back, annotate again, click on incremental order and click OK, and then click again OK. So now you can see this is still C1 and this is C2 because it is not on the same plane or aligned order, it is top, it is bottom. So first priority is goes to top side component, second priority is goes to bottom side components. So if both are on the same aligned order, so the first priority is for first component from the left to right. So we just do it again, annotate, question mark, click OK, and again click OK. So now everything is question mark. Now we'll save this component and then select, right click, go to annotate. So I would recommend you to go with all other options also. I'm just showing you the question mark and incremental order. You can also check with unconditional reference update, add intersheet references, those all you can practice and check it, what will be those output. So this is how now C1 and this will be C2. So this is the application of an annotation in your schematic. For example, if you have a multi-sheet schematic, if you are working on like of 10-15 schematic pages, so you will not be able to change each and every references by manually. Yet you can make it, but it will consume a lot of time. So to avoid that, you just go with an annotation option. So annotation option is the best option to understand and give the automatic references to your components. Okay, so this is all about annotations. Now we will discuss about component wiring. So before creating the component wiring, so we will take the common ground. So go to place and select the common ground. I will choose ground capsim and make sure the name should be GND. So click OK, and then I'll keep just below the regulator and make all the ground connections connected to common ground. Okay, so to wire these components, first we should know this is how we need to wire it. So this is how we need to wire it, and also we need to give the wire names. Okay, we'll come back, and to wire just go to place and click on W or wire. You can see this is the command to connect the wire. Our shortcut key is W. So otherwise here on the left side panel you can see this icon is used to connect the wires. So we'll bring it up. So we will use the written concept. Just zoom in, and I'll press the W from the keyboard. The mouse pointer changes. I will start wiring. So click on this particular box, that is connective element, and now you can see the wire. So once you finish the connection, so click here. If you want to turn, click and then come right side, so left side, up side. So just click on. If you don't click, what happens we will see. For example, if you are not clicking, so take wire. So if one click, so now if you don't, it will work on right side and top side and straight. So if you go here and then if you don't click, the entire wire is shifting. So click if you don't want to shift the wire, click and then you can draw it. So this is just a drawing, so just click and then connect the wire. Okay, so here I will just rotate the capacitor here, press R and rotate it. So I will update the component reference and component value. Okay, so now we'll take the wire, connect the wire to the capacitor, and this is now the written path. So written path will be this way. I'm going to arrange, select it here. So this is all about one side wiring. So we have the line also and written also. Similarly, you can reduce this. So select it and bring it down. So if you are bringing it down, make sure you can bring all other component also. So okay, fine. So now take the wire and give the input to the voltage regulator, and from the ground select common and common ground. This is how we do wiring. And here we will rotate the capacitor and make sure the capacitor is aligned to the other capacitor. You know why? Because of the annotations. So select this wire, connect it, and here also you can connect. If you find it is too much, so just you can reduce this side also. So you can reduce till, so make it short, not a problem. Click on the junction and reduce it. Okay, fine. So you can come towards left side also. Click, hold and drag, click, hold and drag. This register capacitor also. Okay, we'll arrange the capacitor on top of the component, and on bottom we'll keep the value. Okay, so we'll bring the resistor and the same pin, connect the wire, connect it, and an LED we just bring it just in front of the C2. I'll press the W for wiring and connect it, and this also we will connect. And finally we will take the output. So you can see that output is coming from the output of the regulator. So it is connected from here, because so here we find the 5 volt and the 5 volt is connected to the J2 connections. And if you connect by mistakenly from here, so what happens, you don't find the 5 volt here, because across this resistor some voltage will drop and you will have the less than 5 volt here. So if you want exact 5 volt, connect it to this particular junction where you will get the complete 5 volt. So this way we can connect the output, that is connector. One side we need, we'll go here and connect it for 5 volts, and bottom side we need it the ground. So we have got both options here. One, this connector has two pins. One pin is connected to 5 volt and second pin is connected to ground. So you can take it for your any prototype or for any reference purpose. We can use this particular connections. So that LED indicates that there is a proper DC voltage or the linear voltage is flowing across this output. So this is all about your circuit schematic. So we have just developed the same schematic. We have done the component collection, and then we did the component arrangement, reference arrangement and reference update, value arrangement and value update, and then we did the wiring. So the next important topic here is wire naming. We also say it as wire naming, or we also say it as net naming. wire naming or net naming. We also say this as net alias. Alias refers to giving another name to the net. Here the net and wires are same. We call it as net and we call it as wire. Both we call it as. We should give the name to the wire or name to the net. Naming another name because this particular nets or wires will already have one name. I'll show the name. So just click on any wire. Now you can see that particular name is having particular wire is having a name already. Just bring mouse pointer on top of the wire. We can see there is a wire name. That name is N02 502. So this is computer generated net name. If you check it, the other net name, that completely the net name is different. So if you come in front of here, the net name is different, which is N02514. So this is again a different net name. So computer has already generated one net name, so we need to update that according to our requirements. So we don't know what is N00 something, so we use our own net names. So I'll select the segment of the wire. So here in this wire, I'll name such a way that I should understand, and also whatever it is flowing inside that particular wire, I just name it. Here it is just flowing 24 volt DC, so I'll name this as 24 volt DC. Select it and press N as a keyboard or go to place, and you can go with net alias. As I told you, net alias because there is already a computer generated name. I'm giving another name that I wanted to understand it. So how much is flowing inside this, so I'll give another name that is called net alias, and the shortcut key is N. So click on this, press N from the keyboard, it will give you the net alias. So here 24 VDC is flowing. I'll just give 24 VDC as a net name. So if you want to change the size of the text, you can change font also, you can change it here, color also you can change it here, rotation also you can do it. So these are the tools, you just practice accordingly. I'll just change the net name size. I'll just make it 5 and then click OK. Again I'll click OK. So 5, it looks small. So if you click somewhere, it will not place. It is a wire name or this is the net name. You have to click on that particular net only. I just click on this particular net. Now the net name got changed. So escape and then bring the mouse pointer on top of the wire. Now it is 24 VDC. Otherwise you select it and come down here and check the net name is again a different. Click here and go down. Wait. So click on this segment. Now you can see here the net name is 24 VDC, which is updated net name. Similarly, at this point we know what is the voltage. I'll just say 24V. I'll just follow the document. So there is a document. Okay, so double click on this, I open it. Oh, so here they have given 24V and here 24 VDC. So this diode is used to block some unwanted signals. Okay, fine. So we'll go back here. I'll just remove this and again you go back and cross check. This name is again turned back to the original name that is given by the computer. So select it, press N, and they said it is 24V only. I'll just type 24V only. At this corner, at this point or at this node, I'll name this as 24 VDC. So select it, click on this. That means this entire junction from this diode to this pin and the junction wise here also, that everything is 24 VDC now. So the output, we have the 5 volt DC. Select it and press N from the keyboard. It is 5 VDC. Say 5 VDC and click on this, and this entire thing will 5 VDC. So it is also 5 VDC and this is also 5 VDC. This is the output. So after register we have got some wire. You can name it. I'll name this as LED in or D in. So we say LED in. Select enter and place in. This is an LED in wire. Okay, fine. So on the bottom side you can see it from here. This is, and this wire, all the wires are commonly connected to ground. So if you connect to ground is a global connector, so it will automatically change the name of this wire to ground. So you can see here the name of the component, or then the name of the wire is now turned to ground. So here you can see. Okay, so this is the ground names. Because we have already used the ground connector, the same name is applied to this all wires as GND. So this is all about preparing the proper circuit and wiring, and also giving the wire names. So if you want to select the entire circuit, you select an entire circuit, and whenever you bring on any component, the mouse pointer will change, or icon will change, and it will be in a move command. Click, hold and move, the entire circuit will be moved. Now I'll just bring it in at the exactly center and then click OK. So zoom it. So this is the entire circuit which is we need to prepare. I'll click on save, go back here, and you will get the star. Click on save. Make sure you should the star should go, so that it is saved latest file. This is the latest file which is already saved. So once you finish this creating the schematic preparations, we will do the design rule check. So before going to design rule check, we will update our design cache. Right click here, clean up the design cache, and then everything is fine. So then our software is lightweight. Now we can go for DRC, or that is also called as an ERC, that is electrical rule checking. So in the electrical rules checking, so we will have some background about electrical load checking. For example, in electronic components, you will be having different types of pins. For example, this particular ICs might have an input pins. This IC might have an input pins. It might have an output pin. So these are all unidirectional pins. Input means only input is allowed on that particular pin. We can't take an output from that particular pin. So if you are connecting any output connector to any another input connector to this input connector, or output connector to another output connector, you will find the errors. So we will also have a component of pins like bidirectional pins, and there are some pins which are passive, and there are some pins which are power, there are some pins which are ground pins. Similarly, the other side, so we will be having unidirectional input pins, and then we have a bidirectional, that is IO pins, and passive pins. Something like if you are connecting output to the output of another component, it is clear case of uh, error. So because it is also going output, and here it is also coming output, so you cannot get the signal. So schematic will find out those kind of signals if unidirectional pins are connected this way, output to output or input to input, so it will give an error. So this is one type of example I am just giving you here. And the second type is you can connect unidirectional, because it is IO, sorry, bidirectional, it is IO. So sometimes you can use it as an input, sometimes you can use it as an output pin. Also you can connect it to passive pin that doesn't have any attributes. So this is one type of example, so that OrCAD software will identify these kind of connections, and it will notify you, or it will inform you through the ERC error. And the next thing is, if you have a circuit somewhere other, if you forgot to add the junctions, if the some junctions are missing, it will ask you a questions about should I add the junction or not, this way. And some components, for example, if you are adding some component, I'll just take a register example, and by mistakenly you have added multiple components. So you can see there are two components, R1 and R2. Both component are connected here. So this will be an overlapping. If you have overlapping, so just click and drag and check it out, because there are two components. So these kind of situations you will see the component overlapping error or warning. And apart from that, if you have not connected anything, so for example, so this pin is not connected, it will also check the no connection pins. So that says this particular component and particular pin is not connected to anywhere. So, and also if you have started the wiring but you have stopped somewhere in between, it is not connected to anywhere, so that means the wiring is started but this wire has no end. So this comes under single net node, that means it started but it has not end. And if you have not done any naming to the wires, so that all wires all comes under non, otherwise I can say that wires will, we can get the report of the wire or net naming. So there are many things. If you don't have a ground or if you don't have a return, so you will also get the no return or no driving source error or warnings. So we'll check for this particular circuit whether what are the errors or warnings we will get it. So select the DSN file, and if the circuit is not saved, make sure there is a star mark here. Save it before doing any operations. Select it and save it. So DSN, select and then save it. Select the DSN, go to PCB and select the DRC. We have the option called design rule check. So if you click on this design rule check, PCB design rule check, we will be having options here, different options on the left side panel. You can see in the left side panel we will have different options. So in that we need to select rule setup. Select the rule setup. So click on the rule setup. Again we got two different types of rules. One is electrical rules, second one is physical rules and custom rules. I will just uncheck the physical rules. Physical rules can be applied when you have the physical footprints applied or connected to your circuit. So I will only check the electrical rules. So inside the electrical rules you can see I will check for the single node net. That means the net has start but there is no end, or it is not connected anywhere, it is disconnected in between. That's those kind of things we will check. And the next thing is check no driving source or pin conflicts, as I explained you about unidirectional and bidirectional pins. If you have any conflicts it will check that. So if you have a duplicate net names, it will check out and it will inform you. If you have any off-page connector which we have not used and not discussed, if you have any off-page connector, it will check out off-page connector, hierarchical connections, unconnected bus nets, and unconnected pins. As I told you, that's if any component has no connection, pin has no connection, it will also inform you. Just have to check that boxes so that you will get it online. That means while creating the schematic itself it will show you these are the errors you are, or you are getting it. So just make it all on and then click on apply and then click on run. So once you run the DRC, if you observe on the left side panel you have got the output folder. That output folder was empty earlier, now it has filled with the DRC. So I just repeat it, right click here, otherwise select this and delete. So now you see there is nothing inside the output folder, which is empty now. So select the DSN, go to PCB, select the DRC design rule check, go to the rules and select all. Only in electrical rules, physical will come once we apply the footprints. So click on run now. So once you click on run, you can see the output. There is an output with the DRC. So I'll double click on the DRC. One more tab will open here. So you will see the report of DRC. We don't have any errors and any warnings here. So we will make some mistakes intentionally and we will check it. So what I'm going to do is I'll just remove this particular wire and I will add small piece of wire here. So, okay, and then so I'll delete this LED in name, so we'll get the report of that. Okay, now we will try to check the DRC. Select DSN and save this. Click on the DSN, go to PCB and click on design rule check. I will check run electrical rule and click on the run. Say yes. And now you can see the marker. This is DRC marker, we say that's blue color. This is called DRC marker. So go to the outputs in the DRC, double click. Now we will find the warning. So here it comes under warning. So that says net has fewer than 2 connections. That net has connected. You can see this is a single node net. That means it started but it is not connected anywhere. So apart from that we don't find anything. So I have not checked it for a report. So we go to DSN, go to PCB and design rule check. So to get the report, I will select the report here. So come to the report setup. So inside the report setup, I want report all the net names. So I will be able to identify which is assigned by the designer or which is assigned by the computer. So enable this. If you want any off-grid objects, if you have, select this. In hierarchical of 4 connections, whichever is applicable, you just click on that. So you don't find these two in our project report hierarchical ports. We didn't use upphase, also we didn't use misleading tab connections, also we are not using. So I'll just uncheck this box. So I want to see that the net names, if any net names are deleted or removed, and off-grid components. We'll just make the off-grid components. So off-grid components just means we'll add the off-grid component first. I'll take a copy of this and paste it. Usually component will be off-grid. I'll just make the page smooth and small movement I'll make it. So you have the fish eye. So we can go to view and you find the fish eye here. So you can see the grid here. Just click on the fish eye on this. You can see that little bit darker grids here. Okay, so any component you just whenever your snap to grid is on, you just copy component and paste it. I'll just copy this diode and paste it. Now you can see the pins are aligned on the grid. You have the grid point here and the pins are aligned on the grid. So but this is not aligned on the grid. I'll just zoom in. So you can see there is a grid. This is the grid. This is the grid. But your pin is not aligned on the grid. This is off grid now. Similarly, the other component you see, this is properly aligned on the grid. Pins, you can see here is the pin, here is the grid, here is the grid, but here is the grid. This particular pin is properly aligned on the grid. So we can do wiring. For example, if I take a wire, so I can do the proper wiring this side, but I can't connect to this particular pin. So that is why this is off grid. So always make sure you have the on grid components. Okay, so now we will check with this setup. So go to select DSN, go to PCB design rule check, and in the rules I will all on electrical rules. In the report as I asked for report for off-grid object, there is one off-grid object, so we can get the report of that particular off-grid object. So I will uncheck the physical because we don't have any physical related components, or we don't have any footprints. Okay, so just click on apply and then click on run. So it will update the existing output. So click OK, say yes, and now you can go for DRC. Just open the output DRC file. So now we got the report here. There are 3 different, either you can say warning, error, or question, or information. So it is clear case of warning where it has got net has fewer than connections, and the net name got changed because we have not assigned, we just draw the unconnected net. And the next is J3 page 1 is off grid. You can see this is off grid object. J3 is now an off grid object. And apart from that, we have also the reports, the net name reports. We can see the ground which came from the global connector ground 24V, which is we have manually added the name 24VDC 5VDC, and these two are the net names which is generated by computer and not changed by the designer. So this way we can see the net names report also. So these are the three to four things we need to update. We will do that. So here in the C1 section we just remove this connection, and this particular wire has got different net name that start with N. So and also it has got no connection, fewer than one connection it says. That means it is no proper connection. I will connect the wire, join it, right click and done. And now we will go back and check it, because one net name has to be gone, that because the net name is changed to 24 VDC. So we will check the DSN, save it, go to PCB, and then go to design rule check. So we will run the setup also, click on run, and now the marker should go off. Now you can see there is no marker here. We will check out inside the DRC. See, now we don't find any single node net. So you can observe here we don't have any single node net, and also now we are only left with N020, only one net name we are left with. So we will rectify that net name also. So the net name is here, so we have not done net name. So how to identify? So just go to the DRC. So just copy this net name, copy the net name, and go to DSN. Inside the DSN, that is inside your file system. So inside the DSN you have the filter option or find option. So here you just paste your, I don't find it is okay. So just go to page 1, and you have the, no, it is not activated. Search box is not activated here. Here again we have one more search item. Select the search item here. So here you can see the icon search button. So click on the search button on the right side. You paste that net name, and I will just select find option. As soon as you click on find option, we should find the net name. So on the bottom side you can see the nets. I'll just increase this working area here. Here I'm talking about in this bottom area. I'll just bring it up. You can see the net name. Here there is a net name, result of the net. So you can double click on this object ID, double click, and now inside the screen you can see that particular wire is what we are searching for, that is N0209. So this way we can identify. What we need to do is, from the DRC we need to copy this net name, right click and copy, and go back to your schematic, and in this inside the schematic I'll just close it and reopen, because okay, that's fine. So inside the schematic, so you will have, okay, so you will have a find button here. You can see there is a find button. I will click on that find button, and on the right side paste the net name. Find what? Find this net name. Click on the find. Once you click on the find here, you will see the result on the bottom side. If you don't see it, just drag it up, so you'll get the object ID. Double click on this particular object ID, so your wire is selected and it is in front of your screen. I just close this. Now you identified this, and you just could do the net name. I'll just zoom it and select this wire, and press N from the keyboard. This is LED in, and then I'll place the LED in here. So this is your net name. I'll just close, save it, and reopen the project. So double click. Okay, that's fine. So now we will run the DRC again. Go to the DSN and run the PCB design rule check and the electrical rule, and then run it. So now we don't find the electrical report, anything which is starting from N. We'll go to DRC, open it, and inside this you can observe there is nothing which starts with N. and then we have only one thing, which is off page connector, which is reporting this particular object is off page. So we'll bring it on page, on grid, sorry, off grid it is, we'll bring it on grid. So to bring it on grid, we just click and move it a little bit, so now it is aligned on top of the grid. To check it, view, go to fish eye. On the fish eye, now you can see it is aligned on the grid lines or grids. It is aligned properly on the grids. Okay, now you go and cross check the DRC again, save the file, select the DSN, go to PCB, and select design rule check, report for this, and click run. Okay, fine. So now we will click on the DRC file, open it, and we don't have any such errors now. You can see here, electrical nothing, single node nothing, unconnected bus nets nothing, off page pin to report connections of grid object, and we also have the net names, which are all net names are properly given. So this is how we identify any errors or any warnings which you face inside your schematic. Now J3 is aligned on the grid, so I just don't want, I just for reference I use it, I just delete this one. So we'll take the zoom to fit option and select this part. That's it. So this is all about design rule check. Design rule check will help you to identify the warnings. There are few types here, so it will identify the warnings, and it will identify the errors. You must clear the errors, or you must rectify the errors. Warnings not necessary. Few warnings you can neglect, based on the practical impact on your PCB. So if it is having any issues, or if that particular warning is giving any issues in the physical level, so you will be able to rectify those warnings also, and if any normal, you can neglect it, but in certain conditions they should not give any effect on your PCB. So the third one is, it will ask some questions. So if the if the software has got some confusions, it will ask some questions to you. So it's your decision whether to keep that or whether to rectify that. So these are the three things we will face inside the schematic as a electrical rules checking. Okay, now we are going to study about the bill of materials. So initially we will create a primary bill of material where we have a very few details about the component. For example, we will be having the serial number. By default we will have four things. One is the serial number, and second one is the quantity, so how many components were required of same same value component. And the third one is the part reference, that is the J1 R1 C1, that is a part reference, and then we will have part values. So these are the minimum requirement of to generate any proper bill of material. At least minimum things we need is either reference and value. So these are the at least required things to make a proper bill of material. So now first thing, we are going to export this minimum required bill of material, and later on that we will do the research, and whichever component is required we will update all the details. So first we will see the minimum bill of material. So we should go to the DSN file on the left side panel and go to the tools and click on the bill of material. Now you can see there is a bill of material, so click on the bill of material on the tools. So once you click on the bill of material, so you can observe here we have the header. Inside the header we will have four items. First one is item, that is equivalent to serial number. Second one is quantity, how many number of quantities are required. And third one is the reference, that is component reference. And the last one is part value. So these are the string, so it will fill all particular data related or particular component related data inside this Excel sheet. So I will click on the Excel sheet, and this is the location where you want to save your your bill of material, that is primary bill of material. So okay, we will go back to DSN file, click on the DSN file, go to tools, click on the bill of material. Make sure you have the four headers here. So header meaning that inside the Excel sheet, so you will be having the header. So that header, there are four elements in a header. First one is item, second one is quantity, third one is reference, and the fourth one is part. So the all four will come and sit inside the header of your Excel sheet, and these are the commodities are particular detail about the each and every component. So for example, item number 1, 2, 3, 4, and the first one is J1, J, that is connector, the reference is J1, and value will be displayed inside the Excel sheet. So this is what this particular header and the string will represent of. So where you want to save this bill of material, so we have already created the bill of material folder, so we will go to that particular folder, go to browse here, so go back to your project location. Inside the project location, so we will be creating a bill of materials. So we will go to the desktop. Inside the desktop we have got project 1. Inside the project 1 we will have the folder called bill of materials. If you don't find it, at least you put it under the documents. So select the documents, you just write the project name, or you can write even bill of materials. So I'll give the project name here. It is power supply design. Yeah, it's only the power supply. I'll just click on open, and if you want to see in Excel sheet, just open the Excel, select the option called open in Excel, and click on OK. So as soon as you click on OK, so Excel will ask you to pop up. So just click on the Excel on the bottom side. So now we have the detail about the components here. So that is, these are the primary details, and also you can go and check in the output of left side panel in the output folder along with the DRC. So BOM is also updated. So the BOM is also updated inside that particular document. So inside the document folder, power supply.bom is also created, and that we can witness in the output folder of your project hierarchy. So this is all about how to create the primary bill of material, and we will review the Excel sheet. So now you can see here, so this is the project sheet name, and whenever you have created this project, that date is here. You can see the date, and now we got the bill of material of page 1, and you can see the item, that is the first column. Second column is the quantity. So here we can see these are from the header of the BOM. So the next one is the reference, which we have the C1, C2, D1, D2, J1, J2, and R1, V1. Like we also have the component value or part value we have. So if you want, you can edit. So I will just edit it. I'll just remove these things and delete. And I want to edit this particular header. We will increase the font size. I will increase the header font size, and I'll make it bold, and we'll make it color also, and we will also add the borders. So these are the basic things. You just do it just to make it proper visibility. So reference we will double click, and then part value will double click. So this is the minimum bill of material required. So these are the things. If you don't want, just delete it. Delete these items, right click and delete these items. So now we got the proper bill of material details. So first thing we have items, then second thing we have got the quality, and third thing we got the reference, and fourth thing is the part. So that's just save. I'll save this particular BOM. So click on the save. It'll ask you the location where you want to save. Say yes, otherwise I can do save as also. Go to save as, and you can make it Excel workbook, or if you want, if you have any other data, you can put it inside that format. I'll click on the project one. Inside the project one, you will be having a BOM folder. If you have a BOM folder, if you created a BOM folder, then go and select the BOM folder. So currently I will choose the document folder. Inside the document, I will be having power supply dot xlxs. Then click on save. So now you can close it and go back and check on the desktop in the power supply one, project one. So we have the documents. Inside the document you can go and see. Now we also have the .bom, that is two things we will have. It is from the OrCAD schematic, and this is which we have opened in Excel and we saved it in Excel also. So this is how we create the minimum, that is primary BOM. So using this particular data, so we are going to do the research and we will collect all the details related to the part. So what are the details related to part we will find? So we will take one example. For example, I will take 1 ohm, or we will take 100 microfarad capacitor. So we need to search from the vendor or the component supplier. I will show you an example. In your company, while you are working, you will get a vendor detail from the company itself. So you directly mail them and they will provide you the component details. Here I will show you online platform where we can get the component supplier. So for example, I will take DC keys. So DC keys, click on the DC key. You have many suppliers. For example, you have element 14, for example. These are also the element 14 is also an online component supplier across the globe, and you will also get components from Mauser Electronics. These are the few of component supplier across the globe, so you can get the component from their website. You can order it. So I will show you it in the DC keys. In the DC keys, if you have a company account, you just log into your company accounts, or if you don't have the company account, you can even search for the components and you can manually add it. So we'll do it manually. So the first thing, we need a 100 microfarad capacitor. I'll go with 100. That is capacitor. You can type 100 microfarad capacitor. Press enter. For microfarad, you can use a small v also. So if you want through hole or aluminum type of capacitor, ceramic type of capacitor, you can choose it. But clients will ask you to choose a particular component. They will give you the part number. According to part number, you can search for the component also. So if it is completely you are the decision maker in BOM, so you can consider the price also, and availability also, and the performance also. These are the three main factors. So using that factors, you are supposed to select the components. For this particular project, most of the components I will choose through hole, and only one or two components I will prefer SMDs, just to show you how does the SMDs sit on the PCB. So I'll click on aluminum electrolyte. So I will look for 100 microfarad capacitance capacitor here. Let us see, will we get the 100 microfarad capacitor in aluminum electrolyte capacitors. So in this section, when I selected the aluminum uh, electrolytic capacitor, so we have the list of 74,475. It may be changing whenever you are searching in the future. So we have so many capacitors here. So whichever capacitor you want, the first thing you need to filter with the capacitance. So you can filter with the capacitance, come down, and we need 100 microfarad. I will choose the 100 microfarad. As soon as you select the 100 microfarad, so it will show you how many components are available. There are more than 5,500 components are available. I'll click on apply on that. So wait for some times, it will load 5,000 components. Yes, now it has got 5,000 components. So these are the capacitors which is only having 100 microfarad. Okay, so voltage level also you can look for voltage level. So we need at least minimum 40. So you can see it is 24 voltage, at least 24 voltage required. More than 24 is also fine. So we got the 25 volt voltage here. Or if you want only 25 or the more than 25, you can choose from the filter section. So I will choose through hole here. I don't want SMD. I will choose through hole. So if you want to look for a mounting type, come towards right side and look for the mounting type of the component property. So go towards right side. If you find the surface mount, and here you can see the mounting type on the last side. So use the scroll button towards right side, and here you can see there are three types. One is chassis mount, surface mount, and through hole. So I will choose through hole. When as soon as you click on through hole, it will show you how many components are available. I'll just click on, there are 4,000 components are available. I'll click on apply. So there are 4,000 plus components, that is through hole capacitors of 100 microfarad. You also remember we applied two filters. You can see here in the search entry. So we have applied a filters, that is one is 100 capacitor, that is 100 microfarad capacitor, that is capacitance we applied, and mounting type we applied. So we are searched for 100 capacitors. So come down, you can see all are through hole components, through hole capacitors, and with 100 microfarad value. So in this, I will choose the component which has EDA or CAD model and datasheet. I want both. So I want the datasheet as well as EDA CAD. Datasheet is for creating the footprint, and the second one is the EDA CAD model, which is 3D model. I will select both and we will cross check how many components are available. So now we got 2000 components. I'll select with the datasheet. So you will get almost same component. 1900 components have datasheet as well as both EDA. And also while you are working in a real-time project, so you also look for a in stock. So don't select anything which is out of stock. Select in stock components, and because whenever you procure this particular order, you should get the actual components. You should not get components are out of stock. So it is very important thing. So if you design for that particular capacitor, for example, if you choose this particular capacitor and you design your footprint and board design, but while procuring the components, if you don't find this, or if this is out of stock, so it is again a difficult task to change all the design. That's why I will choose in stock also. Remember, you should always choose in stock components. Now you can see there are 944 components are in stock. Then click apply. So we had multiple filters here. One thing, we have filtered with the 100 microfarad, that is capacitance value. Second thing, we've only chose the through hole components. And third thing we choose, which is having the data sheet, which is having the EDA, that is 3D model, and which is having in stock. Finally we got 944 in stock. In that you can choose whichever component you want, because all categories are accepted here. So I just click on the first one itself. Otherwise, if you have any particular manufacturer, in the filter box you can go back, and in the first filter option you can see the manufacturer names. According to the manufacturer name also you can choose. So we have already choose the country here, India. That means these components, in stock components, whatever you filtered components, are all available in India. So if your country is different country, you just choose, click on this flag, so you will get the country details. According to your country you can select, and you can then filter the components. Whichever component is available, you can choose that particular components. Okay, so now the next filter is the price. Price is also plays a major role, because whenever you are going for mass production, you need like a lot of components. Like mass production, you need a mass components. For example, if you are creating 1000 components, each 1000 PCBs, each PCB needs two capacitor. That means you need 2000 capacitors to be in the table after manufacturing. So price matters here. For every one component it is 28 rupees. If you purchase 1000 quantity of capacitor, it is per capacitor it is 7.47 rupees. So that's why the price is also matters. The cheap and best also you should look for, or minimum order. If you take it, you will get a less price. If you are taking single components, the price will be 28 rupees. So you make sure how many quantity you required. Price is also plays a major role here. So based on that, you just go and search for the component. So I will choose which is near to 24 voltage. All are more than 20. Yeah, here we have the 30. So which is two side So we'll go with, okay, we will go with the 50 volts. That is enough. First one I will choose, select the first one. I'll click on the first one and we will see how many details we needed to update in our Excel sheet. The first thing here you can see, this is the manufacturer part number. You can see that manufacturer part number here, the same manufacturer part number is displayed here. Most of the clients will provide you the manufacturer part number. You just look, copy that manufacturer part number, put it in a Google and you will get the link. So this is the manufacturer part number we need to update inside your Excel sheet, and this is the supplier part number you need to update inside the Excel sheet. So now we just skip this part. I'll only add the manufacturer part number. So we need the manufacturer name and then manufacturer part number and the description about the component, and the data sheet, which is very essential. Data sheet must have, that particular data sheet must have a dimensions to create the footprint, and here we have the EDA or CAD model. So I'll just right click here, open in a new tab. So inside this, yes, it is the Digi key. Inside this we can see the 3D component. So this is what the 3D model. So if you want to download, you can download that. Okay, fine. So we'll go back into the Digi key, and you can see the price here for one quantity. If you are purchasing 1 2 3 10, up to 9 component if you purchase, so per component it will be 28.31 price, and if you purchase 10 capacitors per unit, it will be 18.73. If you purchase 50 per component or per capacitor, is it 13.77. So if you purchase it for 100, so it will be around 11 rupees. If you purchase for 1000, it is around 8.8 rupees per component. So now if you purchase bulk like 1000 2000, so if you purchase 1 lakh capacitors, so per capacitor you will get it only for 5 rupees. So this way you can just purchase the component whenever you are having mass production. If you are producing 5000 PCBs, you need a 10,000 components. If consider if your PCB needs 2 capacitors per board, so based on that we will procure the components. Okay, so now you know the detail about, now you got to know about the detail about what are the details we need to update inside the BOM. So I will open the Excel sheet and we'll try to update the things. First we will, not in the Excel sheet, I'll just show you in the Excel sheet, and later we need to update those details in the schematic itself. The first thing here we need is the manufacturer name. Second thing we need is manufacturer product number. Third thing we need is vendor name. So vendor name is important because some components you don't get it in the Digi keys, so we will change the vendor or supplier. I will change it to element 14. I will change it to uh, different like Mouser Electronics, or if you have if you know anyone else, you can you can add their name. So here for the training purpose I will provide vendor name is Digi, and then vendor part number is required and it is optional, so I just leave it vendor part number. So you will need at least a description. So we need the description about the component, that is short description is needed. So you will get the component, that is manufacturer name, manufacturer part number, description, and then we need the data sheet. We need the data sheet. We need to collect the data sheet and you download the data sheet. And then we need to go back and check it. So we need, if any category that's capacitor, it comes under capacitor category, no need. And mounting type is very important thing here. What is the mounting type and what is the package? These two are the important things under the attributes. So I will choose these two. One is mounting type and package case. One is mounting type empty and package. So finally we need price. Okay, so these are the details we must required. So whenever you are creating bill of material, so most of the bill of material related details will be provided by the client itself. So you just have to update it to your schematic. So in Excel sheet we updated this, but how to update inside the schematic we will see. We'll go back to schematic. We'll go back to schematic now. So we need to select only the components. You can see that component, right click on the part and edit part. Now inside the edit part, sorry, not in the edit part, sorry, my bad. Right click and select edit properties. Click on the edit properties. So now inside the edit property we have the column called color, designator, graphic, implementation. So similarly we will also have the part references, footprint, and we have the value. So these are the columns which we have already existing columns. So from that column we have only taken 4 details, that is item, that is serial number, quantity, and part reference and value. So we need to update this particular table. So how to update that particular table? So go to DSN file, right click in the DSN, and now go to edit object property. So if you select DSN and right click DSN and edit object property, so it will give you the properties of all the component which is there inside that particular project. If I click here, now you can see, so this color not for one component, it is for all components inside this project. It's color, designator, graphic. Similarly, if you come towards right side, you will find the reference, you will find the part value. So C1, C2, D1, D2, J1, J2, R1, and U1. These are the components which we have inside this particular project. And also we have the PCB footprint. Okay, now we need to add the columns now. So how to add the columns, we will see. So what are the columns required here is, if you go check in Excel sheet, first one is manufacturer name, vendor name, manufacturer part numbers. These are the columns which we require to update here. So I will choose the first column here. This is the, just imagine this is an Excel sheet. The first column is this one. So I will choose this first row, first column, or the first cell. So it is just like a select all option. It is like a select all options. So you just click on it and check. I will just click on it, it is selected all. So now on top of it we just have to click on new property. So this will create one more column inside this, and it will ask you to update the header and inside value. So I will click on new property. So I say this is the vendor name. So as of now I will take all the parts from the DC keys, or maximum part I will take it from the DC key. I will update the part, I'll update the value, that is DC keys. That means, so this particular property means the first name, you can see that name is VN, that is vendor name. So it will create a column, and the column header will be vendor name, and inside that I have written it as DC keys. So it will write everything. The entire column will be written as DC keys. The entire column will be written as DC keys. That means the first component, which is C1, I will collect and I will order the C1 component from the vendor DC key. C2 is also I'm going to vendor. I will add. I will purchase the component from the DC key. So C3 is also sorry, D1 is also I will take it from the DC key. That means, so I will add DC key that will fill the entire column. So click on apply and then click on OK. So now you can see that there is one new column is created. The column name is now, the column header is vendor name, then all the vendor name got updated. So if you want to change, just go to change, just double click on it and change it. That means now the C1, C2, D1, D2, J1, J2, R1, U1, everything is taken from the DC key vendor. So this is how we create a new property or new column inside the capture. So I will create another one. Click on the select all, click on new property. I would say manufacturer name. Manufacturer name can be different for capacitor, different for diode, different for connector, different for registers. That's why I don't use anything. I'll leave it blank so that you can add it later. So I'll click on apply. Now you can see, I'll just close this and I will show you the manufacturer name, the column created as manufacturer name, but inside that nothing is updated. That means we will update it later according to our research. Similarly, we will create a properties called manufacturer product number. So product number will be a different thing. So I'll click on apply. So after that we will create, so we have created the first three, that is manufacturer name, manufacturer product number, vendor name, then description, data sheet we will add. Then it will be a description, and I'll leave it blank, apply, and then data sheet, and then click, and then mounting type, and then click apply. And after that mounting type we have package and price. So the next will be package, and click on apply, and the last one will be the price. So these are the different columns or the properties which were required and we have created. Just come back and check it. This is the scroll right and scroll left button. You can click it and drag it. So I'll come towards the first. We will have the data sheet column, description column, which is created by us, and then we will have manufacturer name. We will also have the manufacturer product number, mounting type, package, and then we also have the price option. So here the price column is also created. So this is how we create the properties to add the schematic BOM. So I'll click on apply. Once you click on apply, make sure you just right click on this particular tab and save this. Right click and save it. So we can close this. So now we have all the properties. So we will update the property by researching the components, and we will update inside the schematic BOM. So now we are going to research the detail about the component and fill it into the BOM part. So we will go to the DC keys and we will search for each and every component. First thing, we have searched for the capacitor, and next we will search for the 0.1 microfarad capacitance. So we'll go back here. I'll just copy this one and put it in the second column. So otherwise we will put the first details of the component. So this is the manufacturer. So you can see here on the right side, where as soon as you bring the mouse pointer on top of this particular row, you can see at the end one small icon to copy it. I'll just click on it. So you can copy the manufacturer name. So I'll make a half screen this here, and in the another half screen I will take the OrCAD BOM. Just right click here, go to the schematic, edit object properties. So inside the property, we'll just reduce this, and okay. So inside the property I have copied a data sheet. The first one is the data sheet of capacitor C1. So I will take the data sheet, right click on the data sheet and copy the link address and put it inside the C1's data sheet. So select Control V. So now the description is required. I will take the description, come towards right side here, and I will find the copy option, that copy here, and bring it inside the description box and paste it. So come towards right side. Now it is asking, the next thing which is asking is manufacturer name, that is MNP, and mounting type. Manufacturer name here is just, this is the manufacturer name. I'll come towards right side, copy this and paste it. Manufacturer product number, here is the manufacturer product number. Come towards the right side and copy this and paste it here. So come down and check inside the attributes. You can check the product attributes. You can check the mounting type, which is through hole. I'll copy this mounting type and put it under the through hole. So come towards right side again, and package, it is asking. You can see the package here. There are two packages. Don't get confused here. This is what the package we need to update. So there is another package here. This is cut tape and tape or the box, which is used for uh, bulk component package. So this is actual components package. So just copy this and put it inside the package. And then we need a PCB footprint, which we will create in near future, and then we will add inside that. Price per unit, you can add it. Initially you can add it per unit, so price details will be sent separate in the separate mail. So here you can add per unit and inform them it is per unit or per one quantity, and according to their requirement we will send entire thing. So we can skip the price here if you don't want. I'll just put it, for example, I'll put it for one quantity, so just paste it here, that is 28.31. So come towards right side, and finally what we need is done. This is the vendor name, this is the part name. So this is what the capacitor 1 is. And now we will look for the 3D package. So if you want to download the 3D package, so come down and select the download format, click here, and I need a step file. Select the step file and then click on delete. So it will ask you to log in sometime, otherwise you can download it. So okay, fine. So now we got this particular component downloaded here. So we will create another folder and put it this. I'll right click this zip file and go to unzip. So here we have the unzipped file. So we will have the step file. So this is C1 step file. I will just type it as C1. I can identify it very quickly. C1.step file. So I'll make a folder called step inside. Otherwise inside the footprint only we can keep it. So I'll just copy this and go back to your project location, which is there inside the desktop. So inside the desktop, inside the footprint, I will keep it, and I will create a folder called a step. Don't get confused. I just type the folder inside the footprint. I'll put the 3D step model, means the 3D model. It is dot step. So we'll understand once we create the footprint. So this is all about the step or 3D component download. So this is fine. Now we will search for the second capacitor, which is 0.1 microfarad. So we will go to the capacitor, just right click here, go to the new. So now we are inside the capacitor, and I'll type 0.1 microfarad capacitor. You can type or search like this, so it will give some capacitor categories. According to the category you can choose. If you want SMT, you can choose SMT. If you want through hole, you can choose through hole also. So for better, I will choose SMT for this particular capacitor. I'll click on that SMT, and also you will learn how to create SMT footprint, and also we will search for the component which is having the EDA model. So first thing we will discuss about, we will filter about the capacitance value. Just check here, because we searched for 0.1 microfarad, I will only get 0.1 microfarad. So, okay, so now we chose SMD, so fine, it is SMD. We want in stock, we want data sheet, we want EDA components, so select EDA also. So that's it. This output is actually, if you see the schematic, or the BOM, so output voltage is not negligible because it is connected at the output side, that is 5 voltage. So we can go for any voltage level which is more than 5 volt, remember that. So I will choose which is in stock, which is in data sheet is available, and EDA model is also available. Apply, click on apply all. The 2423 components will be showing now. So we chose SMT intentionally because we wanted to know how to make the SMT component. So I will take the first component here. So the price is around 8 rupees. Just click on top of this. Okay, so come down the EDA model. So you can see that there is an EDA model, and click on this EDA model. You Okay, so we have this capacitor. You can see the 3D model is updated here, so we can use this particular 3D model and we can update inside the schematic. I'll just click on the select download format. I wanted the step model, click the download button. So we can also download the footprints, but I would not recommend you to download the footprint, but make sure you create footprint so that you can verify it, and while doing assembly and soldering, so you won't face any issues. So we'll go to the second component, which is inside. I will just remove the previous one. So right click here, I'll just unzip. Click on this. This is the step model. I will type, this is C2. For my easy reference, I will type C2, and we will cut this and put it inside the project 1, which is in the desktop. So go to the desktop, project 1, and inside the footprint we created a step model, and this is C2's 3D model, that is 3D step model. So okay, step model is downloaded, and now we will update the details of this particular component. So we need the data sheet. Right click on the data sheet and copy the link address. I'll make it off screen. This one will make it off screen, and go to the schematic. We will update inside the schematic. So second one is data sheet C2, select, paste here. So right click on the data sheet, copy the link address, paste it here, and then we need the description, copy and then paste it here. I come towards right side, and here is manufacturer name. So this is the manufacturer names, and then manufacturer part number. This is the manufacturer part number. Copy this, paste it, come right side, attributes, go to attributes and look for the mounting type, that is surface mount. It is MLCC surface mount. Just paste it here. So now the package, it is 0402 package and 1005 in metric. I will explain you about that metric and where is the package. Here is the package. Metric and imperial, there are two types of units, metric and imperial. Will explain while creating the footprint design. The next one is price. I'll just update the price per unit, go up, and per unit it is 8.33. Update it here. Okay, done. The second component is fine, and we will go to the third component. We will see that third component. Just come right side, and the third component will be D1. So D1, you just look back inside the schematic. The D1 is diode 1N4004. The part number is already given, so inside that you can directly search for the part number, that is 1N4004. Press enter. Now we can get this particular diode, which is through hole. That's fine, we can create a through hole. So I will take anyone out of this. So we'll take the first. So we need to search for the 3D component also. If we have the 3D only, we will go for it. So you can come down and check it. I think we don't find any CAD models here. Okay, we are not having any CAD model for this, so we will search for the diode, and we can change the part number in the data sheet. So we can take the single diode, click on the single diode. Okay, so now we will search for data sheet and EDA. That is what important thing is. And we'll apply this, and later we'll go for through hole. If you find the through hole, that's fine. If you don't find the through hole, we will apply the through holes. Okay, the first one is available. Click on this. So go down and check it out for this. Is the part number is different. We will update in our data sheet, in our schematic. Come down and look for the EDA model. Yes, we have the EDA model. So you can see the 3D model here. Yes, that's fine. So this diode is okay for us. So we can download this into the step model. Just click on download button, open this, right click and extract. Double click on top of it. This is D1. I will just select D1 and I'll put that in the step folder, that is inside this desktop project 1. Go to the footprints. Inside the footprint, inside the step, we will put the D1. So that is enough. So okay, we will go back to the details which we are going to update it. We'll make a half screen and half screen. So go to the data sheet, right click here and you can copy the link address. We should go to the properties. So come back, the data sheet. Third one is the data sheet. Then next one is the description. Select the description and put it here. And then we need the manufacturer manufacturer name and paste it. And finally here we have a manufacturer product number, paste it. Mounting type, we can go to the attributes, that is through hole. So I'll select this, copy and put it under through hole. So come right side, the package, it says DO200204AH is the package. We'll select this here and come right side, the price we will update it per unit price, which is 8.33. Come right side, that's all. So these are the details which is required by the D1. So the next component we will look for is D2, that is an LED. Okay, fine. I will update everything and we'll come back. Okay, now we are filled up with all data related to data sheet. We have updated all the data sheet links and the description of each and every component which we have inside our schematic. And then we also updated the manufacturing name, manufacturer product number, mounting types also updated. Along with that, we also updated the packages. Wherever there is no package is shown inside your data sheet, inside your component details or attributes, just make it as not available, like not available. So then we also updated with the price tag, and then yes, we also had the dizzy key names. So once you finish everything, we can export these details into your Excel sheet. So no need to again add inside the Excel sheet. Otherwise, if you have only few component, you can copy paste it from the schematic. We just have to copy paste the data sheets here. So just copy it and you can paste it into this particular Excel sheet. But I will show you the shortcut key where you will get all the details into the Excel sheet automatically. So we will go to the bill of materials. So we'll go to the Excel sheet. Once you update everything, click on apply and then right click here and save this and then close it. So if you want to come back and see, just select all the components. But here you can see whenever you select the entire screen, sorry, inside the page, so it is also selecting the wires. So just if you only want to select the component, right click here, go to selection filter Inside the selection filter, I'll just make it clear all. I just wanted to select only parts and then click OK. Now select the area. It will be selected only parts. No wires are selected. Now right click on any part, go to edit object, edit properties. Now it will take you to the same location. So otherwise, so as of earlier, whatever option we have used, I'll just make it select all. Earlier we have went on the left side panel, which is in the DSN file. Save the DSN to latest, right click here and then go to edit object properties. It will also bring you to the same page. Okay, so once you are done with this, so we will go to the bill of materials. So go to DSN and then go to the tools and then click on bill of material. So once you click on bill of material, we need to update this particular header as well as string according to the required columns. I'll just copy this inside our Excel sheet. I'll just paste it somewhere here. That's fine. And the second thing is I'm going to copy the string and I'll just paste it just below this. Now we are going to update these things. Sorry, I'll just copy this and we'll paste it inside this. Okay, so I'll just make it bigger in size so that you will be able to understand what we are doing it now. Now currently we are exporting only these 4 tables or 4 columns, because in the first row we have only 4 items. So items, quantity, reference and T part. So now we need to update this with the updated columns. Now you can see we just follow the same thing. See, each and every header has small t and the quantity. Similarly small t and the reference. Similarly small t and the part. So now what we need to do is we just click on this, double click, and I'll also take the / small t, and then the next table I want is manufacturer name, MN. We just have to copy the same name, whatever name you have here, same name you have to copy here. And on the bottom side you can see it should be copied. Copy the same thing and you have to paste it here, and it should be under flower bracket. Make sure it should be under flower bracket. So I hope you understood this part. So we just added one more header and header related data that is inside the string. I'll just copy this entire thing and put it under BOM. So inside this I will put it under BOM, and the second part is also I am just copy it and paste it here. So now I will open in Excel sheet, click on OK. So now we will get another Excel sheet, the new Excel sheet here. I'll just make it full screen. Now you can observe carefully on this side we got, along with the item, quantity, reference part, manufacturer name is also updated, and related to manufacturer name table or the column we have all the manufacturer names are appeared here. So this is for header and this is for string. So we have updated one extra. Now we are getting one extra column inside the Excel sheet. I'll just close this without saving because I will update everything, and then at once we will export. I'll go to / now. The second table here is the manufacturer part number. I'll just copy the same thing and put it here. So small t, don't remember small t, and then paste it. So I'll just copy the same thing, put it inside the string and put it this inside the flower bracket. So now we will get 2 columns, that is manufacturer name as well as manufacturer part. These 2 will be updated inside our Excel sheet. The third one is VN / small t VN. Similarly I'll copy this entire thing and paste it here and put the VN under the flower bracket. So now it will be updating the 3 different columns. Now next one is the description. I'm just doing this in Excel sheet because I don't want to miss any spelling mistakes. If you done any spelling mistake, that particular row or column will not be updated properly. That is the only reason I'm just making it copy paste so that I will not do any spelling mistakes. So copy the same thing and paste it here and put it under the flower bracket. Okay, the description is done. Data sheet also, we will take it, copy backslash small t and then data sheet. So copy the same thing and put it here. Data sheet will be kept inside the flower bracket. So similarly, we need a mounting type. We come towards right side. We'll take the mounting type, double click here, small t, paste it and copy the same thing, put it under the string. So now we'll put this under the flower bracket. Same thing for the package also, copy, double click here, backslash small t, paste it, and we take the copy of this and paste it here, put it under flower bracket and flower bracket. So make sure if you are not understanding, please watch it again and again so that you will get understand once you see this twice or thrice. It is not that difficult, it is very easy task. Just make sure you should follow the procedure properly to update the BOM link. So now we got all the rows and columns here. The manufacturer, will just zoom it and show you. This is all about manufacturer name, manufacturer part number, vendor name, description, data sheet, mounting type, package and price. The same thing we have inside here. Manufacturer name, product number, vendor name, description, data sheet, mounting type, package and price. Okay, just I'll copy the first thing on top, double click here, select entire thing and copy this, and we will paste that give me a minute, I'll just minimize this and we'll go to the DSN file, go to tools and bill of materials. Now I'll paste that in header, and the second one I will put it the string which we have prepared here. I'll copy this entire thing and put it under string, just paste it. So now I'll open in Excel and then I'll click on OK. So it will ask you to open the Excel sheet. I'll just click on open the new Excel sheet. Yes, the every information is exported inside the Excel sheet. Now this Excel sheet I am going to update inside the BOM. So I'll just remove unwanted things, unwanted, and these are all not required. If any reviews if you have, you can put it, so otherwise just leave it. So now I just click on the item. I'll just increase the size to 12 or the 14, and the item, sorry, in the commodities I will just make it 12, and then item I'll make it a little bit bigger and bold and color. So I'll prepare a table, select everything, click on this, put all borders, and now you can increase the quantity. Double click on this, manufacturer name, product number, vendor name, descriptions, and then mounting type, package, and then finally we have the price. So if I double click on datasheet, it is very big in size, so that's fine. So this is all about the BOM, which we have exported it from the schematic. We have updated initially in the schematic, and then we have exported it to the Excel sheet. Now it has got primary, which we had 4 items. One is column, that is item column, quantity column, reference column, part column, and then we manually updated manufacturer name, manufacturer part number, vendor name, description, data sheet, mounting type, package and price. Manually we updated inside the schematic BOM, and then we exported into the Excel sheet. So this is the entire procedure. So then next what you need to do is you need to send this particular BOM to the client for the further approval. If they say everything is fine, you can go for footprint preparation. If anything changes required or updates required, so what we need to do is we just have to, according to the review, we just update the BOM and again we send it for the review. Once everything is fine, if this Excel sheet or if this BOM is approved, if this BOM is approved, then we will move on, and create the footprint preparation. So then we will create footprints. So this is the procedure till BOM. Now we will start creating the footprints using the data sheet which we have already collected. We have just collected the link of the data sheet. We will collect the data sheet and put it under datasheet folder, and then we will start creating the footprints. Footprints, the procedure will be 2D as well as and 3D, both we are going to create it. So we'll create a 2D layout and then we will attach the step models, that is 3D models, into your schematic. And whenever we create a board design, so parallelly you will see the 3D board in a board design. Okay, now we are going to collect the data sheet which we have already done the BOM, and we have the link inside that each and every particular component. Just right click on this J1 and then go to edit properties. Go to edit properties. Inside the property you can see the datasheet link. So we'll take this particular link and we will collect the datasheet into our datasheet folder. This is one way. Just I'll copy, or you can double click and copy the link, but that is datasheet link, and you can go to the favorite browser and put it inside the address bar. So the datasheet it will directly open, and if you want you can download this particular datasheet. So this is for a 2-pin connector. We will see how to create that footprint and everything. So now we will collect all the data sheets. So we have already the Excel sheet which we have prepared inside the project. I'll open the project one, and there is a data sheet. So inside the data sheet we will collect all the required data sheets. So to do that, we will go to the documents. Inside the document we had the BOM Excel sheet. I will open the BOM Excel sheet, that is bill of material. So in this bill of material we have the data sheet. So what we need to do is just double click inside and then press enter. So the link will be generated because that is the HTTP link. So once we enter inside and press enter, it turns to the hyperlink. So now we can directly click from here and go to the browser, and the PDF will be opening inside the browser. So what I'm going to do is just bring on top of it, just right click, or you won't direct click, you can click on the direct. So the first one is, that is capacitor. So it will ask you to open in the browser, click OK. So you come back to the browser and you can see inside the browser the data sheet is opening now. So what I'm going to do is right click here, and otherwise you can click on the download options. So I can do the right click. So if you can't download after right clicking, just click on the download button. So this particular file will ask you to save this, and I'll go to the desktop and go to the project one. Inside the datasheet, I would say that the name is different. So this is for capacitor one. I'll prefer C1. So it is about your understanding. Whatever name you are giving, give according to your understanding. So this is one, the data sheet, and then we'll go for the second one. Click on the second link, which is C2. You come to our right side, the reference, you can see the reference C2, and I'll click on the second link and then click OK. So go to the browser, so it will open automatically. So this is the second data sheet. So right click, check it out if you can download or save this PDF. Otherwise just click on the download button. Here you can see the download button. Download this file. So we'll go to the desktop, project one, inside the datasheet. This is for C2. I will just type this as C2 and then press save. So the two data sheets which we have created. Now we will go back to Excel sheet, and the third one we will make it. So click on the third one is the on semi D1, that is diode. Just click on the diode, click OK now, and the PDF is opening now. So this is the diode which we are going to create the footprint. So right click if you can, otherwise click on the download button. So the download button will open. Go to the desktop, go to the data sheets. So this is D1. I'll just type the name as D1. I'm just making it simple, so people uses the part number to identify the PDF. Our part name they will give you. I'm giving the reference name. So next one we will go, that is the D2, that is LED. So click on this LED link, click OK. So now this is the LED which we are looking for. I'll download this LED. Go to the desktop, go to the project location inside the data sheet. So this is D2, and people use LED also. I'll write D2. So this is easy for my reference. So the next one is the 24 VDC, that is 2-pin connector. Both are same, so I'll just save only one. So this is the male header pin. I'll explain the male header pin. So for 2-pin, how we have to do, I will explain. Click on the download, go to the datasheet location. This is J1 and J2. I will write it as J1, J2, then enter. Okay, so two components done, J1 and J2. Both, if you observe here, the both links are same. So I just saved it only once. So the next one is we have 1K register. Click on it, click OK. I'll close these data sheets. Yeah, this register is fine. We'll download this particular data sheet. Go to the desktop, go to the data sheet, and this is for R1. I'll type R1. The last one is U1, that is regulator. Click on the regulator, click OK. So this is the regulator which we are creating. Right click or download this. Okay, so now we have the data sheets, that is U1 data sheet. Enter. That's all. We have collected all the data sheets inside the data sheet folder with the help of BOM, which we have already created. So we will go to the data sheet one by one and we will understand the data sheets. We'll go back inside the data sheet. Now we have all the data sheet required for this particular project. So you observe here, first thing we did the schematic. Inside the schematic we have all the schematic related files and also the DRC files, BOM files also. And then in symbol we have created the component symbol, that is power supply dot library. So inside that library we have all the symbols which we have created. And then we have the documents required for this particular project, that is we have the circuit photo as well as we have the bill of material, BOM Excel sheet. And then we have the data sheets, or the data sheet we collected inside the data sheets. And only two things we left is, one is footprint. So we will create the footprint. Inside the footprint we already have the 3D step mappings, and then we will create the 2D footprints. So on board design we will create once we done with the footprint creation. So now we will create the footprints for this particular project components. So footprint, that means we have to create a dimensions. Using the dimensions we need to create the solder mask on top of the PCB board. So footprint, I will take, there are two types of footprint. One is surface mount and then second one is through hole. So we also call it as So SMT, that is surface mount technology, and PTH, that is plated through hole technology. So SMT usually will sit on top of the board, that is, so it will not put any kind of holes, and it will be soldered on top of the PCB, and it is connected to only on the one side of the PCB. Through hole, it will put the hole, and your lead will go through the all the layers, and then either it is soldered on top or it is soldered on bottom. So these are the two difference between SMT component and through hole component. So we will open the data sheet. So I will first show you how to create SMT datasheet, and then we will see how to create PTH datasheet. After knowing this, we will create each and every component using the actual datasheet. Okay, so I will take a register, for example, an SMT register. For example, this is an SMT register. I'll show you the pic. SMT resistor footprint. Inside the image, you can see. Now this is what the SMT register footprint looks like. So here you can observe there is a component. This white color is the component, white and black color is the component, actual component, which is placed on top of the PCB, and outside you can see the golden color. This is the solder mask, solder pad and solder mask, and then outside white color you can see this is a silk screen top. So we will discuss about that in detail. So I'll take the pictorial representation, and then I will explain you about the footprint. So if I take the cross section, so if this is your PCB top and bottom, I'll just make it solid. So now I will have the component on top of it. So I will have the component, it's a cross section. Now the component has the pin on the bottom, that is pin 1 and then pin 2. If you want to keep this particular component on top of the PCB, we must have the solder mask, solder pad first. So solder pad is not equal to the actual pad, it is quite extra, that is used for soldering purpose. So the for other pin also we need to have the extra solder pad so that we can solder on top of it. Along with that, we will also have the paste mask. We will discuss what is paste mask. For SMT components, we need a paste mask to do the soldering of the SMT component. This is also called as solder paste. And then to avoid the coloring on top of the solder pad, we put the solder mask. So now we say this is the red color, you see this is a solder pad, and the yellow color we see that is the solder paste. We can say solder paste is applied to SMT components only, say solder paste. So whenever you will not able to solder with the solder bit, so you can put the solder paste and we pass the heat air or hot air, and then this automatically will solder it to the component. And these are the actual pin. This is the actual pin on the component, it is component actual pin. So we need to solder that particular pin. So to create the footprint, we have the two parts. One is first you need to create the pads, pad creation you need to do, and the second thing you need to do is the PCB editor, and that is also called as package creation. That is package creation. There are two options you have, one is pad creation, another one is package creation. So we will discuss in detail. So we will take the cross section of the PCB through the PCB way. So we have seen the component and then PC board, and now we will see on the PCB we will draw the solder pad. And then what we need to do is, so we go for a coloring on the PCB, that is epoxy we are putting on top of the PCB. If you put the epoxy on top of the PCB, your solder pad will be inside the epoxy and you will not be able to solder your components. So to avoid that, what we need to do is we need to put the protector, that is also called as mask. So we'll put the mask, extra mask on top of the solder pad. On top of the solder pad we'll put the extra mask to avoid coloring on top or putting epoxy on top of the solder pad. Now if you want to put the color, you can put the color till here and then till here, and you can put the color on this area. So now what happens if I remove the mask? For example, now I will remove the mask after putting the color. So color on PC will be this way, and you don't find the color on top of the solder pad. So this is what the epoxy or solder mask will protect your solder pads from the epoxy. So now you will be able to do the proper component placement on top of it, and this is the actual pad, and you will also be having a paste mask. So here also we will be having the paste mask. So now whenever we go for the hot air, if you pass the hot air on top of these solder pads, the paste will be melting and it is doing the soldering onto your components. So this is how we protect. So that's why what we need is, there are three different things we need. So first thing is, so we need to create the solder pad according to the data sheet, and then we need to create the solder paste for SMT components we need, and then solder mask is required to protect your solder pad from the epoxy. So these are the three files we need to create according to the rules. According to the IPC rules we will create it. And then this is all about the pad stack creation. So whenever you are creating the pad stack, so you just have to consider these things. And whenever you are creating the footprint, or package, we will be having assembly top, seal screen top, and some other restrictions. So we will discuss that in detail. So this is in through hole, sorry, it is in SMT. In through hole we will explain it. For example, if this is your PCB, we will put the hole on wherever you want to add the leads. So I will put the hole here. So here also we will put the hole. So top to bottom we will put the hole, and then I will show you the example of a resistor. So I'll take the component, and the component lead will come till here, and it will bend and it will get inside the drill. So it will come till here and it will get inside the drill. So now using that drill you will put the lead, and then we need the connections and for soldering purpose, so we will use solder pad. On top layer also we will use the solder pad, on bottom layer also we will use the solder pad. Similarly here also on top and bottom we will use the solder pads. So paste mask is not required here, we are not doing any solder paste here, so we just skip this paste mask. Once you solder, either you can solder it on top as well as bottom. So I'll just, if you solder it on bottom, so your component will be fixed properly, and this solder pad will also give, it is used for two applications. First one is the electrical connection, and the second one, it will give a soldering option. So that means it will hold the components. So the two applications for solder pad. We also put the solder mask here to avoid the color epoxy on top of the solder pad. We will put the solder mask to avoid the coloring on top of it. So this is all about through hole. So we will discuss in detail using the data sheet. So first I would like to take the capacitors 2. We will see the capacitor 2 data sheet, which is SMT data sheet. And so I don't find any solder pad related details here. So we can see this, the component package, It's a 100 microfarad package, and we will look for the solder pad details. So I'll just copy this part number, copy this particular part number, and you can go to the dizzy keys where we downloaded this particular part. We'll go to the dizzy keys. Otherwise, you directly paste inside this and you will see the dizzy key part number. So click on top of this link where it takes to the dizzy key. So come down, and here in the documents and media, so you will find the EDA models, or also if you find the CAD models also, that is fine. So we will click on top of this EDA model, and now we can see the footprint. So this is what the footprint looks like. So this is the footprint, this is a 3D. So come down, and here you can see this is the footprint, and this component will come and sit on top of this particular footprint. So this will be printed on the PCB, the component will come and sit on top of this one. So if you want, you can download the footprints, or if you want, you can create on your own. So I will show you how to create on our own. Now here you can observe the red color is outline of the component. So this is the actual component area, that is also called as assembly, and this small portion is of actual pad of the component, and the extended portion is the solder area. So that is called solder pad. So okay, fine, we will discuss about that. So we will see the package. It is 0402 package. So the package you see here, it is the 0402 package. So if you want 0402 package, so we can go with, I'll give you the link in the description about this. We will look for a 0402 package. It is for resistor and capacitor, both same. So they have mentioned here of 1005 metric. So 1005 metric or 0402 is the imperial code as well as metric code. So here we can get the component. There are two tables here. The first table will explain you about the component area, that is assembly, component length, component width, and as well as component height. So come down, and here you can see the solder pad or LAN pattern details, where so it is the actual solder pad or the required solder pad of 0402 or 1005 in metric. So here we will be having length and width. So length and width of the solder pad, and you can see the dotted line here. This is the component as our assembly length and width component area. So we will discuss about the footprint creation in detail. Okay, so now we are going to discuss in detail about footprint creation. Footprint creation, we will have two methods. One is we will create the solder pads, that is using the pad stack, and the next one is we will create the package, that is PSM, which is using the PCB editor. So now I have taken the resistor for an example. I will show you both. One is creating completely manually, and then second one is how to download it from the websites. So both we will see. I'll create a few components manually, and I will download few components from the websites. So I have taken one SMT, that is just for an example I have taken to understand how the SMDs will be created, and on the downside we have the through hole component also. So this data sheet, the link I'll share you in the description. So we will discuss both about SMT, how to create and what are the rules according to IPC, and through hole, how to create and what are the rules according to the IPC, we will see. So you can see this is the SMT register or the component which will sit on the PCB. So if I see it from the top view, inside the on the PCB, if you consider this as the PCB, on top you just find the rectangular body, that is this component has a rectangular shape or geometry, we can say. So I can see the rectangular on top of it, and on the right side we will find some solder pads. On the bottom side, sorry, on the bottom side we will find another one solder pad. There are two solder pads for soldering purpose. So similarly, so we have two codes here. One is an imperial code, and then second one is the metric code. The imperial code and metric code here represents the actual area of the component in inches as well as in metric. For example, if you say it is an imperial, if you got the imperial code, that means all the data dimensions are in inches. So if you get the data sheet, everything is in metric. If they say it is in metric, that means all the units are in millimeters. So remember this. So this, if you get 0201, 0402 or 0603, this code, if you get it, that means the length of the component and the width of the component is in inches. Okay, so similarly, if you get the metric code like 0603 1005 and up to 6332, if you get in metrics, that means the length and width of the component is in millimeters. So we'll see how to decode this imperial code and metric code. So I will take the first one, that is the last one will take 2512 and 6332. So we'll go to the white screen. So we have taken, that is an imperial code. First I'm going to explain you about imperial. That does means all the dimensions in units are in inches. All the dimension units are in inches. So in that, the first one is the 2512. So 2512 is an imperial code, so they will write it in like imperial. So this is an imperial code. So how to know the length and width of the assembly? So this would be the length, this is L, and this is the width of the component. So what will be the length and what will be the width, we will see. So in an imperial units, so this is the width, this is length. You can also say this is width and this is length of the component, or height also you can say in 2D. Okay, so what we need to do is we need to separate two things, that is 25 we will make it separate, and we make it 12 is also separate. So and divide the 25 and divide the 12 by 100. If I divide it by 100, 25 divided by 100 and 12 divided by 100. So here the first half you will get, that is 0.25, and this in the second half you will get it 0.12. Okay, so this is length of the component and this will be the width of the component in inches. So both are in inches. So this is length and this will be the width of the component, that is the actual area of the component. Here the length is 0.25 inches and width is 0.12 inches. So now we understood how to we decode the imperial code. If it is 2512, it is an imperial code. So I will take first half, that is 2 digits and another 2 digits divided separately by 100 and 100. The first half will get 0.25 inches, that is length of the component, and 0.12 will be the width of the component. So this is how we decode imperial code. So now come back and see. So I have taken 2512, that is an imperial code. So we will see the length of the component, that is L. So this is the length of the component, that is L, and the L here in inches, if you see, if I come down, so this says 0.25 inches length. So the now the length is 0.25 inches. And what about the width? Width will be, so like here we have the width table, and we also have the inches table. For 2512, so you can see that 0.12 will be the width of the component. So 0.12 will be the width of the component. So this way we can decode the component geometry or component area, what will be the length and what will be the width, using the imperial code. Similarly, you can check with I will check with 1812. So what we did is 18 will make it separate, 18 and 12 will make it separate. So divide 18 by 100. So divide here 18 by 100, we will get is 0.18, and 12 is 0.12. Now you can observe the first half is the length of the component, this is width of the component. So now you can see 0.8, the length is 0.12 and width is 0.18. This is quite reverse here. So you can rotate the component anyway. You can rotate the component this way also. So the length and width is similar to that. So we will see that 1206. So 12, the first half we will divide it by 100, we'll get 0.12 the length, and 0.6, if I divide 0.6 by 100, I will get 0.06, that is width of the component. You can cross check anyone, like we will do that 0.402. That means 0.04 is the length of the component and 0.02 is the width of the component. So this is how we decode the imperial code. And now we will decode the metric code. So metric code we will take, metric means every information is in millimeters. So I will take the last one, that is 6332. So we will go with white screen. So this will be 6332. So 6332, they said it is in metric code. So we will separate again, 63 we will make it separate and 32 we will make it separate. So here we'll take 63 and this is 32. So now no need to divide it by 100, you just have to divide it by 10 just to decode this particular code. So if you divide it by 10, the first half it will become the 6.3, that is 6.3 in millimeters length, and this is 3.2 in millimeters in width. So now what we need to get, what we got it here is the length is 6.3 in millimeters and width is 3.2 in millimeters. So these are the things we have got decoded the metric code. The length of the component here is 6.3 and width of the component is 3.2. that is what 6332 meaning. So metric, you now know about how to decode imperial code as well as metric code. So this defines the actual area of the component, the length and width of the components. Now you can cross check with the different, that is 5025 if I take. So we'll just make it 50 separately, just divided by 10 and 5025. So 25 you divide it separately, here you will get 5 and here you'll get 2.5. So the 5 is the length which is in millimeter, okay, and 2.5 will be the width which is in millimeter. So this is all about 5025. The length is 5.0, the width is 2.5. So this is about metric code, decoding the metric code. So now you are familiar with code, imperial code and metric code, and how to decode and get the component area out of it. So this is the body area, we also call this is the detail about your assembly. So now we will go with the soldering details. So come down, so there is another table where we will get the solder or land pattern details. So we will take the solder and land pattern details, which is quite different. So we are going to create 6332, or we can create 1005. Anyone you can create. For example, I will take 1005. So here the solder pad it is given, that is length is A and width is B. So this is the solder pad area which will be printed on the PCB and which is masked just to avoid the coloring on top of it. Similarly, we will create only one and we'll take the copy of it. So this is the solder pad and paste mask, and the next we will be having solder mask. So the length I will create here, that is 0402 or 1005. The length is 0.6 and width is 0.5. As I told you earlier, so if this is the component, and we will be having the solder pad quite different, like some extra space we will be having. So this is your footprint. The component is different and solder pad is different. So I will just name this as an assembly. This is an assembly top or component size, and this is the solder pad. So this is the solder pad. We have minimum things here: component area as well as solder pad. So first we will take the solder pad. So there are three things we need to design. So we know the length and width of the solder pad, so we will just note it down that solder pad length, that is L. Solder pad length, that is L, is equal to, and then solder pad width, that is W, is equal to, we need to get these details for 1004 package or 0402 package. So 0402 in imperial and 1004 in metric. So this way we need to collect the detail about the solder pad. So what is solder pad? Solder pad is the area where your component is getting soldered, and this particular solder pad we need to mask it. So once you get the solder pad details, we will also collect the paste mask, also we can call it as, or you can also call it as solder paste length and our solder paste mask width, both we need. So what about solder paste, and what about paste length and width? And also after that we'll calculate solder mask length and then solder mask width. So we need to calculate these things according to the IPC standard. We will see how to calculate these things. So I'll open the notepad, and inside the notepad we will discuss about these things. Okay, so which one we are creating? We are creating, that is 0402, that is an imperial code, or we are creating 1005 in metric. So come down, and we need to get the solder pad from the data sheet. So the formula, no need to have any formula because we have directly the solder pad. You will get it from the solder data sheet. And then we need the solder paste and paste mask, both are same. So solder paste is equal to, it is equal to the solder pad. So no need to calculate here. Whatever the solder pad you have created, the same thing you just put it to the solder paste also. The solder mask is quite different. The solder mask is equal to, it should be greater than the solder pad. So solder pad and then plus solder pad plus we put 5 mils, 6 mils according to the requirement, client requirement. We put it for this, for training purpose we will keep it 6 mils. So we'll discuss about what is mils. So 1 mil is equal to 0.0254 mm. So the 1 mil is 0.0254 mm. Similarly, 2 mils is equal to 0.0508 in mm. So similarly, if it is 4 mils, example 4 mils, it is 0.1018 or 16 mm, and 5 mils will be 0.1270 mm. So this way you can go for 10 mils, 10 mils is equal to 0.254 mm, 254 mm, and so approximately 40 mils is equal to 1 mm. It is 39 plus for 39 point something is equal to 1 mm. So approximately we'll take 40 mils as 1 mm. So what about 6 mils now? So you just make 6 into 0.0254, that is 0.1524 mm. So you have to add 0.1524 mm to the solder pad. So then you will get the solder mask. So this is all about a formula about how to calculate solder paste and solder mask. So remember this conversion between the mils and millimeter, which is very important. So every step you have to do the same thing. You have to calculate from mils to millimeter. So why we need to calculate always from mils to millimeter is all the standards are will be in mils, and sorry, yeah, rules and standards will be in mils, and all the data sheet dimensions will be in either inches and millimeters. So if you should have a knowledge about how to convert inches to mils if you are working in inches, or mm to mils, or vice versa, mils to mm or mils to inches. So make sure at least you should know what is mils to mm. That is 1 mil is equal to 0.0254 mm. So if you want to calculate this any mils, for example if you want 2 mil, you just 2 into 0.0254 you make it, you will get the 2 mils. If you want 7 mils, 0.0254 into 7 you can do it, and then you will get the millimeter options. Okay, so now we will calculate the solder pad which we have in the data sheet. The solder pad length of the 0402 will be 0.6 in mm. So I'll keep it 0.6 mm, that is length. We'll take the width also, that is 0.5. So it's 0.5 mm. So you can cross check here. So the 0402 pad length is in millimeters, it is 0.6. Pad width in millimeter, it is 0.5. So 0.5 into 0.6. So this is 0.5 and this is 0.6. So this is about the solder pad. So solder paste, as I told you, it should be same. This both are same. Now the solder mask. The solder mask is solder pad plus 6 mils. So 6 mils in mm, it will be 0.1524 mm. So 6 mils. This is in mils. It is in millimeters. Okay, so we will add for solder mask. So the length here is 0.6 plus 0.1524, so it will be 0.7524. I'll just keep it as 0.7524. This is in length. What about width also we need to add. For width also we need to add 6 mils. So here the width is 0.5, so we will add 0.1524 and then output will be 0.6524. So this is all about solder mask length and solder mask width. If the solder pad is 0.6 and 0.5, solder mask is quite bigger than this, that is 0.7 and 0.6. So 6 mils extra we are putting. This is how your solder mask looks like. That means it will cover the entire pad, and if you do any coloring on top of the PCB, so that your pad will be protected by the mask and it will avoid coloring on top of the solder pad. And later we will remove the solder mask. If I remove the solder mask, I will get only the pad, so where the coloring is not happened, the epoxy is not covered on top of it. So your solder pad will be open and you can do soldering and any connections you can take it. Testing also you can do it. So this is the advantage for putting the solder mask. For example, so if you have a wall, so if you want to paint the wall, but there is something on the wall which you don't want to paint. For example, there is a window not the window. So you have some paintings, very important paintings, which is already there on the wall, and if you don't want to paint again on top of it, so we have some different art related paintings you have here. So you don't want to spoil that painting. So to do that, what you need to do is you first have to mask that particular area, and then an entire wall you just color it, but that particular mask will protect that painting. Once you remove the mask, the entire wall is painted, but the particular area will not be painted, and your previous painting will be in safe. So the same way, so put we don't want to put color on top of the solder pads. Solder pads must be open for electrical connection, testing, and for soldering purpose. So this is the use of solder mask. So I hope you understood about why we are putting solder pad, why we are putting solder paste and solder mask. So now the calculation wise is okay. So we will create the solder pad now. So to create the solder pad, we will open pad stack editor. So go to start and click on pad stack editor. I'll click on the pad stack editor, open the pad stack editor, and now we will use the footprint folder which we have created while creating the fresh project. So we have the footprint project. Inside the footprint project, we will add all the pads related details. So we'll go to the pad stack editor. We open the pad stack editor. So now we'll go to the file option here. Inside the pad stack, we will go to the file and create the fresh new footprint or pad stack. Go to file, new, and it will ask you the small pop-up where you need to select the directory where you want to save, and then you can give the pad name. So I'll click on the browse button here and then go to the desktop project 1. Inside the project 1, we have the footprint folder. Double click on the footprint and give the name here. So here you have it will ask you to give the name. So what I'm going to do is, so this is 1004. I'll give the 1004 name here. So there is a naming standard is also available. I will explain you while creating the through hole components, and then click OK. So this is an SMT component. We'll choose the pad stack usage as SMD pin, and then click OK. So now once you click, now go on the top, and in the header you can see the name of the pad and the location where you are saving this. Please confirm that before going to design any pad stack. So once you are done with, immediately come down and choose in which units you want. So here I want this in millimeters, so I will click on, here it is in the bottom, I'll click on the units and choose the millimeter and say OK. So click yes here, and the accuracy you can see decimal places you keep it 4 always, because so after decimal we need to get 4 digits, because 1 mil is equal to 0.0254, because after 0 after dot you will get 4 units. So that's why we'll keep the decimal places 4 in millimeters. So this is all about the first initial setup. To create the pad stack, go to file, new, and then give the name and the location, and as soon as you select the location, come down, adjust the unit to millimeters. Now, so here in the first section we have the pad stack, what type of pad you are creating. In the second section, what is the shape of the pad. In the first section I will choose it is an SMD pin, so I will choose SMD. So you will have others like through pin, via, blind via, braid via, micro via, slot, that is a rectangular slot, mechanical. There are many types of package we have. So I am creating the solder pad. I will select SMD pin. Now what type of the solder pad you are using, that is geometry, whether you are creating circular geometry or you are creating square or rectangle. So here we are creating SMT, that is the pad stack, and rectangular pad I am choosing, that is the geometry of the pad. So it looks like this. the rectangular pad SMD, and this is the shape is rectangular. So now we come to see, we don't have any drills here, so drill will be kept none on the second tab. Here you find the second tabs. First tab is start, where we select the design, whether it is SMD or through hole, and the geometry, whether it is circle or rectangle or any other like square. And the second one is drill. We are not putting any kind of drill here, so keep the whole type as none. Once you keep it none, the secondary drill symbol, drill offset will be disabled, so we no need to give anything and directly go back to design layers. So click on the design layers. So now we have the begin layer. So while creating SMT pins, we have only the two layers are visible. One is top, which is also called as begin layer, and second one is bottom, so we also call it as end layer. So by default, you prepare all the footprints on the top layer only, so that is the best practice. You are doing it while creating the footprints. So now I will select the begin layer. So and end layer we have, I will select the begin layer. What is a regular pad? I have already selected it as a rectangular here. So if you click here, so I'll get the rectangular. Now come down in the rectangular, so it will ask you what is the width of the component and height of the, sorry, not the component, what is the width of the solder pad and height of the solder pad. I will mention here. So the width here is, so you can see in the data sheet, the width is 0.5 and 0.6 will be the length into width, and here I'll give the width is 0.5 and height is 0.6. So now you can see I have given 0.5 and 0.6. So 0.5 will be the width and 0.6 will be the height. So I can see here 0.5 and 0.6. This is the solder pad, that is SMT solder pad. So if you come back to if you come back to offset here, so both offset we kept it 0. Just show it here. Offset here X is 0, offset Y is 0. So that means it defines the origin of the solder pad. Come right side and you can see the origin here. So this is the origin. So if you change the X and Y axis, the origin will be shifting. For example, I'll keep X axis as 1 and check the origin is shifting towards 1. I don't find the origin here, so I'll just make it 0.2 and check it. Now the origin is shifted towards left side. That means origin is not shifted, your pad is shifted towards right side, so that looks like origin is shifted left side. So I'll bring back, I'll make it 0.1 and you can see the pad is shifted to 1 mm towards right side. So I'll just make it 0 and the pad is on the origin. So even in the y-axis also, if I put 0.1, the pad will shift to up. That means you can see the origin somewhere here. So you can like this. So the pad is shifted up, that is 0.1 on the y-axis. So make sure both are 0. That is good. That is a very good practice. The solder pad is done. Now we will go to the mask layers. The regular pad will keep the solder pad design layers. In the mask layer, we'll put the two different masks. The one mask is solder mask and the second mask is paste mask. The two things we will, paste mask you already know the formula, the paste mask is equal to the solder pad. So we'll keep the same inside the paste mask top. For solder mask, I will keep the extra 6 mils, we will add it to length and width, which we have already calculated. So come to the solder paste or paste mask first. Select on it, it is a rectangular, width is 0.5 and height is 0.6. And now this is the solder paste, it is just same equal to the solder pad. Come to solder mask top, we have done the paste mask top, we will add the solder mask top. Click on the solder mask top. So we have already calculated solder mask, that is 0.7524 is the length, that is height, and the next one is the width is 0.6524, we'll put it in the width. Okay, so now we have got some extra, that is 6 mils extra. That means if this is your pad, so we are protecting that pad using the solder mask. So once you are done with your coloring, if you remove the mask, your solder pad will be open to the soldering as well as testing. So this is all about how to create the solder pad. I'll just go to file now and click on the save. So now in the bottom right side corner you find the footprint that 1004 pad is saved. So you should get this, otherwise your pad is not saved. So I'll go back and check. We'll go back to the footprint folder. Inside the footprint folder, yes, we got 1004 pad. So the pad stack is created, and next we will discuss about footprint preparation. Okay, so now we will discuss about footprint preparation. So we will see the steps involved in the footprint preparations. So we'll open the PCB editor to create the footprint. We'll go to the PCB editor, select the Allegro PCB Designer, and then click on OK. Okay, fine. So we will understand the procedure or the steps behind the footprint creation. The first thing, we have created the pads. So we have created the date creation of pad has done already. It is solder pad using the pad stack editor. And the next thing is we need to do the pads placement according to your data sheet. So how where the pads will sit. For example, here in the resistor or capacitor you got two pads. The passive pads are plus and minus pads. That solder pad which we have already created. So we need to do the pad placement. So we must know the distance between the two pads. For example, what is the air gap, what is the pitch, and what is the lead span. So these are the things we must know before placing your component pad or pad placement. So once you finish with the pad placement, and then we will go for assembly top creation, where assembly means it shows the actual area of the component. We need to draw the actual area of the component, and then we will draw the silk screen top. So before that silk screen, we will draw the place bound top. So using this particular place bound top, we will get the one boundary for the component, and also we can assign the height of the component. Next we will assign the silk screen. Silk screen is an ink print on the PCB, so we can draw the outline for the component. So that means that is that particular area, that particular drawing shows you what type of component it is, and it is printed on top of the PCB, which is ink print. And the next we will be having the DFA bound top. So DFA bound top is another rule which we need to apply for design for assembly. DFA refers to design for assembly. That means whatever the design we do here, the assembler has to for assembler, this design must be good for proper assembly, proper testability, and proper desoldering and desoldering. So we need to follow that rules, so that assembler will not face any kind of issues while physically is adding the components, soldering it and desoldering it, or while testing also. So this all comes under the footprint preparations. We will see one by one, and we will create the entire footprint. So in the first step, we have already done the creation of the pad. Second step will go to the pad stack placement. So to do that, so we'll understand the data sheet. We'll go back to the data sheet. So now here you can see, so we got the C, that is the air gap. That means from the inside of the two pad, edge to edge, the area between the two pad from inside edge to edge, that is called air gap. So we'll understand the air gap using cross section of the PCB. For example, if this is your PCB top and bottom layer, and then we will be having a solder pad on top of the board. This is one pad, solder pad of the resistor. This is another solder pad of the resistor, and then we can go for component placement on top of it. So once you place the component on top of it, so we will be having component as well as paste mask on top of the solder pad. So now you can see the gap between the two pins. So this is the gap between the two pins. This particular area is called an air gap. So similarly here in the data sheet they have shown it. This is the air gap. So here the air gap is from this point to this point. So this is the air gap from inner side of the solder pad to another inner side of the solder pad. So if you see from the outer side, for example, outer side of the solder pad to outer side of the solder pad, this is called lead span. So this is called lead span from outer side to outer side. So this particular area is called lead span. So these are important while calculating some distances. We say it as lead span. And from the center of the first pin to the center of the second pin, from the center of the first pin to the center of the second pin. So this is called pitch. So this is the pitch. So we always need to calculate the pitch because our solder pad origin is the center of the pad. So origin falls in center of the pad, so we need to calculate always the pitch. So I hope you understand about the pitch. So we will calculate the pitch between the two pad while placing the pads. So the mouse pointer will directly jump to the or it will hover to the center of the solder pad. So accordingly we will place the component. So once you place the component, so you just cross check what is the distance between center to center and what will be the air gap. If you find both right, that means your pad positioning is right. So we will discuss about that is 0402 or 1005. So we know that B. So if you want to calculate the center, it's a half, and here also it is the half of the pad. Okay, so now here it is B by 2. This is B divided by 2, half of the pad, and the other side also it is B divided by 2. So that means here this is the B by 2 plus air gap, that is C, and another B by 2. So the pitch formula here will be, the pitch, P refers to pitch. Pitch is equal to, the first thing is B divided with 2 on the left side and then plus C. C is the air gap and another plus another B by 2. Another B divided by 2. So okay, so now we have a B, that is B divided by 2. So we have the B here is the pad width. The B is pad width, which is 0.5. So 0.5 by 2. So 0.5 by 2 will be 0.25 plus here the C is 0.5. We can see the C, that is the gap, that is air gap. For 1005 it will be 0.5. So it is the 0.5 plus another B by 2 is another 0.25. So the total it will be 0.25, 0.25, 0.5. The total it will be 1 mm. So the pitch here is 1 mm. That means once you put one solder pad, after 1 mm you will put another solder pad. So the center of the first pin to center of the second pin will be 1 mm. Okay, then in this case, where should be the origin of the component? Origin of the component must be center of the two solder pad. So this will be the origin of the component. So this is how we calculate the pitch. So pitch is always from center of the first pin to center of the second pin, center of the first pin to center of the second pin, and this is the pitch. So you will calculate this B divided by 2 plus C is air gap, and again plus B divided by 2. So if you take B divided by 2 plus B divided by 2, it will be common and it will be 1B only. 1B plus C, or you can also say B plus C will be the pitch. So B plus C, you can see B is 0.5, C is also 0.5, that is 1 mm will be the pitch. Okay, fine. So we'll go to editor. Now we know the pitch. So go to the PCB editor. We will create the fresh new package. Go to file, go to new, and we will browse the footprint location, which is in desktop. We'll go to project 1. Inside the footprint, we'll select file all, and we'll give the name that is 1004. Either it is 1004 or 1005. It is 1005. Fine, no problem. So we have the editor 1005. We can write it 1005, and we should always choose package symbol. Package symbol is the type for drawing type for creating the footprints. So now we got, can go and check here, that is 1005.dra, that is the drawing file, and this is the location where we are creating the footprint. So now we need to do some setups here. Go to setups. So I will just go to design parameter. Inside that, first setup is display setup. So I want all displays to be enhanced. So enhanced display mode, I'll keep it all on so that I can see each and every whatever design I am doing, or I can see each and every layers. So click on apply. We'll go to design, and you set the units here. Here I am setting the unit to millimeters and A4 sheet. That's all fine. So I'll just say millimeters A4 sheet, and that you can keep it as it is, and then click apply, and then click OK. So the next thing is we need to set where is the pad location. So go to setup, go to the user preferences, and go to the paths here and click on the library, and here in the library, so you can look for the pad path. So this is the pad path. So we need to assign the pad path so that this particular editor will look for the pad in that particular location. So I will delete the existing. If you find anything which is existing, if you want to delete it, you can use the delete button here, select and delete it. Otherwise you can add it. So click on add. So you'll get the blank box here. Click on browse button on top of it, and you can locate the footprint folder. I'll just select the footprint folder, choose this one. So now it is footprint folder selected. Click OK. So we need to give one more path. One, you keep the pad path. Second one is PSM path, that is the package symbol module or the footprint. That means if you create the footprint, where does that footprint will save, that same location I will give. Open the PSM file, and then if you want to add, you can add it, or if you want to delete the existing, you can delete, and click on add. Go here, go to the desktop, locate the footprint location, just choose it, click OK. Now we have applied the footprint path or pad path. So I'll just zoom. This is the origin. We can see, bring the mouse pointer on top of the origin and scroll it, it will be zooming in. So now with respect to origin, so we have the pitch 1 mm. That means 0.5 left side I'll keep one pin, 0.5 right side I'll keep another pin. That means from pin to pin you will get 1 mm, and origin will be on the center. That is what our plan is. So how to place, I will just adjust the grid to half of the pitch. So if the pitch is 1 mm, I'll put the grids to 0.5 mm. So go to setup, grids. So inside this X and Y, I'll keep the grid, X grid and Y grid. Similarly, I'll keep it for all edge. So don't keep it for offset. So only keep it for spacing. So I'll keep it 0.5 for X axis. Y axis not required, I just keep it same, 0.5 and then 0.5. So then click on OK. So I will on the grids. If you want to on the grids, just go to setup here. Inside the grids, you have grids on button here. Click on the grid on button. Otherwise, you will also find the grid on button on top of here. So you can see the grid toggle. So this is the grid toggle option, the small icon, and this both are same. So if you once if you click, it will be on. One more time if you click, the grids will go off. Similarly here, if you check the grids, you can see. If you uncheck, you will not be able to see the grids. So click OK now, so you'll be able to see the grids. Here you can come to this, click once, the grids will be disappeared, click another, the grids will be on. Now you can see there is a origin on the left one and the right side. I can take a scale also. Here you can see the scale. Click on the scale. So on the left side of the origin, I'll click 1, and on the right side I'll click 1. See the distance, it is 1 mm. So this is how we calculate or we measure the distance between the two grids. So this is 1 mm where we need to keep our solder pad. We will call the solder pad. So to call, go to layout, go to pins. On the right hand side, click on the option. Inside the options, we find the pad stack. So browse for the pad stack here. Click on the browse button. You can see 1004. By mistakenly, I have written it as 1004. Select 1004. Click OK. Now you get your solder pad. So before placing on top of this on top of the screen, just come down on the left side. So here make sure the pin number 1 and it should increment by 1, and offset you keep it both. Offset that refers to pin number location. So where should be your pin number location? So first click, I will right click, oops, if you by mistakenly click somewhere, just make it right click and oops, so it will do undo. So one click should be on the left side of the origin, click. Second click should be on the right side of the origin, click. So right click, done. Now you can see our pad positioning is done properly. So here this is the origin. We will see the distance from center to center, it should be 1 mm, and the air gap they have given is 0.5 mm. So we will also see the air gap. So if those two are right, that means your pad positioning is absolutely right. So we will take the measurement. So click on the first pin and the second pin. I'll just zoom in here and you can see the total pitch is 1 mm. Yes, the pitch is right, and the air gap which is given inside the data sheet is also 0.5. We also achieved 0.5. That means this particular pad stack positioning is perfectly all right. So now here you can see the green color, which is the solder pad, as well as on top of it we will also be having solder paste or paste mask. We say solder paste or paste mask. Outside here we will get the solder mask. So this is which protects your solder pad from the epoxy. This is solder mask, and this is the origin of the sheet. This is origin, and these are pin numbers. These two are the pin numbers, that is pin number 1 and pin number 2. So this is all about pad positioning or pad placement according to your data sheet. The next thing we need to draw here is an assembly top. So assembly top, that means which is the actual area of the part or component. So we need this. So first we need to add actual area of the component, that is assembly top, and then we go for assembly reference. The assembly reference, that means naming the assembly top. These two things we will do. So we know it is 1004, 5. That means the length is 1 mm, width is 0.5 mm. Then that means the length is 1 mm, width is 0.5 mm. So this is what the component or assembly of this particular component. So you can go and check in the data sheet also. So the length here is 1005. It is the length is okay. So the length is 0.04, width is in inches. It is in mm, 1 mm, and width is 0.5 mm. So that is millimeter. This is also in millimeter. So 1 mm length, 0.5 mm width. So how to draw? So we will go to the editor. So go to add, click on the line. So go to right side options. So here we will look for package geometry, assembly top, and we'll keep it 90°. This is bending, line bending 90°, because we are creating 90°, that is each and every bending is 90°. If you keep 45°, the design will come look like this. So we don't want that, we want 90°. We'll choose it. Line width according to standard, you just keep it either 4 mils or 5 mils. I'll keep it 0.127, that is 5 mils. Keep the line font solid. Okay, we need to draw, so just right click and oops. So I will click on the origin, and we need to draw 1 mm right side, 0.5 mm upside. So to do that, we will use the command prompt. So the command prompt is, we have already clicked on origin. If you have already clicked, so if you want to start the design from the previous click, it should be ix. Command is ix. So here x refers to origin, x refers to from origin, and ix refers to from previous click or from last click. So this is how these two command will work. If I put x here in the command, you can see the command bar. If I put x, after x we will add space, it will go to x axis. For example, if I put 0, it will be x axis, or that is origin to 0, and again if you space one space, that will be y axis. That means x refers to origin, this is the origin. So first number which will be given to x axis, second number is given to y axis. If I type this, so you will be having one click on top of the origin, x00. ix, that refers to, ix refers to from the last click, ix space. So from the last click, where was the last click? It is on 00, that means it is on origin. So ix space, it is 1 mm on the x-axis, space, it will go to y-axis, that is 0.5. So this is how we give the commands here. Ix, that refers to from the previous click, that means from the origin. Already one click is done from the origin. If you want to come towards right side, so the x-axis is 1 mm, so I'll give 1 mm. If you want to go up, the plus space, and then this will be the y-axis coordinate. So this way use the command, and we will draw the x and y axis. So I'll just zoom in here, I'll just make it oops, will start here. I'll just type x space 0 space 0, that means I am clicking on top of the origin. Now you can see automatically it is clicked on top of the origin. So now I'll go to ix, that means from the previous click 1 mm on x-axis, space, that will go to y-axis, that is 0.5. So the first number will be on 1 mm, that is x-axis, second number is of y-axis. Just close this. Okay, so I'll just press OK here, enter here. Now you can see, so this is 1 mm, this is 0.5 mm. If you want to come back to 0, I'll just press x space 0 space 0, x space 0 space 0, and then right click, done. So this is the assembly of your component. So now it is on the x and y axis on the right side. I wanted to move it to the body center. To move with the body center, I'll click on the move button. Here you can see the move button. So click on this move icon, and so if you want to move, just click on the assembly. So now you will not be able to place it properly on top of the center of the component. So if you want to do so, on the right side, click on the point, this is mouse pointer. So I will choose body center. If I click on body center, what happens? If I click somewhere, it will take to the body center. So this will be the body center. So now I will be able to put it inside on the particular origin. So now click here. Now it comes to the center. Now you click on the origin. So now this particular assembly is exactly placing on top of the solder pad. So here this is solder pad, paste mask, solder mask, and now we got the assembly. That means this is the actual component area. As soon as you draw the assembly, we'll quickly go for place bound top. So we'll go to edit, place a z copy shape. I'll just draw the exactly whatever it is. So go to package geometry and draw the place on top. So I'll just click on the assembly. So there is a small symbol is created. So using this, you can go to check 3D view and 3D canvas. You can see the height of the component. So this is the random height. So if you want to reduce or if you want to give the exact height, first we will see what is the exact height in the data sheet. The exact height of this particular component is 0402 or 1005. The height is given in the height column, that is in millimeters. It is 0.35. So the height is 0.35. So we will assign the height. So go to editor, go to setup, go to areas and package height. So now click on this shape. Now here on the right side, if you see, the height column will open. I'll give always maximum for SMT component. The maximum height is 0.35. Press enter, come inside, do right click and done. So this is a procedure to check the height of the components, to add the height of the component. Now we go to view and 3D canvas. You can see the footprint now. So here you can see this is the solder mask and solder pad. This is the solder pad, this is the air gap, and this is the component which is placed on your footprint. Okay, so next we need to add is name to this particular assembly. We will add the name to this assembly. To add the name, go to layout, label, reference. So what reference? It should be an assembly reference, but reference designator assembly top. Reference designator, that means giving the name to whom? To assembly top. So that class is reference designator, assembly top is a subclass. Just click on assembly, type it is a capacitor we are creating. I just say capacitor C star. Actually the data sheet of register, but both will be the same. I'll put the C star, that refers to the capacitor. Star refers here the variable number, that is C1, C2, C3, C4. Likewise the number will increase according to your schematic. So this is the procedure to create assembly, height as well as solder pads. The next thing we are creating is silk screen. Silk screen top. Silk screen, as I told you, it is an ink print. Okay, it is an ink print on the PCB. So for capacitor you can draw like rectangular. So whatever you draw, it's depending upon your drawing skills, that will be printed. Some people use complete box, they will draw, so that no other component should involve within that area. So that is like a boundary and it is printed on the PCB. And some people will draw on the only corner this way, that is also fine. And some people will draw only on the top and bottom, right and left. So this is the print which will print on the PCB. So we will go with the standard and we will draw the complete rectangle. So there is one rule here. So if you are drawing the silk screen, from this solder pad, at least it should be 20 to 25 mils outside. 20 to 26 it is, 20 to 26 mils away. Either it is outside or inside, no problem. It should be 20 to 25 mils, it should be outside. Similarly from assembly also, whichever is outside, from there it should maintain 20 to 25. So I will reduce the grid to, go to setup, I will reduce the grid to 20 mils, that is 0.5 or 0.6 you can take. I'll just make it 0.5, the minimum value. 0.5 is up to 20 mils. You can go for 0.6 or 0.7. I will reduce it to 0.5 and then I will show you how to draw the silk screen. So I'll go to add line. On the right hand side, go to class must be package geometry, that means it is footprint. In footprint I want to draw, that is subclass, that is silk screen top. So 90° only I will draw, and line width must be at least 6 mils. It is a proper visible width, it is 1524. 0.1524 is the line width. So this is about the settings. So now we will click outside. So here you see this is the grid which is very near to the solder pad, and we can't achieve 20 mils. Here also we can't achieve 20 mils. So I'll go to outside grid. So from here I will draw the silk screen. So that is at least minimum 20 mils. Click here and then you can draw silk screen on the four corner. So now you can see it is minimum, it will be having 20 to 25 mils distance from the assembly, also from the solder pad, also on 4 sides. So this is the minimum spacing we must give according to your rules. So you can also put it inside, make sure the same 20 to 26 mils distance it should follow. So now we will give the name to the silk screen also. So go to layout, labels, reference designator, go to reference designator and silk screen top. Click on the silk screen, it is capacitor, I'll give C star, right click and then click on done. So now we have done assembly as well as silk screen top. The final touch we will give, the final touch is go to edit Z copy shape. We will give the one more, that is DFA bound top. So package geometry and DFA bound top, we will expand it from the silk screen, we will expand it to 20 mils, that is 0.5 mm. 0.5 mm we will expand. That means it will give another extra space for DFA bond top. So this space is used for proper soldering purpose. The assembler will get enough space between the components so that he can solder it properly, desolder it properly, assembly testing he can do it properly. So this is for DFA bound top. This extra area for any component to get proper soldering or proper placement, assembly placement and testability purpose. So this is all about the footprint creation, and we have got some extra restriction. The restriction here is route restriction. So routing is not allowed in some certain part of this area. That means if you are routing the PCB, so you can do route from the pin here and outside, you can go wherever you want to connect, you can connect it, but inside, in between the two pads, it's very small area. So here we don't want to route, so we don't want any designers to route between the two pins and manipulate. So that's why what we need to do, we will put a proper restrictions between this. So this area we will block it for routing. So we will reduce the grids to 0.5 because it is very big grid. So we'll just reduce it to 0.1, that is 4 mils. Okay, so now we will take one routing here. So to get the routing, we'll just click on the route option. So here is the route option. This is a route icon. Click on the route icon. So I can do the routing this way. So now there is no restrictions between, yes, it is coming in between this. So I just don't want them to route like this. The designers are, if I am the designer, I don't want to route once I am doing the board design, because this routing may consisting of high voltage or high frequency signals which affects the pad, or these pads might have high voltage or high frequency signals that might affect your content or the data or the information which is flowing across this particular trace or route. So to avoid that, we just have to restrict the area. I just block the restriction routing in between this. So what I'll do, I'll just delete this routing and we'll put the shape rectangular I will take, and here I will take the route keep out option. On the class I will take route keep out. So on which layer, I just want it on the top layer only, because this is SMD component. By default on the top layer I don't want, bottom layer no problem, and internal layer also no problem. Let them design, they let them out. So on top, because we have the solder pads on top only, so I don't want any routing between that on top layer. So click here and then we'll add some restriction, right click and then done. So I draw some shape here so that now it will restrict the route inside that particular two, between the two solder pads. Now I can route. See, I'm now getting the error. So if I go, it will go from the outside. So it is now, if I forcefully click, it will go outside only. So if it is left side, it will come left side. If it is right side, it will go to the right side, but it will not do routing in between the two particular pads. So this is how we do the restriction of routing. So if you have these restrictions, yes, you will get the error. You have to remove that particular error. That means you have to remove the routing, and then this is blocking your routing creation on top of the or on between the two solder pads. Yes, this is all about footprint preparation. And now this is the capacitor to C2. We will apply the 3D component. So to apply the 3D component, we already have the 3D which is stored in our data in our folder. We'll go back to the folder. So we'll see before adding the 3D how it looks like. So I'll go to view, I'll save it. Once you save this, you can see the PFSM file is created. So the drawing file is saved to the disk, and 1005 the PSM is created. This PSM itself is our footprint. So now we have successfully created the footprint. Now we will apply the 3D model or step model. So before adding the step model, you can see view 3D canvas, and you can see this is what the component we have. So this is the component, this is a solder pad, and here white color you see, this is masking where we do not have any coloring on top of it. And here we have the cell screen, that is ink print on top of the PCB, and extra space is reserved for proper soldering and desoldering and testing purpose. So this component is very small actually, so testing is quite difficult. Your solder bit will be big, testing bit will be very big if you compare with this particular component. So this is about the 3D. So we will add 3D. Before 3D it looks like this. Now we are going to add the 3D component. So to do that, go to setup and then click on the step package mapping. Click on the step package mapping. So now you can see the two things here. On the top side we have the footprint, on the bottom side it will ask you to add the step model. So to add the step model, first we need to locate the component. Here we got the C2 is a step model. So on the right hand side you can see here, this is the C2 which we have. It is locating the step model C2 which we need. I selected the C2. Now C2 I can see here. So to overlap this, we have the transparent symbol, you can see, or step you can see, both if you want you can see both. So if you overlay, the both will be overlapped and we can see both. I'll just take the step model. Yes, we have this SMT solder pad, and on top of it we have the component. So hide the board, we only see the footprint and 3D models. Okay, fine. So everything is fine here. Okay, we'll go to click OK now. Save this and close it. So now save this particular footprint and go to the 3D canvas. Go to view and 3D canvas. Otherwise you have a 3D option here also. 3D. So now you can see the 3D component. So before there was no 3D component. Now this particular 3D is properly sitting on top of the solder pad. So you can see this white color. So this is the actual pad. On actual pad we have this solder pad. So this is the solder pad, and white color you can see here. Due to the mask there is no color. Due to the mask, this is the color of the PCB. Due to the mask we don't find any kind of color over there. So this particular solder pad is open for soldering. So this is all about creating the solder pad, creating the footprint, and adding the 3D step model to your particular footprint. So we will continue the footprint for other components also. Okay, so now we will discuss about the capacitor C1, which is 100 microfarad, and which is through hole technology, or it is PTH, that is plated through hole. So we have the data sheet which is downloaded, and just go back and check with the BOM creation, where you will get the link for a BOM. So this is the capacitor. We have multiple sizes here. You can see the D that says the component diameter. So this particular component is an axial or cylindrical. We can say this looks like this. So, and there is a body of this particular capacitor, and we have got two leads. So this is the caps D, that is the body diameter, and here is the body diameter. We have a different size of the capacitors here. So I am going to create the first one, which is 5 mm diameter, and the lead dia, which is given here, the small d. You can see the lead dia, and this is the laying capacitor. So you can see this is the body diameter, and this is the body height. And then we have the lead, the one lead which is uh, the length is more, and one lead the length is small. The assembler who assembles this particular component on top of the PCB is, whenever he see the long lead, that is the pin number 1 or the plus pin. If the pin lead is small, the length is small compared to the other one, which is minus pin or the negative pin or the second pin. So I'm going to use the first one, which is 5 mm diameter, and the lead dia for the 5 mm is 0.5 mm is the lead dia. So nothing else, only these two, and the pitch is also given. The pitch here is the F. I'll just zoom in a little bit, and the pitch between the two pins. So this is the first pin, and this is the second pin reference, and the pitch between the two is F, which is given in the third columns. So only the three details they have given. One is the body diameter, lead diameter, and the pitch. So you can see the lead diameter, the lead diameter is same for the 0.5 for 5 mm dia and 6.3 mm dia. Likewise 0.6 is the same for 8 mm, 10 mm, and 12.5 mm diameter, and the pitch is same for 10 mm as well as 12.5 mm dia of the component. So now I am going to choose the first one only, that is 0.5 mm diameter and 0.5 mm lead dia and 2 mm pitch. So before that, we will discuss about how the through hole component will be placed. So this is a PCB. So we have the component which is axial or cylindrical, we also say. So this is a cylindrical, and this is the component. And we got the two leads. One is the long length and one is the small length. So the long length is pin number 1, this is plus pin, and this is minus pin. Yes, the lead diameter is given. The lead dia, let's say the lead dia is equal to 0.5 mm, but nothing else given for creating the footprint. So we have to follow the standard, that IPC standard we have to follow to calculate the solder pad, the solder mask, and as well as the drill. So we are putting the drill on top of it. So what if I put the same drills? If the drill dia is also same, if I put the drill dia is 0.5 mm, so here you can see on the PCB I am putting the drill which is 0.5 mm for both, and lead is also 0.5 mm. So you will not be able to insert the lead properly inside your PCB. So that's why what we do is we add some extra drill, so that our lead should properly insert inside the drill and it can pass through the PCB. So that's why the drill we need to add, that drill formula will be, so the drill dia formula will be, it is on top of the lead dia, so it should be lead diameter plus, at least we should go for 5 mils minimum to up to 10 mils. So this is what the formula is. So the lead dia plus either 5 mils is a minimum, is a requirement, and up to 10 mils also you can take. And don't waste too much drill. I don't recommend you to take more than 10 mils, like 10 mils, 15 mils, 20 mils. I don't recommend you to take. So keep it short, a small drill, a little bit bigger length if you compare to the lead dia. 5 mils is enough, 10 mils is more than enough. So we can insert the lead properly. Now we got to know about the lead. So, and then we will add the solder pad. Solder dia we can say, because this is a circular or annular ring, you will get it. So the solder dia will be on top of the drill, so it should be drill dia plus. So drill dia plus, according to the rule, it should be at least, that is minimum will be 12 mils. So 12 mils, you just convert it into millimeters. So this would be the formula. So it is not exactly 12 mils, it should be minimum 12 mils for proper soldering purpose. So you can take more than 12 mils, that is also fine. I can take more than 12 mils, like I can take 15 mils, 20 mils, 25 mils, 30 mils, 40 mils, you can take it, but don't take less than 12 mils. So your solder will not be that much strong if you take less than 12 mils. The suggestion or recommendation is minimum 12 mils. So in this case I will take into twice, so into 2 I will take. That means if the drill is 1 mm, if the drill is 1 mm, I will prefer 2 mm solder pad. So here the drill is, for example, 0.5 is a lead dia. Drill dia is 0.5 plus 5 or 10 mils we will have, so we will get around 0.6 or 0.7. So I will take dia solder pad is into 2 times, that is I will take 1.2 mm. So this way also you can make it, but make sure you have at least 12 mils, so angular ring should be designed. So this is all about through hole. We will do the calculation. So I will take the first one. We'll open the notepad. We do the calculations for capacitor. So this capacitor is radial lit, just set cap, that is capacitor. And I will take the diameter, so the body dia, that is assembly here this case is circular. And the diameter is, assembly dia is 5 mm, so that is diameter is 5 mm. So the lead dia, the formula is, the lead dia is already given, which is 0.5 mm. So the lead dia is 0.5 mm. So you can concentrate on drill dia formula. So we'll take the drill dia. So I will take drill dia, that is lead dia plus. So I will give the 5 mils minimum, that is 5 mils to 10 mils you can take. That is what they recommended or suggested from the IPC. So you can take 5 or 10 mils. I can take 6 mil also, 7 mil, 8 mil, 9 mil, also 10 mils. Don't take less than 5 mils. Again, it will be difficult to insert, and don't take more than 10 mils. It is a waste of space on the PCB. So in this training purpose, I will use 10 mils. That is lead dia. In this case is 0.5 mm plus 10 mils. I will take 10 mils. Okay, so that is 0.254 mm. So the drill dia here will be, that is 0.754 mm. So now I hope you understood this calculation. So whenever you have a drill dia, so I will take at least drill dia, whenever you have a lead dia, I will take drill dia will be lead dia plus 10 mils. So now I got the proper, because the lead which I am looking for, the lead diameter which I am looking for is 0.5 mm. So I want the drill must be more than that, so that it should insert properly inside this. So I taken 10 mils extra, so it will insert it properly. So the next thing is the solder pad. It required solder pad is equal to, so I will say drill dia, it should be on top of drill. So drill dia plus, will take drill dia plus at least 12 mils, as I said, should be 12 mils, or I will take into 2. So you can take drill dia into 2 times, that is also good option. So here 0.754, we have a 754 mm into 2, so into 2 you can make it. So we'll go with calculator. So I will always prefer, for after decimal 4 points I will prefer for accuracy purpose. I will take 0.754 into 2, that is around 1.508 is the solder pad. So if you feel it is very big, you can reduce it, come 12 mils, 15 mils, you can add it. So this is enough. So into twice the solder pad. So when you design, you will understand how it looks like. So now the solder mask is the same. So solder mask is equal to, it is on top of solder pad, it is solder pad plus 6 mils, that is 0.1524 mm. So the solder pad here is, which just now calculated, it is 1.508. It is 1.508 plus 0.1524, it is 6 mil, that is 1.6604 will be the solder pad. So these are the calculations. Simple. Solder mask and solder mask is same. We are just adding 6 mils extra from the solder pad, and whenever you have a lead dia 0.5, I will add 10 mils extra to make the drill dia, and I will add twice to make the solder pad. But minimum requirement is at least 12 mils on top of the drill. So this is all about the solder details, and then we go for pitch. So the pitch is F, which is given, that F is 2 mm here, so we'll take 2 mm. The pitch is 2 mm, and we'll take the grid, half of it. So grid is equal to 1 mm, so we'll put the grid 1 mm. So okay, we'll go to the pad stack editor, and we'll go to, okay, for before that we will discuss about the naming standard. The naming standard here is, so what will be this? Drill or solder pad. So the drill is circular, so I will take C as a prefix. Underscore or hyphen you can use, up to you. Don't use any other apart from underscore and hyphen. Don't use any other special symbols. So it is, the drill refers to D, into P refers to pad. So D is a drill, so the drill in this case is 0.754. so here this represents 0.754 mm drill. So that's 0.754. The D refers to drill, or you can even use H also, that refers to hole. So similarly, pad is 1.6604, sorry, 1.508. So we can take 1.508. So now here to explain that, this is 0.754 mm drill, and this is 1.508 mm pad. The P refers to pad, and later you can write anything like, which is to identify like what type of package it is, what component it is, like capacitor, you can write it. But this is to identify what will be the drill and what will be the solder pad, and the C refers to what is the shape of the solder pad or the drill. So that's it. This is the pad name, so I'll just copy, and while creating the solder pad in pad stack editor, I'll go to file, new, and go to the location in the footprint. I'll just give the same name here. I'll be able to understand this. So now go to the through hole. So click on the through hole here, or through pin, click OK. So now you cross check, come up here and cross check. This is what the pad name, and this is the location where we are creating the footprint. So now come down and check out the units. Units must be in millimeters, and then click OK. It is a through pin, so I choose through pin and circular pad, so I will select circle pad. So go to drill now. So drill, we know the drill section, so here 0.754 will be the drill, and the tolerance which is given in the data sheet, according to that you can give the tolerance. Just go back and check the data sheet. If the tolerance is given, you can add the tolerance. Here it is not given, just leave it. I will come back, and secondary drill not required. Drill symbol, it will be given to you what type of symbol to be used, circular symbol, and the character, if I say A, and the drill figure, just you can leave it. So similarly, the drill offset, I just don't want, keep it both 0, so that the origin will be exactly on the center of the circle. So origin will be exactly on the center of the circle. So later we go to design layers. So here, if this is your PCB, if this PCB is multi-layer, like 4-layer or 6-layer, if you are putting the drill, so drill has to pass through all the layers from the top to bottom, and including the internal layers. So we need to add all, that is begin layer, end layer, and default internal layers. So I want to put the whole from top to bottom, that is pad from top to bottom. So come here, select the pad is 1.508. I'll put 1.508, Now you can see that on the top we got the drill and pad. So here you can see on the top we have the drill and pad. So here, so the red color is the drill, and the blue color is the pad. So if you see this pad is too much, you can reduce it here, no problem. So but make sure it should have at least 12 mils outside the drill. So I'll just copy the same thing, put it to the internal layers. Now you can see here this internal layer is also updated. Now we'll put this into the bottom or end layer. Now you can see from top to bottom we have the drill as well as solder pad. So on the top and bottom we used to solder it and get the connection. For example, if you have the PCB on internal layers, so why we need solder pads in internal layers? That is what the question is. So if you have a drill on top to bottom, so if you have a drill from top to bottom, so on top we know that for soldering purpose we need the solder pad, and bottom also we are doing soldering on the bottom, so we need the bottom side solder masks. But what is the reason we need an internal layer? The solder pad is only not only used for soldering purpose, for connectivity purpose also we use the solder pad. So on top and bottom, yes, we can do the connectivity. Along with that, we can also use it for soldering purpose. For internal layer, it is purely for connectivity or the routing purpose we use. So for top to bottom, we must have the solder pads. So this is all about adding the solder pad and a regular layer. And go to mask layer. So we put mask on only the top and bottom layer. Why? Because so if you have an internal layer PCBs, for example, if you are putting the drill from top to bottom, and also you are adding the solder pad on top, you are adding the solder pad on bottom, you are adding the in internal layer also. So in this case we are coloring the PCB on only top and bottom. For example, if you are coloring the PCB or putting the epoxy on top and bottom only, we are not putting the epoxy on internal layer. That's why we don't want mask on the internal layer, so we only put mask on top and bottom. To protect this, we need a mask on top and we mask on the bottom side. So internal layer, we are not making any kind of coloring epoxy. So we go to solder mask. So we have already calculated the solder mask. We just solder mask is 1.6604. Copy this and put it here in the diameter. So copy this and paste it to bottom also. So top and bottom both side we got the mask layer. So go to file and then click on save. So it has some got one warning and click yes. That's it. Your pad is created. You can see on the right side corner. So your pad is created. Once your pad is created, we'll go for a footprint preparation. So just minimize this and go to PCB editor. So pitch, we have the pitch that is 2 mm. So we can keep the grid as 1 mm so that we can bring the origin on exactly on the center of the body. We'll go to editor now. So go to file and new, and I will choose the same location and I'll give the name of the footprint. I just say cap. That's more than enough. If you have any special packages to the packages, you can write that package also. So click OK. So we'll do the setups which we have done in the last session also while creating the SMT capacitor or SMT component. So select all the display enhancement mode and go to the grids. I'll make the grids as 1 mm because the pitch is 2 mm. I'll make it 1 mm and then click on OK and click OK. So now I'll zoom in on the grids, toggle the grids and call for the pads. So go to layout and pins, go to the right side option, click on the pad stack. We have the second pad, that is capacitor through hole pad, and we will make it offset 0 0 so that pin number should be on the origin of the pad. From the origin left side one click we do, and from the origin right side one click we do. So right click, done. So these are the two solder pads which are for the capacitor. I'll take the scale and check it out. The total pitch is 2 mm, that is total distance is 2 mm. So that's enough. This is the right placement which we have done, and here you can observe. So the white color inside you find is the drill, which is to insert your lead of the component, and this is the solder pad, and outside you can see the 6 mil is the solder mask. This is the solder mask. Okay, so these are the three things which we have created in through hole. In SMT we will also have the solder paste. So now we will draw the assembly. Unlike SMD that is which we have created capacitor, it was rectangular, but here we have the circular assembly. We just go to the PDF or the data sheet. You can see this is the D, which is 5 mm, which we are creating 5 mm circular. So we need to create assembly as circle assembly. So we'll go to add and circular assembly circle. On the right side you come the class, it should be package geometry assembly top, and I'll just give 5 mils for proper visible width. And you can draw here, we got the three options. One is draw a circle, second one is place a circle, and third one is center radius. I'll use third one, center radius, so that it will create and put it on the center of the body. So go back and click on center radius, and then the radius, we know the diameter, so diameter is 5, the radius must be 2.5 in x0 y0, and click on create. So this is your assembly top, which is outside the, or this is what the body of the component. So now we'll go to Z copy shape, we'll put the place bound top to assign the height. So we'll go to package geometry and then place bound top, and click on the assembly, right click, done. And then we'll assign the height. We'll see the height first inside this. So the height is L, it is given here, the height is L, which is inside this table. We should look for the L here. So you can see the D to L. So for 5 mm, so inside this D into L, D is a 5 and L is 11. For 33 microfarad it is 11, 47 is also 11. So we'll take almost, it is 11 mm. So height I will take 11 mm from the surface of the PCB. So if you want some small air gap, if you don't want to put your PCB completely on top of a component on top of the PCB, for example, so if this is your PCB, so if you don't want to touch the component, you don't want to touch the component completely to the PCB and do the placement, if you want some gap, so you can take the at least 1 mm gap and put it that as minimum height. So the maximum height will be minimum plus total height of the body. So it's from the surface to the total body height will be the maximum, and minimum will be the air gap. So this is how we assign the height. If you only add maximum, we'll only get without the air gap. So here it is 11 mm. So we'll go to setup and areas, package height. I'll show you first. I'll click on the assembly. I'll keep it 11 mm directly and right click, done. Check out in the 3D canvas. The component is completely touching to the PCB. So we don't want to touch that. So if you want that, you just have to change, go to setup, areas, and package height. Click on this. Minimum 1 mm gap will give, and if I give 1 mm from the surface, the body height will be 1 mm plus 11 mm, it will be 12 mm. So right click and done. So go to the 3D canvas and you can see this is the component. You can see here the some part of the component is shifted up. So we'll go and check in the view. From the side view we can check it out. So this is the PCB and 1 mm gap will be having, so accordingly the component is placing on top of the PCB. So this is about assembly height. Assembly and assembly height will give the label of the assembly reference, which is C star, it is capacitor. Right click and done. Now we will draw, change the grids to 0.5 mm. Outside 0.5 we will draw the silk screen, that is ink print on the PCB. So to draw the ink print, just change it, go to add and then click on the circle, package geometry, and then click on silk screen top. So I'll keep 6 mils, so proper visible width. I'll draw manually. I'll click on the origin, I'll come outside. From the assembly, one grid outside I will draw. From the assembly, one grid outside. So I'll click on the origin, come towards right side or upside or left side, wherever you want. But make sure only one grid outside it should be. Click on one grid outside, right click and then done. So now you can see the 3D canvas. Outside you can see the print here. So the outside we can see the ink print on the PCB. So now we will rename it, sorry, not rename, we just give the label to the silk screen top. Go to silk screen, click on the silk screen, C star. So according to a schematic, the C1, C2, C3, the numbers will be variable. And finally we'll give the DFA bound top, which I have explained while creating SMT. So DFA bound top, it should be 0.5 outside, that is 20 to 25 mils outside the cell screen, and I click done. So this is about footprint creation of capacitor, that is through hole capacitor. So once I save this, I got here that capacitor dot PSM is created. So next thing is, so we need to add the 3D model. So we'll go to setup and go to areas, and not areas, step package mapping, and inside this I'll select the C2. C2 is SMT, that is C1. Okay, C1 I selected, and I'll click on overlay, and we'll see the bottom view so that we can see whether it is properly assigned or aligned or not. Okay, I hope this is quite different, because as of now you can see the drills are very far. From here to here it is very far drill, because I have used like 2 mm, so they have the 3D footprint is quite different. So I will create a different footprint and assign it, because according to that footprint only we need to create it. So we'll go to the left side. You can see that footprint is different, sorry, 3D is different. I have created different footprint. So I have to increase, for example it is might be more than 2 mm, it is 2.5 or 3 mm. So we have seen in the data sheet, so it has got 8 mm, that is 3.5 mm, 2.5 mm. So I will check it out, and I will create the footprint for that particular 3D, and I will show you. So this is about, I'll just save this. So there is a random 3D, but it is not the actual 3D. So just check it out. So it is not the actual 3D. We'll go to with camera and bottom side. See, the pins are different. The pitch is completely different. We will check this pitch. That particular footprint we are going to create it and put it on top of the footprint. So this is about a through hole footprint. So in the next we will see the connector or header footprint. Okay, so this particular 3D was designed for a 0.6 mm lead dia and a 10 mm body diameter. So I have created a footprint for 0.6 mm and 10 mm body diameter, and 3.5 was the pitch. So that is what the 3D step package. So I have created a footprint for 10 mm body dia, 0.6 mm lead dia, and 3.5 mm pitch. So we can just show you, so which is I have created, and also I've attached the PCB footprint 3D model, and it looks like this. So just come to camera and then the top. This is how it looks like. You can see the sales screen is just out sales screen outline is drawn properly, and we can see the isometric view. So it is shifted a little bit up 1 mm. I have shifted it because it is through hole. I don't want to touch it to the PCB. So you can see that from the front view. Here inside the drill properly, the leads are inserting properly. So this is about the capacitor footprint. So now we will look for, just save this and make sure you have a PSM is created properly or not. Okay, so now we will look for the connector, that is 2-pin connectors we have. So we should go to our data sheets, and the J1 and J2 connector we have. So I'll make sure I just close this capacitor. Okay, sorry. Open the J1 and J2 two connectors we have here. Okay, so I'll just take the minimum required values, and I will show you how to make this. So you can see this drill dia is directly given, that is A. We have to look for A here inside this particular table. So all the units are in inches here, so we will deal with inches only, or you can convert it into millimeters, and accordingly you can choose. So the A is the drill diameter. There is no lead shown here. A is the lead diameter, sorry, drill diameter. Lead diameter is not given. If the directly is drill is given, you can go through the drill option only. So the next thing here is the pitch. Pitch is 2.54. So one next to other pin is 2.54 is the pitch, and on the x-axis also it is 2.54 only. So I will explain you this in detail. So for header pin, most of the time the header pin will take 1 mm drill and 2 mm solder pad, and the pitch is 2.54 mm. Okay, so if we have a two pins, for example, as they have shown here, if they have a two pins, that is one pin here and the second pin. If you have a two pins, so the length of the assembly is 2 into 2.54. Width of the assembly is 1 into 2.54. So if you see, there are two columns and one row. So this is one row and there are two columns. To find out the length of the assembly, so it should be 2.54 into 2, because of the number of pins are 2, and width here you can see only one column, that is 1 into 2.54. So your assembly is 2.54 into 5.08, and the pitch between the two will be 2.54. So that is universal standard. The pitch is 2.54 on x-axis or y-axis. So this is how we make this particular connector. So we will create the solder pad and quickly we will make it. I'll just go to file and click on new, and I say here it is an header 2 pin. So click OK. So we'll take through pin circle pad. Drill is, I'll keep it 1 mm drill, and then we'll go to design layers. In the design layers we'll make it 2 mm pad. So copy this and paste it. Mask, it is 2.1524. We'll take it 6 mils extra, that is 2.1524, and copy it from top to bottom. So I hope you understood. So I'll take it quite faster way, because so you have already know about the complete calculations of through hole. So go to file and save it. So you'll get warnings, close with warnings. That's it. So now to create, so we'll go to editor. So go to file and new, and we'll go to header 2, say header, and then 2, its package symbol, click OK. We'll go to setup, do the setups. So if you feel it's very fast, you can make it 0.2 mm speed, 0.2 speed, and you can make it slow and you can listen the class. So click OK, and then so we'll change the grid to half of the pitch. The pitch is 2.54. I'll make the grid is 1.27. Half of the grid is 1.27. 1.27. Click OK on the grids, and we'll call the pins now. I have already created the header pin. I'll take the header pin and make sure the grid, the offset is 0. So one is on the left side, another one is on the right side. Click OK. Now we will draw the assembly. Go to add line, the package geometry, assembly top. It's a 90-degree. We'll take 0.1 mm and 0.127, 4 or 5 mils you can take, and we will draw it from x-axis. This is x00, and then ix, it should be an x-axis is 2.54 into 2, that is 5.08, and y-axis it is 2.54. Press enter, and then again you bring back to 0. So now you can see this is what assembly is created. Just click on move with respect to body center, bring it to the exact center, right click, done. So if you want the chamfer here, 45-degree bending on the corners, you can choose the chamfer option. So go to dimensions and you can choose the chamfer option. So chamfer is make 45-degree bending on the corners. Fillet is used to make the circular bending or arc. You can do it on the corners. I'll choose the chamfer here, so which is, I'll keep it 1 mm and check it. I hope 1 mm is too big, so we'll reduce it. Right click, oops you do, it's like an undo. I'll make it 0.5 and check it out. If it is feels very big, then you can still reduce it. So this is enough. I'll check. I'll click on the corner segments, one segment and second segment. In that corner you will get the chamfer. So right click and then click on done. So you can go to 3D, you can go to setup, and I'll go to step package mapping. So we have a J1 and J2 step package. So it's okay, the package is sleeping here, so we will make it a rotate option. So go to it is y-axis. I'll make it 90°. Okay, that's fine, and we will shift it to again 90°. Sorry, so make it 0. So we should bring it on z-axis. So it's going very far, we'll bring it 0. So we will rotate it on the x-axis on the 90°. So this component is slipping. We will overlay this one, and we need to bring it y-axis, z-axis to 0. It's already 0, so minus 90 we can do it. Not, it's not working. 0, and this one will make it minus 90. It's going very far. So we should lift up. We will see this from the front view. It's a sleeping mode, and we should bring y-axis. This is right side. Z-axis we should bring it to. We will bring it 0, 0, 0, and this one minus 90. We'll trial and error, we'll do it, and we will rotate this particular component. Click here and make it 0. We'll only take okay, we will keep it 90, make it 0, and then again 90, and then make it 0, 0, and then 0. That's enough. So this particular 3D is perfectly aligned. So we'll go to view and we'll go to bottom and cross check. Yeah, that is fine. It is properly sitting on top of the uh, footprint, and we can see it from the right side. Yes, this is it sitting properly here. Just make it 90 on the rotation, so it will rotate it, and z-axis 90°. It will rotate perfectly. It will sit it on the solder pads. So bottom, if you can see, that's enough. So we'll just save this, click on close, and we'll go to 3D canvas and see here. Okay, so this is perfectly sitting on top of the footprint. So we'll continue the footprint. So here we will assign z copy shape. We'll go to options and go to place bound top and make it 0. Click on top of it. So height for this component, height is also 2.54. Make sure that the header has pitch 2.54, length is 2.54 into number of pins, width is 2.54 into number of pins, pitch is 2.54, and x pitch, y pitch is also 2.54, and height is also 2.54. So we keep it 2.54 height. Right click and done, and we will go with grids to 0.5 at 20 to 25 mils, 0.5, 0.6 you can take it, and then we will add the silk screen, that is ink print on the PCB. We'll take add a line and go to package geometry and silk screen top. We'll keep 6 mil line width, so it is proper visible width. So we'll keep it outside, but here if you see, it is very close to the component. So if you want, you can neglect that, and I will reduce the grids to 0.25 because we can get some extra 0.5, 0.25 0.25, 0.25. So and then go to 0.25, 0.25, and then you can draw. So now we'll go to add and then click on line silk screen top. So here it is 0.25. It is actually not, it is actually 0.5, and here it is, I'll just take this much part. So we cannot waste the space on top of it. Right click and done. So if we have taken 0.5, so from this it will take to the 0.5. It's very far from the this particular grid. So what we did is, so we have taken 0.25 so that we will get the proper grids. So we'll go to dimensions and chamfer it to 0.5. So it is very far. I'll make it 0.75 for the proper alignment. So click on all the segments on the corner side, click the segments, and it will turn to 45-degree, and right click done. So now go and see the canvas, 3D canvas. You can see the print on outside. So this is the ink print outside we have. So we'll now add the DFA bound top. Go to Z copy shape and DFA bound top. For assembly clearance, we'll 0.5 or 0.6, we will extend it according to your company standard. You can extend it. So we'll save. Before saving, we'll go to the labels. It is a connector. For connector we always take J star, J1, J2, J3 it will be, and also add the silk screen and then click on the silk screen, that is also J star. Right click and then click on done. So now save it. So before okay, fine, we have saved it. The PSM is created. You just cross check the PSM is created. Once you're done with this, and we'll go to the 3D canvas and check it out. So this is a total footprint. So you can see it from the bottom view, top view and bottom view. So perfectly it is aligned to the solder pads. It's fine. So this is all about footprint creation we have seen. So we will also see how to download the footprints and use it. So now you know how to create SMT footprints and through hole footprints. Now I will show you how to download it and check it out, how to use that downloaded footprint. So the next I would like to take that register. We have to download all. So we have taken this particular register. So we will go to the BOM so that we will understand. Go to the documents and we'll open the BOM. So we have the part number inside the BOM, so we can get it directly from the BOM. So the register one, so we have this MPN that I'll double click on top of it. Otherwise, this is a PDF, we can get it. So we'll go to the part number and we will search inside the website. So I have taken all the components from the dizzy keys, so I'll select the dizzy keys only. So I will show you how to download the footprint as well as 3D. 3D we have already seen. We will download the footprints and check it how to use that particular footprints. So come down in the documents and media. So inside this we have the CAD models. Select the CAD models. So you know EDA models, it shows you the footprints. The CAD models will give you the symbol creation, symbol to download the symbol as well as footprints. So I'll click on the CAD models. So you can see here we have the symbol of the register and the footprint of the register. So if you want to choose which one you want, so in SnapMagic we don't have a preview. We'll try to select in the SnapMagic or in the LtlBiTech. So these are the two different vendors, LtlBiTech and SnapMagic. From their website also you will be able to download these kind of footprints. So we'll click on the download format. So if you have any OrCAD format, you can choose OrCAD Capture or Allegro. Also if you have Allegro, you can choose the Allegro. So we have OrCAD Capture and Allegro. Just select it, click on download and wait for it. Once it download, we will see whether that particular footprint will run or not. If it is running, then it is fine. If it is not, so we have to create that. So we have downloaded. So we just right click and then we'll go to Wins and then extract it. So we have this, double click on top of it. We have the step model and inside that Allegro. So we will be having the footprint batch file. So you can double click the batch file. So if it is not running, we can create, or otherwise we will find the other way to run this particular file. So we'll go to snap EDA. So we don't have the preview, but at least we will try to download. Okay, only the step model we have. So okay, we'll go to the Snap Magic website. We have the component part number. We will look for the symbol and footprint. Hope we have the footprint. Yes, we have the footprint, but we don't have. And also 3D we can check. Yeah, we also have the 3D. So 3D we have already downloaded. This is the footprint. You can click on the download footprint option. So directly it will download it. So the footprints were not verified. So I just click on download anyway. And it will ask you to take what software you need. So I will choose OrCAD and Allegro. So that's it. So it will download into your download folders. Go to the download folders and check it whether you have the drawing file or not. I'll just unzip this. So open the folder, and inside the folder you can see the drawing files. So you have also see the PSM files and the pad files. So these are the footprints for that particular register, and also you have the step file, that is 3D file. Okay, fine, then we will use this. I will go to the editor and then open that particular footprint. So open, save this. So go to the download section. So inside the download we have the register, that drawing file we have. Click open the drawing file. So yes, and this is what the footprint which is created by our downloaded footprint. So we'll just click on file and save as. I will make it, I'll put it inside our footprint location. So we'll go to the footprint. So inside the footprint, so I'll just type it. This is for register 1. I'll give the name R1, or you can give the same name also. I just type it R1 just for my reference purpose. PSM is also created using R1. So before going that, we will attach it. Attach the 3D also. Go to step map, and inside that we have R1. We will see whether we have R1. This R1 step model we have. So zoom in and then overlay. So that component is very small. The R1 is very small. So we'll go with the bottom view and check it. Yeah, so footprint is bigger, but 3D model is smaller here. We'll go to top front, top left. The 3D model is small one and footprint is very big in size. So I will download the footprint. So we have already have the footprint. So we'll go to the download location. So we have the step model inside this. I hope this step model will work for that. So I will take R1 and write this as R1 space 1, and we will put this inside the footprint location. Inside the project location, inside the footprint, inside the step model, we'll just paste it. R11 we will try and then check it out. So we'll close it and reopen it for refreshing. You just go to step model and we will look for R1-1. So we have R1-1. This is also looks similar. We will see with a bottom view and check it. Okay, this size is also different, so we need to use different footprint to get into this. Okay, so now you understood how to download it from the internet and how to use it into your PCB footprint. So we'll also download some other footprints. So we'll go to the data sheet, or so we have this component, that is voltage regulator, and then go to snap EDA and we'll search for that component. So select here and search for the component, As soon as you search this particular component, make sure you have selected the same component inside the filter. So if you don't find the 3D, see here we are not finding any 3D. The first one is datasheet, second one is symbol, third one is footprint, and the fourth one is 3D, which is not available. We will check the same inside the digit keys, which we have taken it from the digit key only, and then press enter. Wait for this. Now we have the document media. There is an EDA file, but we don't find any CAD model or footprints for this. So here we have the footprint. Just open it in the Snap EDA. If you can download it, we can download it. We don't find the symbol, but yes, we have the footprint. Go to 3D model. We don't find the 3D model. We have already downloaded from the DZ keys. So click on that, select the software, and that's it. You have the footprint downloaded to this particular. So go to the download location, right click and unzip. TO92 is opened. Now we have the pads, drawing, and PSM. So we'll open the drawing. So go to file, open, and then go to the downloads. So 3092 drawing file, will open it. So this is for the footprint we were looking for. So zoom in. So here is the footprint. So we just delete that unwanted symbol. Okay, fine. So this is the minimum requirement, which is 3 solder pads and a silk screen. We have assembly is not there. If you want, you can create the assembly on your own. We will save this, save as. You can do it and put it inside the project location. So inside the footprint, so I would say this is U1. So this is for U1, and press save. That's it. This is all about how to download footprints and use it to your particular circuits. Okay, some of them I have recreated the footprint, and some of them I have taken it from the internet. I downloaded the symbol footprint as well as 3D step model. So I will show you all the component which I have created and downloaded. So we'll go to file, open in the PCB editor, and go to the location which is desktop project 1, and inside the footprint. So go to the file type, which is all. Instead of board, I'll just click on file type all. We'll see the first one, which is C1, that is C1.drawing file. I will choose a DRA file, that is drawing file. So that capacitor one I will just choose, click open. Now you can see this is the footprint, and if you want to see the 3D model, I'll just click on the 3D canvas, and you can see that C1 component, which is around 100 microfarad, and this is the 3D component. We can go to view option, and you can come on the front, and you can see there is 1 mm gap from the PCB. So you can even keep it 0 also. So this is the right 3D which we got it. And then next we will go to the second one, which is C2, that is SMT component, which we have intentionally used SMT to understand how to create SMT footprint. Click on the 3D. Now this is what the 3D which we have created and downloaded 3D step model and attach it to the footprint. So the next one is okay, connector 2, which is header pin, 2-pin connector, and also we attach it the footprint. We'll go to 3D canvas and check the 3D map. So this is how it looks like. Once we switch to PCB, then it looks good enough. Then we'll go to the next component, which is diode 1, this is D1. Open it. It is a through hole component. So, and we'll go to the 3D, and this is what the diode is, and this yellow mark on the diode is the cathode mark of that component. So the next thing is We will open. I have downloaded this. Instead of creating, I have downloaded this particular 3D as well as footprint also. So we'll go to D2, so which is an LED component. So I have created this LED component manually, and we'll go to 3D. So 3D I downloaded and I attached it to the footprint. So the next component is, we'll go to file, open, and that is a register one which I have created and downloaded the 3D. So go to 3D canvas and you can see this is what the register which we downloaded 3D package, and that is step model, and attached to the footprint. The next one is, the last one is the U1, that is regulator. I have downloaded the footprint as well as the 3D model. So earlier whatever I have shown you, I just cancelled that because I didn't get the exact 3D model of that. So I just selected the different one for your understanding purpose, and this is what the 3D looks like, that is through hole voltage regulator. So that's it. We have completed all of this particular schematic. So we have added for each component. For J1 J2 we added adder component. For D1 we added diode, capacitor, one through hole, one SMD, voltage regulator I just shown you, the resistor which is through hole, and LED which is in a red color. So all component has now got the footprint as well as 3D step model. So we will go to the DSN file, select the DSN file, and then right click, go to edit object properties. So you can see that, so we have a footprint location here. There is a footprint location, PCB part reference and footprint. So we need to add the footprints here. So footprint name we need to add. So this is called attaching or adding footprints to symbols. So this is the procedure, but what we need to add to the electrical, that is for capacitor C1 we need to add the PSM file here. So that is what the package symbol module PSM file for all the components. So once we finish that, that means now we are giving the 2D and 3D touch to your schematic. So we should go to our project 1 and open the footprint, and check it out, the PSM files. I will just click on the type, so it will arrange on an alphabetical order. So all the drawing files, we don't want drawing files, we need the PSM files. So come to the PSM file here. Now you can see the name of the PSM of C1 is C1.psm. So I will only copy C1 and paste it inside the edit object properties footprint. Don't add PSM. So what I will do, I will only add C1. I'll just copy from the PSM file. I'll just copy the C1.psm. I don't copy .psm, just copy C1. I will put the PCB footprint name here. So if you keep something else, footprint name as something else, you just copy that footprint name, just neglect the .psm and put only the footprint name. For C1, that is C1 is the name, and we'll go to second one is, that is C2. I'll just copy C2, the name of this package, and put it here on the C2. Now next one is D1. So we will go to the D1. So here is the D1, just copy this, select this, copy, and go to the schematic, and the D1 I'm going to paste it here. So the D2 also we will take it from the schematic location, which is, sorry, in footprint location, take the D2 and then we will add it to the schematic. So paste it. Next one is, so that is J1 and J2, which is J1 and J2 is connector 2. So just copy this connector 2.psm, copy that. As it pressed Ctrl C and you paste it for J1 as well as J2, for both are same. Now R1 we will also attach the footprint for R1, which is R1.psm. Copy this and paste it to the edit object property, and then U1. So we'll see what name we have given to U1. So for u1 also we kept the name as u1.psm. So for our reference, for easy reference, I just named like this. So you can name according to your requirement. So now in the properties column, so each and every properties are added properly. Now you can see the data sheets, we can see the descriptions, and you can go here and check out the reference, and PCB footprint column is also updated. Price is also updated, and final we have the value as well as vendor name also. So everything is updated. Now we just apply this and right click, save the edit object property. So now each and every component has got its own footprint as well as 3D step model attached to it. So we will save this particular project and then we will run the DRC again. So we'll go to PCB, run the DRC, that is design rule check. At this time, at this point of time, I will run both electrical. In electrical I chose all, and then we will also run the physical rules. I will select the physical rules and I will select all components physical rule. So it will check power pin visibility, missing or illegal pin footprint property. So you can read out this. So it will check all this, and also if you want any reports, you can select the reports also, and the physical DRC reports also. If you want, you can select the physical DRC report also. Apply and then click on the run and wait for the output folder. So I hope there is no errors and warnings. We'll go to output folder. Here is an output folder. We have created, updated the fresh new DRC. Double click on the DRC and you can see this is all electrical rules, checking electrical rules. Single net node, no issues, no warning, no errors, no questions like connected bus, off page, nothing is, only we don't have any errors, warnings and questions. We have some reports. It is reporting the global net, that is ground, and it has got some net names. And physical, you can see we don't find any issues with physical also. So physical, it will check the pin properties, it will check the number of pins present in the component and number of pads present in the footprint. If any footprints are missing, those kind of things it will check. If you have any issues or any warnings and any errors, it will show under the physical rule. So physical rule check. So we don't have any kind of errors as of now. That's it. Then close this. So we have done the DRC. The next step is we need to switch to the PCB. So before switching PCB, we need to create the board file, and then to that board file we are going to update the or export the this particular schematic. Now we will see how to switch to the PCB. So before switching to PCB from the schematic, you can write that the topic name is switching to schematic, switching schematic to board design. I'll write it switching to board design. So here to switch to the board design, first we need to create the board file, and to that board we will create the board shapes, and then we will switch from the schematic to board design. So the procedure I'm going to explain you. So right now what we did is we have created the schematic. So here I'll show you the things what we have done till now. So we have created the schematic. So inside the schematic we have also created a folder called footprints. So we have created the folder called footprints. Inside the footprint folder we have all the components or footprints of this particular project. So inside this footprint folder we have all the footprints of these symbols. For example, we have that resistor and some capacitor as a circuit. That's an example. This is a schematic. Okay, so this is, for example, it is R1, this is C1. So we have the schematic and we have done all the required things in the schematic, and then we created the footprint. So we have also created the BOM. So we have also created the datasheet folder and many folders we have. The important folder here is the footprints. Inside the footprint we have the footprint for R1, and also we have the footprint from C1. This is an example. So we have all the footprints, and all the footprints are attached with the 3D model also. so we just skip that part. Okay, so we have many other folders also. Along with that, we have footprint folder, which is very important, and we attached these footprints with this particular symbol. So we have attached the footprint. So here for this R1 we will be having .psm file, so we attached the psm file. For C1 also we attached the psm, that is package symbol module file, that is psm.psm. so we have given the link to the footprint folder. So that's just we have taken the same name whichever is mentioned in the psm, and that this particular schematic or board design will look for the psm inside the footprint location only. So we have created the footprint and we attached it to the symbols. Our next target is, so we need to create the board file first. So we need to create the board. So this is the PCB board, that is printed circuit board. We will create the board file. So inside the board file we will create the board shape. For example, if we have a board shape like this, so we will create the board shape. So inside the board shape we will import the netlist. So we will create the netlist. So one more folder called the netlist. So inside the netlist we will have the wiring informations. So we will also have the wiring informations. So both we are going to import here. So here what we do, we export the netlist, and here we assign the footprints. So now here we will give the footprint link, just like we have given it to the schematic. We also give the footprint link to the board. So this is your board dot brd. So this is your dot brd file, that is board file. So then next we will import the netlist. So as soon as we give the link of the footprint, so we will get the footprints here, like register. This is a, okay, this is one footprint, and this is another footprint. So this is a register footprint, and that is capacitor footprints. So this is just like an R1, this is just like a C1. So if you want the connectivity, so you can get the connectivity once you import the netlist, we will get the connectivity. So this way you will get the connectivity. So the schematic, when you switch to the PCB, it looks like this way. So before switching, what you need to make is, we have created the footprint location and we saved all the footprint location, and we have attached the footprint to schematic. The next step is we need to export the netlist file and create a folder under the netlist file, and then we will create the board file. Inside the board file we will create the shape of the board, and then we will import the netlist from the netlist folder, and then we will get all the connections. So this is what we are going to do it. So this entire procedure is called switching from schematic to board design. So here one very important thing is pin to pad mapping is very important topic. So the pit is pin to pad mapping. That means if the symbol has two pins, so this is an electrical symbol which is there inside the schematic. If this is having two pins at 1 and 2, the footprint of register should have a two pads. So that is pad 1 and pad 2. So that means the pins are mapping with the pad. So the pin 1 will map with the pad 1 and pin 2 will map with the pad 2. So in case if you have a 2 and 3, so here of course the one pin is missing and third pin is extra, you will get an error. So avoid that. Make sure before switching to PCB, make sure all the components will have the same pins and pads in their footprint and symbols are mapping or not. So this is the whole procedure to switch from the schematic to board design. So what we need to do is, so we have the folder called board. So we have created under the project, we have created a board folder. Inside this board folder we will create the PCB board first. So go to editor, so go to file, new, and we'll go to the location where we want to save the board file. So we'll go to board, open the board folder, and then here we'll type the all, and we'll give the board name. I'll give the board name as just like schematic. I say it is power supply. I just give it to power supply. That name itself, same name I will give. And here the drawing type, instead of package symbol, we should use the drawing type, that is board. So I will use the board as a package, as a drawing type. So I'll select the board. So now, so it will show you that you will create a board file called power supply.brd. So under the board folder, so then click OK. So now we got the board file is created. You can see here that is power supply.brd file is created inside the board folder. So that is what we were looking for. We just save this and check inside the locations. Go to the project 1 location inside the board file. So we have the PCB power supply.brd. So that is what our board file. So we have everything now inside the board. We have a PCB board. Inside the datasheet we have all the datasheet. Inside the document we have document related things. Inside the footprint we have all the footprint along with the step model also. And Gerber we need to create, that is the final step. Schematic we have, and then symbols also we have created. So now we are working with a board. We have created the board file already. Now we will continue with the board file. So as soon as you come from the PCB editor, you have to do the default settings. So we'll go to setup, design parameter, all on, the enhancement mode, all enhancements mode will make it on, and then click apply. So go to design. Here it is in millimeter. I'll just leave it and I'll select it as A4 sheet, and here that's enough. That's click OK and then click OK. So we will also assign this footprint path. Make sure your pad path should be the footprint path. I'll delete and then click OK. It should not be a board file, it is a footprint location. So this is what the footprint location is. Select the footprint location, click OK. Similarly, pad PSM path, we will delete that and we will select that PSM is also the footprint location, because now I am assigning the board the footprint location where it is where it takes the footprint from that particular location. Apply. OK. So I'll zoom in. You can on the grids. Okay, so this is what the board design file. I'll just reduce the grids to 1 mm, so that is enough, I believe. So if you have any other, you can choose that particular grid. Okay, so now I will draw. The first procedure is we need to draw the board shape. So we have the board file. The first procedure is we need to create the board shape. So how to create manually I will show you, and also I will show you how to import, how to export and import. So how to create a board shape? Here we are working on board design, so the class must be board geometry. Remember this, while creating footprint it was package geometry, now it is board geometry. And then subclass will be either outline or design outline. So we will be having two things, one is outline or second one is design outline. So these are the things we need to consider, and then create the board shape. So I will create a board shape around 50 by 50 mm into 50 mm. So just for an example I will create, then we will import all the parts from the schematic and then check it out whether all the components are placing it or not. So we will go to add and then click on the line and go to package geometry and change it to board geometry on the class. So now the subclass is outline. So I'll just keep it 90° and I'll keep it 0.1 just for visible width, and then I will go for x00, enter. Now from here I will type 50 by 50, that is from the previous clicks ix 50 space 50 and then press enter and bring it back to x00. Once you bring it back to x00, it will attach it to your origin. So this is the board shape. If you go to 3D canvas and see the board shape, this is 50 by 50 board shape. So now what we need to do is, so I will convert this board outline to design outline. I will convert this board outline to design outline to get the proper design outline. So before that, I will make one more step. If you want you can do the chamfer. So otherwise, if you want, you can do the fillet option. So the two things, chamfer means 45-degree, fillet means an arc. So I'll make the top two are fillet and bottom we will make it chamfer. So we'll take manufacturer drafting, and inside the drafting we have the fillet option. So I will take like 5 mm diameter. I'll put in the corner and check it out. So this is on the corner, we have the fillet, and also I'll do this corner also. So all three corners I have done fillet, and one corner I'll make it chamfer. So that is 6 mm chamfer, we do it. So click on this corner, we will get the 6 mm chamfer. So this is the board shape. Now I will convert this board shape into design outline. So go to edit to convert, click on the change. So go to board geometry and you convert it back to design outline. So select this, click on this particular. If you don't get it, so what we need to do is we just have to take the edit Z copy shape, and here we'll take board geometry and then design outline, and we'll just click on the object and right click, done. So you can see here, so one thing is one copies the mode. That means I have copied the design outline. So just move with respect to body center, or some just like normal move you can do. You can see now one more symbol is created here, and this is the board design outline. So I just want to remove this. Yeah, otherwise if you want you can keep it, that is not so no problem. So both we have that. Now you can go to 3D and cross check. So this is what your board looks like. All four corners you will be having the arc or the fillet option, and at this particular corner we have 45-degree. So now we will add some restrictions. The first restriction will be like package keep in. The first restriction is the package keep in, and the second restriction is route, sorry, that is route keep in. The package keep in says that if I exceed that area, for example, if I have this much package keep in on the board, if I exceed my component placement outside the board, it will start giving the errors. So I wanted to keep this particular package inside the package keep in. Similarly, routing also, if you want to do some routing must be inside this particular routing area. If it is goes beyond, and it will give error. So according to the standard, at least 1 mm inside we should give this particular restriction. So to do that, I'll go to edit Z copy, and we'll click on package keep in. The first option is package keep in, and where I want it in all layer, that is in top also, in bottom also we need it. So in top, bottom, that is package keep in all, and we'll take the contract means it is inside. Wherever I click, I'll click on this outline. So this outline inside we will get one more shape that is having package keep in restriction. So I'll just contract it to 1 mm inside, which is the standard. Now you can see the blue color mark. Inside this only we need to keep any component. If you keep outside, so that particular thing will start giving the errors. Similarly, we'll give one more restriction, edit Z copy. I'll put the route keep in. So select the route keep in. I want to select all for route keep in also, and contract 1 mm from the board edge. Right click, done. So both are now placed. Restrictions are placed 1 mm inside the board geometry. So now you go and check the 3D canvas. It looks like this. We can't see the restrictions. Yes. So the next thing is we need to import the circuit here. So to import the circuit, we have to create the circuit export. Just right click here, click on the empty, click OK. And what we need to do is we go to schematic. First here we need to export the file. So we'll go to DSN file, go to tools and create netlist. I will export the netlist. So click on the netlist and Allegro. It will create a folder called Allegro. I'll just leave it as it is. Click on OK. Then click say yes. So it will create a folder inside the schematic. We'll go to the project one. So inside the schematic, it will create a folder called Allegro. Inside the Allegro, we have the netlist file. So now the netlist is exported to the particular folder called Allegro. Now we go to board design and we will import the logic or the footprints. Now you can see I will just go to right click on the black screen, go to application mode and general edit. So as soon as you have the general edit, we don't have any options here. So now if we are placing the component from the footprint folder. So once you do the netlist import, you will get all the connections along with the footprint access. So to see that, I need to change the application mode to placement mode. So click on placement mode. Now you can see inside this panel we don't have any options for component placement or placement edit. So as soon as we log in, as soon as we import all the components or logic, we will get the components. So we'll go to file here, we'll go to import and then netlist or logic. So we need to tell from which software we have created the schematic. So we have captured using the capture option. Click OK. And where are your netlist files? So we'll just locate the netlist file which is there inside the schematic and Allegro folder. Just go to here and go to the schematic, then go to inside the Allegro and click on choose. So now I will import. So as soon as you import, so all components you can witness on the right side. So in the right side panel we can see all components are ready to move in. So if you have a general edit, right click here, application mode, general edit, we don't find those components. So right click, application mode, placement edit, we find the components or footprints on the right side for proper placement. So this is what we created. So this is your board file and we have got some component. Now we will start placing the components. I will select all. If you select all, you can place components one by one inside. First C1 and then C2 and then D1 and then D2, J1, J2, R1, U1. So this is how you place all the component. Otherwise you can also do the other options. I'll just remove, like right click, select all and right click, unplace component. It will come back here. So one by one also you can take. You can take here like C1, like C2, one by one also you can take it. This way we can do component placement from the left side panels. So I just right click here and place the component. So but we should not place this way, we should place according to your schematic. That is the very important thing or important role. So we will study the circuit, that how the schematic flow, and according to schematic flow, so we will place the component. But before place the component, we will do some editing in the sense we will change this board shape. We don't want to use the same shape. I just show you how to get the components. If you put only that package key pin and route key pin only, you will get the component import options. Otherwise you won't get it. So if I place it like this, you can see the component error, you will get it. So to avoid that, you need to place it inside, then the error will go off. So this is why we kept the package key pin. Okay, fine. So now what is our next motive is we need to check the circuit flow, and according to the circuit we will place the component. Before doing that, we will change the shape like we will do some rectangular shape PCB, and we will keep the mounting holes on all four corners. All four corners will keep the mounting hole, and then later we will bring this component inside this PCB board. So this is just for an example. I showed you how to create a board shape and how to create the restrictions and how to add the components. Okay, so now we will delete this and we will create 60 by 30 board outline. So we'll go to add line, so go to board geometry, that is outline 90 degree, and just I'll keep it 0.1, and we will put it x00, and ix I'll keep it around 60, and iy 30. 60 by 30, then x00. So right click and done. So now you can see this is 60 by 30. So we will just do the copy, z copy shape, and we will take board geometry, design outline, but before that we will create a drafting, that is fillet. I'll keep it around 6 and check it out at this particular corner and another corner. Right click down. So I hope this is fine. If you want this side also, we can choose. I will take drafting and then fillet with a 6 mm this side as well as the other side. So right click done. We do now edit, z copy shape, design outline, and we'll just click exactly on top of the outline. So we'll go to 3D and check this is what the PCB looks like now. Okay, so we will add the restrictions that we discussed earlier. About the restrictions, we should go to edit and z copy shape. So first thing is package keeping, and all. I don't want, okay, I want it all on top as well as bottom, and contract it to 1 mm inside, and then click on the design outline or outline. So now we got 1 mm restrictions. If you exceed that 1 mm restrictions, you will start starts giving the errors. Z copy shape again for route keeping. So go to route keeping option, all, and contract it to 1 mm. I'll just select this area, right click, done. So both are overlapped now. That is the reason we can see this way. So you can click on the move and check. There are two things we have. One is route keeping, another one is package keeping. So right click, oops, and cancel it. So it will be on top of the package keeping, and then route keeping are overlapped. So this is how two restrictions we have added. So this is the board outline. Now we will save this file, and we will create a mounting hole on all four corners. I will create a 3 mm. It is also called as non-plated through hole, that is 3 mm non-plated through hole for screw purpose. So how to create? We just go to editor. You can create a mechanical hole, select the mechanical hole and go to file here, new. So inside the footprint location only we need to create, that is I would say 3 mm drill, that is NPTH. So 3 mm NPTH, instead of through pin we choose mechanical hole, click OK, and we'll choose millimeters. Click on the drill, circle drill, this is 3 mm drill, and we no need to have any mask. So if you start saving it, so this will not save because we need to add mask that at least 0. So design layer, we will add the pad at least 0.1. We will add the pad on top to bottom because it is a pad stack editor. It required a pads. Go to file and then click on the save, close with warning. So we are getting some errors. We will see what is the error. Patch decorator. Pad size is 0. Solder mask pad size is 0 and still isn't okay. So solder mask pad size it is asking. We will make it null here, none, and then we'll go file and save it. So close. Now it got saved. 3mm is saved. So go to PCB editor now. PCB editor. So we need to create a footprint like thing. So for NPTH also. So go to file, new. We should say browse the location which is in the desktop. Inside the footprint folder we need to create, that is 3mm NPTH. So we should choose this as mechanical symbol, or else you can also choose this as a package symbol. So click OK. So we go to setup, design parameter. So we will design, enable all the enhancement display modes. Click apply. Go to design. I'll change it to millimeters. I'll just say take it A4 sheet. I just make it -100 and -100 for getting the origin. Zoom it. So we'll call the pins now layout pins and look for the pad stack, so which is 3mm, and I'll put it on the origin. This is 3mm. Right click, done. So this is a small solder pad. On top of it we will have the drill, so the solder pad will be drilled away. So we need to draw something like assembly as well as silk screen to this, just to understand this is also a proper board related component. So now what we need to do is I'll just change the grids to 0.5, 0.5, 0.5 and 0.5. Click OK. So on the grids, okay, so we will draw the assembly first. It is circular assembly. So board geometry. So we don't find assembly related things in the inside the board, so we will create this as a package geometry and assembly. 0.127, that is 5 mils. We will draw it manually. Just bring it exactly on the edge of the drill. So this is what the assembly says. Assembly says the outline or the drill size, whatever the drill size it is. So outside to this we will add the silk screen, just to understand. On the PCB wherever you have the hole, outside the hole we will draw little bit outside, that is the silk screen, just to set, that's to understand this area is for drill. So we'll take circle, add circle and silk screen top, which will print on the PCB, that is 0.1524 width. We will draw 0.5 outside the assembly, that we will keep it 0.5 outside the assembly. So here one more thing, we need restrictions here. Inside the drill, we are not expecting any components or parts. That means we should keep out option we can use. We are also not expecting routing inside the drill. So inside the drill we are not expecting parts or package. Inside the drill we are not expecting routing. So the restrictions what we need to do is, outside the drill you keep this package, outside the drill we keep the routing. So that is why it is called route keep out restriction, as well as package keep out restrictions. So the two restrictions we will draw, I will overlap it on top of the silk screen only. I don't want to waste much more space. This much space is enough. 0.5 mm space is more than enough. So any component or any other routing should not come inside this area. So we'll keep Z copy shape on top of the silk screen. So go to edit, Z copy shape. So we will take package keep out and then route keep out. Route keep out either on top and bottom, but we want it on top and bottom and all internal layers also, because there is a drill. I'll keep it all. This drill goes throughout the complete PCB. So we will expand, or you can contract. I'll just click on silk screen. So this area, now in this area no other component will allowed. Inside this area no routing is allowed. That is what our main motive is. If you want, you can extend it, but don't waste that space. So the next restriction is edit z copy shape, that is keep out package keep out. Click on top of this, right click, and then done. So this is the mechanical symbol which we have created. Then click on the save button. So now DFA bond top is not required, just these two is more than enough. Just click on save. As soon as you save, so you can see here there is a drawing file is created. Along with that we have the BSM file also. BSM, that refers to board's symbol model. This mechanical design is belongs to the PCB board. That's why it is board symbol module. So just close this and we'll open our PCB. So now we will bring that 3mm non-pillated through hole here. So we don't find that inside this because these are all the components which is having the reference designator, that is C1, R1, D1, D2. So now we need to look for the component or the part which is mechanical. So to do that, we'll go to place and we choose manual option, place, and choose manual. Inside the manual we'll go to advanced settings first and click on the library. So advanced settings, click library, and then come back to placement list. Now here inside the placement list we'll click on top of this and select mechanical symbol. I'll choose the mechanical symbol here. Now you can see 3mm and PTH is located. So what we need to do here is we just have to select one time, bring it inside, place it. Select second time, bring it inside, place it. Select third time, bring it inside, place it. I want fourth corner also, place it. Once you are done, just right click, you choose done. So now you got 4 mechanical drills. Now you click on the 3D and check it out. So these are the 4 drills we have on top of the PCB. So we will arrange it properly. So what we need to do is click on move, select this. So it is, if it is not body center, make sure point to body center, click on this, so it will come to body center. So we'll bring it here, don't go beyond this, we'll keep it at this point. So right click, done. We will see the position now. Go to I, so click on this. The position is 4 by 4, that means 4mm from the origin, 4mm from the origin. So we will keep here also 4mm inside. So now we know, this is just for our planning, I'm telling you. So this drill placement, the coordinates will be given to you. So according to the coordinates you can keep it. So I will give you the coordinates here. So the first one is with respect to origin, it is 4mm on y-axis, 4mm on x-axis. So this is your first coordinate. So here the next coordinate is x-axis, it is 760 minus 4, that is 56, and y-axis is 4 I'll give. So we'll take the move option, click on the second one. I'll go to here, just press X space, x-axis is 54, y-axis is 4, press enter. So it is very near to this, so I hope this length will be different. So till here to here it is around 60, so which is 56 it should be. Click on move, click here, and we'll make it ix only, not ix, x, that is 54, 56, and y will be 4, enter. So this is exactly on the second corner. From here it is 4mm inside. Similarly we will take the third one. The third one I want this here, which is x-axis 60, 56, and y-axis which is 30, that is 26. So x will be 56 and y is 26. Then press enter. Sorry, I by mistakenly I have written 65 here. X 56 and 26, enter. So similarly the last one we will keep it here, that is x-axis 4, that is x-axis 4, y-axis 26, then press enter. Right click, done. Now we have the mechanical drill on all four corners. So this is what we have expected. All four corners we were expecting the 3 mm non-plated through, that is screw hole. So now we'll save this file and check inside the 3D. Go to 3D and now you can see in all four corners we will be having mechanical drills. So, okay, so now we will work on component placement. So this is also called as part placement. So placement, we can do it on the two sides. One is top side placement and another one is bottom side placement. So here all SMD components, all through hole components, that is PTH component, that is plated through hole components, I'll keep it on top, and I'll keep SMT components on bottom side. So because I wanted to only route on the bottom side, I wanted to only route on the bottom, and on top side I don't want to route it. That's the reason I'll keep the SMT components on bottom side, so that I'll get all the access on the bottom. I'll show you in the cross section. So if this is your PCB, in the cross section, for example, I have a component. So if I have a component on top side which is through hole component, it's top side, the second through hole is also on the top side. But if I have an SMD which is on the bottom side, for example, this is an SMD component which is having access in the bottom layer. So now what we need to do is, I skip the routing on top, I only do the routing on the bottom layer, so that I will get access to the all components, because I'll keep SMT on the bottom, but through hole I will take routing on the bottom itself, and on the top side I will keep completely a ground connection. So in the bottom side, I do the normal routing, and on the top I will keep the common ground connections. So this is my plan for component placement and for routing also. So now we will work on component placement. So before doing that, I just wanted to fix these. Right click on this my NPTH and click on the fix, so that whenever if you by mistake, if you take the move option, even if you slide it, so it will not move. So we do that, fix it, so it will not move anywhere if you have by mistakenly selected the move option or rotate option or copy option. So it will not move. So if you see move, so you will not be able to move this. So to avoid those kind of unwanted errors, we will make it fix those components. Okay, so now our first motive is, I'll keep all the through hole components on bottom side, and SMT I will prefer in through hole on top side, and SMT I will put it on the bottom side. So to put it on the bottom side, we just have to mirror the components. So before that, we'll go to the schematic and understand. The first is the J1, which is on the left side, which is an input, and J2 is an output. So I'll prefer keeping the component J1 and J2 on one side and other side. I will check the J1 and J2. I'll keep the J1 on the right side, left side, and J2 on the right side. So right click and you can do done. So just go to 3D and check it, and accordingly you can check and do the other placement. So now we will see some tools here. Click on the move option. Here we have that move icon to move the component. Select and click on the component, and you can just not drag it, just move the mouse pointer, it will move. If you want to rotate, right click here and you can even option to rotate, but make sure now we are already in a move command. So now we are doing the right click and rotate, so you will get one small thread. So using that 90-degree you can rotate it. So rotate it this way. If you want to change the angle, you have an angle option here. Instead of 90 you can take 45 degree, whatever degree you want you can take it. Make sure the type is incremental so that we can rotate the component properly. So I will just click once your rotation is done, click it. Now it will come back to move command, and I will place it somewhere here at the center of the two NPTH. So right click and then done. So if you do right click and done, that operation is successfully done. So we will reduce this grids to the smallest, that is I will make it 0.1, that is 4 mils. So we can do the smooth design. So click on move, click on this component from here to here. We will place this component. That is an input component, and you can see the 3D model. So how it looks like now, properly it is sitting on the input side, and this is the output side. We will change it now. So just go to move option and click on the component, right click here, rotate. So we'll get the rotation option, so we'll rotate it, and I'll keep that somewhere. Okay, so bottom side we will keep it little bit down, so that here we'll put some indicators. So right click and done. So now we got two components for the input and output side. Okay, we'll try to keep the LEDs here. Just go to LED, that is D2, select the D2, and I will place the D2 here, right click and then done. So go to 3D and check it out. So we have done that input side and output side and indicator, output indicator. So if you want to rotate, you can rotate it, that's not a problem. So we just got the output along with the indicator whether your component is giving the proper output or not. So you can also rotate this component using the spin option. Go to edit and click on the spin and click on the component. See what happens, this component will not move, but it will rotate on the existing place. So click, right click and then done. Click on the 3D now. So now it looks like this way in the PCB. Once you manufacture and assemble, this is how the PCB looks like. Okay, so now we will bring the next component. We have done the fix. I will just make it fixed because it is input and output. We'll make it fixed. So we'll make it fixed so that we don't want to change it. These are the permanent placement setup. So click it here. So we don't find any issues here, any warnings. So here you can see this connection which is coming from the schematic. We call it as RADs. RAD shows the connections according to your schematic. That means the J1 the pin is connected to J2's, this pin, and J2's and D2's. So these are all I think these are all ground related pins. Okay, so next we will bring, I will go to the schematic and check it out. So D1 I'll keep it near to the J1 so that I'll get the connection. So D1 and J1 and C1 also. So we'll try to keep D1 so near to this. Later we will arrange, and then C1 near to the D1. Similarly, we have U1 which is a regulator, and then we have the C2. After regulator we'll get the C2, and then R1 before the LED. So these are the components we were taking it from the according to the schematic placement. Okay, fine. Now we will do some arrangement here. So this one I will rotate and I'll get the access connection from here. Okay, once you've done that, we will have a capacitor which is placed. I'll make sure the capacitor and zoom it. Don't worry about the ground pins. So not to worry about the ground pins, what we need to make is we put the plane on the top. We will go to shape here and rectangular. So go to H, and on the top side I will prefer the net which is ground. Click OK and the draw. On the top we will get the green screen. That means all ground connections you observe, that is all shorted. So now we will get the only important nets which we need to connect it to routing section. So this is 24 VDC, that is 24 VDC after the capacitance. Okay, so we can keep this. If you keep near to that component, example for just click on move, click on the component. If you keep near to the component, it will show the connection to the U1. So what we need to do is, if you keep near to this, we will get the connection from the other side. So I'll keep in front of this. That's fine. We can take the connection routing from here. So we will bring near to, I just wanted to hide, click move, bring it near to this component. Okay, so done. So as we discussed earlier, we will keep that SMT to bottom side. So what I'm going to do is right click here and then you click on the mirror. So right click on this component, click on the mirror, so it will go to bottom side. So once it is go to bottom side, so we can go to 3D and check it. On top side we don't find that particular component. Here we don't find that particular component. That component is on the bottom side. Go to view, go to camera. On the bottom you can see this particular component is placed on the bottom side. SMT, I just plan to place it on the bottom side, so we place it on the bottom side. Okay, similarly we will go to move option. So take LED, we just fix it, so we don't want to move that. So we'll place this resistor here and we do the routing on the bottom side. So right click, done. So that's all. We have done the placement, so we just click on the top. Okay, so once you've done the placement, just check in the 3D. If you want to make any changes, you can make it. That's more than enough, I think, for understanding purpose. So now what we need to do is we do some alignments, the placement alignments. Make sure whenever you do the placement and alignments, you have to select the placement edit. The application mode must be placement edit. Otherwise you can go to setup, go to application mode, and it should be placement edit, so that we can get all the components. So alignment is also similar. I'll just hide the top edge. Now what we need to do is these two components we will align it. If you want to hide the rats, we have an option to hide the rats in the display section. You can go to blank rat and click on the hide. Otherwise you have the option here, that is rat unrat all. So here we have unrats all and unrats on, rats all, unrat all. You can use that option also. So if you want to align these two components, so select those two components. According to which component you want to align, right click on that particular component. So I'll right click on it, I'll click on align component. Both components will get aligned now. Similarly, now I want to align these two according to this. Right click and align the component. So right click and then do the done. So this is, I want to align with this. Otherwise we will keep this component a little bit downside, so that we can align with respect to this register. So this is bottom, however we don't need to worry about that. So we will align these three components. Okay, and as well as we will align these two only, because this is in between we have. If you want to align these two, just select these two components, right click and align the component. So both components got aligned, and then you do right click and done. Similarly this also, right click, align components, right click, done. And here these two I will select. I don't want to leave that bottom side also. Right click here, the first component will take, and then select control and right click, align these two components. These two components got aligned. So if you want to move towards right side, you can move towards right side. Move with respect to this component, and we will move a little bit right side, then click OK. And I want to align this component with respect to this. Right click. You don't find align component because that component is fixed. I'll just make it unfixed and right click. You do align that component. Select this and this, right click, and you can do the alignment. Alignment we can't do because this is on top and one component is top and one component is bottom side. That is the reason we can't do the alignment. So we'll bring it up, mirror this, and we just align. Right click, align the component, right click, done, and just bring it downside. That's enough. So we'll bring it towards right side, we'll bring it up and right click here, align the components, right click, done, and right click, go back to downside. So this way we can do component alignment. We'll select both and move towards right side, right click, done, and we'll do the alignment here, right click, do the alignment, and right click, done. And once you select these two, right click, align accordingly, right click, done. Similarly, we'll make these two, right click, align accordingly, right click, done. And that's all. We have done all alignments. These two are already fixed, so we can't do that alignment. So now we go to 3D and cross check once, and before that you just save the code. Click on 3D. Now you can see it looks fine. The placement looks fine. Now we'll start the other operations. So now we will discuss about the routing. So before discussing about the routing, we will know what about constraint settings. That is constraint settings. So constraint manager we also call it as. So in the constraint settings, we were going to discuss about width, how to assign the width and what will be the width for particular voltage and particular current. Along with that, we also see the spacing. How do we assign the spacing and what will be the spacing for different voltage ranges? So to discuss the constraint settings, we must know what copper thickness we are using and what core thickness we are using. So based on that, we are going to calculate what will be the width as well as what will be the spacing. So I will give you the brief introduction about the constraint settings, where how to calculate the width of the trace track and how to calculate the spacing between the tracks and between the track and through hole, between the track and non-plated through hole, like between the track and the board edge. So we will calculate those things according to your copper thickness as well as according to the IPC standard. So and then how to apply that comes under the constraint settings. So now we'll go back and see, we have already discussed about the two layer stack ups, and also we have discussed about the copper thickness, how much the copper thickness we are using along with that core thickness. So for two layer, as we already know about, there will be a copper on top of the PCB as well as bottom side also we have the copper is foiled on the bottom layer of the PCB too. So the thickness we will discuss. So we already have know about the knowledge about the thickness. So we have the copper thicknesses like standard thicknesses of 0.5 ounce per square feet, 1 ounce per square feet, 2 ounce per square feet, as well as 3 and 3 plus also we are available. So but we have to check with the manufacturer about this. So we have the standard. So in other words, so we can also say that around 0.17 micrometer in thickness, and the second one is one that is 0.035 micrometer, and the third one is around that is 0.07 micrometer, and the fourth one is that is 3 ounce, which is around 0.1 micrometer. So we will discuss about this. So I will take around the second one, that is 0.035 micrometer, and let's assume that we have the current that is 1 amps is flowing inside your circuit. I'm just assuming that for this training purpose. So otherwise you have to check out how much current is flowing inside this particular circuit. Based on the current, we are going to calculate the trace width. So here I will choose 0.035, or you can also say this is 35 micrometer, or it is also 1 ounce. This is 1 oz, that is 1 ounce per square feet. So I'm going to use this one, and I assume that there is 1 amps of current is flowing inside this particular circuit. So but if you know exactly how much current is flowing, accordingly you just make your calculations. So I will set up this one. That means the first setup is the cross section. Inside the cross section, so I decided this is the first point is this is a two layer PCB. This is 2-layer PCB. So for the 2-layer PCB, if the copper thickness I'm going to assign is around 0.035 mm, or it is also called it as 35 micrometer. I'm going to assign this one. And the third is the core. So core I am going to take around 1.5 mm, just for an example. And then the copper, that is the current, sorry, not the copper, current I, that is, we will consider this as 1 amps. Just this is an example. So now based on these inputs, so we are going to calculate what will be the trace width. So what will be the trace width? We will calculate the trace width, and we will also calculate the trace spacing. Trace spacing. That's two things we will calculate, as well as we will apply it to the cross section. Okay, so now we will apply the cross section. As I told you, this is 2-layer PCB. I will take copper as 0.035 mm and core as 1.5 mm, and 1 amps is the current. Based on the current and thickness, we will calculate the trace width. Based on the voltage, we will calculate the trace spacing. So make sure that the thickness and the current, the thickness of the copper, the thickness in the copper, and current flowing inside the copper. Using these two inputs, we can calculate the trace width. So using the voltage flowing across your circuit, we are going to calculate the trace spacing. So this is all about the inputs. So we'll go to cross section, where first we will set up this as a 2-layer PCB. So we already set up this is a 2-layer PCB. By default, any PCB, it will be a 2-layer one. And then we will assign the core thicknesses. We need to refresh these settings, we need to update these settings, as well as core as well as copper. So to do that, I'll just go to the setups and click on the cross section to insert the cross section. So, or otherwise, before doing this, you just cross check, go to the visibility here. You can see there is, by default, there will be a 2-layer PCB, that is top as well as bottom, there is already by default. So now we are going to check it out. So go to setup and then the cross section. So we will apply this to the 2-layer PCB. So we already have, this is top layer PCB and this is bottom layer PCB. This is a cross section. So and here you can see, you can observe the top is a conductor, and in between we have the dielectric material, and bottom is also a conductor. So that is a 2-layer PCB. So one is copper, then core, and then the bottom is also copper. In between we have the dielectric, or we also call it as non-conductive material, that is FR4 material, and it is a core of the PCB. So here is the conductor, dielectric, and conductor. That layer function, this top is a conductive material, it conducts the electricity, and the second one is dielectric material, which is hazard in the nature, that used to support the component placement and soldering. The third one is also electrical connections. So here is the thickness, which is in millimeters. If you want to change it to mils, or if you want to change it to microns, or if you want to change it to inches, you just have to go to the setups and change it. For example, so if you go to the setups and go to design parameter here, inside the design you can change the units of this particular, and you can change it whichever unit you want. So I'll keep it in millimeters and I will apply that. So click OK, and we'll go to setups and cross section. So we already have the 2-layer PCBs already set up, and we will update the thickness. So the thickness will take the 0.035, that is such as 35 microns, and the second one is we will take it 1.5, that is FR4 material, and that is the third one, which is 0.035. So this is what the thicknesses we required. So I assume that there is a current 1 amps current. For the 1 amp current, that 0.035 is a good option. So or if you want to learn in detail, so check with the manufacturer about the layer stacker. So for for example, if you have a negligible current in milliamps or microamps, you can check with the manufacturer which copper thickness is good for that particular current. So they will suggest you some layer stacker. Based on that, you can choose it. So for this 2-layer setup, so I'm going to use copper thickness 0.035 and core thickness 1.5. I will use FR4C material. You can check the material list here. So there are so many FR4 or so many dielectric material are available. So and you can check out what is the advantages and disadvantages, cost and everything. So FR4 is the most widely used, and I will use the same thing also. For conduction is also same. So we are using copper is the best conductive material. Apart from the copper, we will have many things like aluminum, chromium, and we also have the gold, and we also have many metals we have. So copper is the best suited for PCB, so we prefer copper thickness, a copper foil for the conduction on the PCB. So this is my layer stack up. So as soon as I assign this copper, that is 0.035 or 35 micron, so core 1.5 and another one is 0.035, the bottom copper. So we just go here down and check it out, the total thickness of the PCB. The total thickness of the PCB is 1.57, which is, as we have already discussed about the layer stack up, 1.57 is ideal PCB for 2-layer. So that's it. This is all about applying the copper thickness, core thickness inside the cross section. Just click on apply on the bottom side here, click on apply and then click on OK. So that's it. Your layer stack up is already set up now. So to calculate the current, we will go to the calculator. So as I told you, so we have a different voltage ranges in this particular project. So we will take the current which is flowing 1 amps across this, and we also know that thickness of the copper is around 35 microns or 0.035 So based on this we can calculate the width. So based on this we can calculate the width. So we can calculate the width, trace width specifically. So to calculate the spacing, so we need a voltage input. So input will be the voltage. So how much voltage? Based on the voltage, so we can calculate the spacing. So for first thing we will calculate the trace width based on these two inputs. So I will show you the trace width calculator. I will also share the link to calculate this trace width calculator. So this is the first link, you can go through it. I will share the link in the description box. So that is for PCB.com trace width calculator. So I will also show you the example, that is the formula which is used to calculate the trace width in mils. So you can see the trace width calculation is here, and this is according to the IPC 2221 standard, both trace width calculation. So IPC 2221 standard, according to that we are going to calculate. So this is a formula. If you want to explore the formula, you can explore the formula, but I would suggest you just go through the calculator. We have the calculator here, so input you can give it here, and if you have any optional input for a temperature on the track, so you can input this. So based on that you will get internal layer result for internal layer as well as an external layer. So you can just ignore the formula, or if you want to learn and study the formula, so you have the formula here, you can study on your own. So I will use this calculator to calculate the trace width. So as of now I know I have 0.035 that is thickness. So this is also, otherwise we can call it as 35 micron, otherwise this is 1 ounce per square feet, 1 oz per square feet. Okay, so these anyone you can put it inside this particular thickness. So here it is, the first thing is it is ounce per square feet. So we are taking 1 ounce per square feet and 1 amps of current. So 1 amps of current, and you can come down here for external layer. Here the external layer is top and bottom. So here, so we have only two layer, that is top, and the second one is bottom layer. So these are called as external layers, and if you have any internal layer PCB, so that all comes under internal layer PCB. Now we are only using 2 layer, so we can take that as external layer. So if you have any internal layer routing, so you can choose the internal layer results. So here you can see that for our input, that is 1 ounce or 1 amps, so it minimum requirement is 11.8 mils, or if you want in millimeters, I will choose the millimeter. The 0.3 trace width is required. So this is how you need to calculate the trace width. So we will just change it. You can change it to the mils not, we will change it to mm's here. You can see mm, so it is not 1 mm, that board thickness is not 1 mm, it is 0.035 mm. Now you can see that is still 0.3 mm. So if you want to transfer the current of 1 amps on a thickness of 0.035, so you need a trace width as 0.3 mm. So what is thickness? If this is your PCB, so this will be the height of the PCB, or you can also say thickness of the copper. So width, this will be the width. So this is the width 0.3 mm, and this is the thickness of the copper. So if you want to put this much, so you can send it. So what if the current is double? If the current is double, of course the trace width will be doubled, or it will be increased. Similarly, if the current is less, 0.5, the trace width will be less. So this is how we calculate the trace width according to current requirement. For example, if I have 1 amps current and the thickness is 0.035, and you want the temperature, ambient temperature is the room temperature, which is nearly around 25 to 20 degrees Celsius, and the temperature rise. If I say temperature, if I want to increase the temperature, for example 20 degrees, it will be decreasing. So the less trace width, more heat. That is what it's showing. So more heat. So if you want to reduce the heat, so we need to have a more temperature. For example, if it is 10, yes, 0.3. If it is still 5 degrees Celsius, yes, you can use more copper. For example, so more copper, the copper will dissipate the heat, or the heat will be dispersed inside the copper. The more copper, the more will be dissipated inside the copper itself, because the copper melting point is 1080 degrees Celsius. That is the reason. So we use copper. It is 1080 degrees Celsius. If you heat the copper to 1080 degrees Celsius, the copper will become the liquid form. So other boiling point you can say. So if you increase the copper, that is 0.4, the expected is 0.3 mm on 10 degrees Celsius. If you decrease the, if you want 5 degrees Celsius, of course I need to increase the copper on the trace. So to increase the copper, that will be 0.457. So see, this way you can do the optional setups here. So see, we are calculating it for the ambient temperature, which is 25, which is like a room temperature. So if your product is working under high temperature, you can put the high temperature. Based on that, you can get the result. For example, if you are working on 50 degree, always if you are working on 50 degrees Celsius, yes, this is what the output is. So we want, if you want to maintain the temperature rise, the temperature rise is on the PCB, on the track. If you want to increase the temperatures to 25, of course it is less because of the ambient temperature. So that is why we just keep it default values. That ambient temperature is make it 25, and this will be, we will making it 10, and this is what the trace width is all about. So you have the optional inputs. So based on that, you can input and get the proper trace width. So this is all about how to calculate the trace width. And the next when we will discuss about how to calculate the trace spacing. Go to the trace spacing calculator, so which is also according to the IEEE standard, IPC standard. That is, there are two standards here, that is 2221. The first one is IPC 2221B, and the second one is IPC 9592. So we will use any one. For the training purpose, I am going to use 2221B. So here, whether it is AC or DC doesn't matter. So if you are if you know the voltage, for example, if you have around 240 volts, and I'm going to calculate it. Click on calculate. So I clicked on calculate. So according to the IPC, that is 2221B, for external it is 1.25 mm. So that means if you are transferring the voltage 240 volts on this particular track, so you have to maintain 1.25 on the right as well as 1.25 mm on the left side. So there should not be no routing and no spacing. There should not be no routing and no spacing, no other routing, no other component, and nothing. It should be just an air gap. So you have to maintain like this. So if it is an internal layer, it should be 0.2, that's very less, and if it is coated, that is 0.4. According to the old standard, that is IPC 9592, you can take it as 1.8 mm spacing on the right and left side of the trace or the track. So like if you have a 40 voltage, if you have the 40 voltage, I'll just click on the calculate. So according to the standard, that is I221 IPC 221B, the external layer top and bottom you can put 0.6. According to IPC standard 9592, it's 0.5. So this is how you calculate the trace spacing. So I'll leave the link in the description about the trace space calculation as well as trace width calculations. So this is all about trace spacing and trace width calculation. So now we are going to apply this inside the constraints. Okay, so now we are going to apply trace width in the constraint settings. So we should go to the setups here and go to the constraints and then constraint manager. So once the constraint manager is open, I'll make it full screen. On the left side panel we can see the electrical constraints, which we'll discuss in multi-layer. Then we have the physical, so I'll just click on the physical. Inside the physical we have the net layers, net all layers. So now inside the net all layer we can apply the line width. So you can see we have the net list which we have created while creating the schematic. We have a ground, we have LED in, we have 5 volt DC, we have 24 VDC and 24 volts. To this particular nets we can apply the line width. There is a column here, that is the line width column, which is minimum and maximum column. So whatever minimum you add here, so by default it will be setting up while routing. So whatever maximum you want, you can do the maximum. If you exceed that maximum, so it will show you error. If it is 0, that means there is no limit for maximum. You can put whatever trace width you want. So we will discuss this one. So for ground, usually for ground nets we use around 10 mils to 20 mils, 10 mils to 20 mils. No need to calculate it. 10 mils to 20 mils you can keep it. Or most of the time we use the ground planing, so that is why we neglect the trace spacing. So whenever the ground planing is not reaching, we use 10 to 20 mils trace routing. Otherwise we use the planing. So this is all about the ground. So here just for an example, I'll just give 10 mils. So the ground here, the minimum I'm going to give is 0.254, that is 10 mils, and maximum, if you want to restrict maximum, you can give 0.508, it is double that one. So LED 1, I consider the LED here is the data, or you can also consider this as a signal. So I will keep the data around 6 mils. That is the minimum manufacturing standard. Most of the manufacturers have 6 mils, or you can take 8 mil, 10 mil also. For this reason here, the training purpose, I will use 6 mils. So make sure that the 6 mils can be manufactured. Check with the manufacturer if he can manufacture 6 mils. So you can go for minimum manufacturable standard for your data lines. So 6 mils here in mm is 0.1524 mm. So I will assign 0.1524 here. That is the minimum value. Though I will take it as 0.1524, and I will leave a maximum blank so that how much you want you can take it. Otherwise, if you want to restrict, you can give there. I just restrict it to 10 mils, that is 0.254. I don't want to exceed more than that, so you can give that the maximum threshold here. So you can start minimum and the maximum is still in between that. You can give whatever value you want. So like 5 volts, we have already discussed about that voltage. So we know that there is a 1 amps current. So based on that 1 amp current, I will give here, that is around 0.3. So for all three we will give 0.3 mm. So maximum I will leave it, and I will only give minimum, that is 0.3, 0.3 and 0.3. So this is the minimum value. You should give more than this only, not less than this. If you give less than this, so for example there is a ICR, there is a component. So if you are transferring one particular, for example if you are transferring 1 amps to one end or one IC to another IC. So the minimum standard is 0.3 here for 1 ounce or 0.035 microns. It needs 0.3, it says. So if you are giving less than 0.3, for example, if you go less than 0.2, if you've given the trace width, so instead of 1 amps, you will lose something in on the transmission line. You may not get 1 amps, you will get less than 1 amps. That is not acceptable. So minimum or more than minimum you can give, so that you will expect 1 amps on the output side also. That is the reason we should give more than this, not less than this. Okay, so here if you want, you can increase. I will increase it to double. That is not an issue. I will just increase it to 0.6, and I will increase it to 0.6 here too, and zero point 0.6 here too. That is not an issue, so you will not have any transmission loss. So we can give it. So minimum is 0.3. I just doubled it, not an issue. So if it is low density, you can do that. If high density, you can get it minimum values. The maximum, I'll just leave it as it is, so you can give how much you want, and I'll just restrict it to 1 mm. That is enough. That is 1 mm is 40 mils. It is too much for low voltage and low current. So the next one is neck. I will discuss you with when we are doing it routing. So I will discuss about the nets. So this is all about assigning the trace width. You just come towards the right side. If you need any vias, you can set it to vias. So nearly we will discuss what is via. So we will also use one particular via. Here it is not required, but for I will just show you how to create via and how to assign the via and how to use inside this particular board. So this is all about applying the trace width, minimum and maximum trace width. So neck, I'm going to explain you while routing, so you'll understand it properly. And also we will show you about the wires while doing the routing. So this is all about applying the trace width. Sorry, and go to analyze and analyze modes. So we are doing the physical, and I'll just make it all on and then apply it so that we can have all the visibilities. So this is all about the trace width. So you can just cross check. I'll go to route here, click on route and connect. So if I wanted to route on top layer and bottom layer, so you can see this ground. So this is what the ground looks like. I'll just show you an example. We will discuss in detail about this while routing. I'll just click OK, as well as I will take another route. So 24 voltage is a little bit thicker. Just right click, done. So here you can see the spacing. That is default spacing. We just not applied the spacing. Once you applied the proper spacing, you can see that. So here ground, you cannot see the spacing because this is also ground and the planing is also ground. So no need to route ground signal. So if you wanted to route, it is what we have applied it like 10 to 20 mils. So you can do that. Minimum value is 10 is applied here. For 24 volts, it's 0.6 mm is applied. If you want to cross check, click on the I button here, click on this trace, and you can see the trace width around 24. Trace width is, you can see the minimum line width, that is 0.6 mm. So that minimum only we have applied. So this is how it looks like. 24 volts and all 24 only. So go to some other signal, like it is also 24. 5 ADC is also 24, and the data we had somewhere, that is LED, near to LED we got the data. Okay, so this is data which is 6 mils. It is very short in, it is very small if you compare with these two. So we'll compare with that with the 24 volts with the ground. So ground is, you can see that this is 0.6 mm, and the data is 0.1524 mm, that is 6 mils, and the ground is 10 mils, that is 0.254 mm. So this is how the difference between the high voltage and data and the ground. So here the data is minimum manufacturing standard. Ground we can take 10 to 20 mils, otherwise you can use the plane. And 24 volts here, 1 amps is flowing, so that is what the reason we are putting. 0.3 was required according to the standard, and 0.6 we are taking it just for a safer side. So we don't want to lose any current, so I don't want to make it any transmission loss, so we can use more the trace width. And also it will not give any heat because of the more copper, heat will be dissipated inside the copper, so we can get the safe PCB, safe routing. So this is all about applying the trace width. We'll go to apply the trace spacing now. So we'll go to setup constraints, click on the constraints and go to constraint manager on the left side panel, and down we can see the spacing here. Click on the spacing. So click on net all layer. Yes, now you can see the ground with respect to ground line. For example, with respect to ground with respect to through. That means if you are drawing line or trace of the ground signal with respect to another ground signal, with respect to ground through pin, with respect to ground SMT pin, okay, this is how the trace spacing is calculated. So what we need to do is select the ground and here all. So for ground, whatever the width spacing, we will take it. So you already know how to calculate spacing for power. So but what about the ground? So for ground, so whatever width you kept, the same thing you can keep for spacing also. For data or signal also you can follow the same thing. Whatever the width you have, the same spacing you can put it. For power you need to calculate. So for power we need to calculate. So we already have the calculator. So for example, if it is 5 volts, it is low voltage, so you will have 0.1 mm. So if it is around 40 volts, it is around 0.6 mm. If it is around 100 and 200 volt, 240 volts, so it comes around 1.25 mm. So this way I'll just show you how to calculate. For power, we already know the calculator. We have the calculator 2221B calculator, and for data and ground we use whatever the width we have used, trace width, the same thing we will use it for spacing also. For ground, what I'll do it, I'll keep it 0.254 only, which we have kept the width. So we just copy this and paste it to all here, through hole all, SMD all, test pin we don't have, leave it, Y also we don't have, leave it, and rest of that we don't have, leave it, but we have the shape, that is the shape here that refers to the board edge, and hole refers to any hole that non-plated or plated through hole. Similarly for the LED, that is data, we kept 6 mils, we can keep 6 mils only. It's 0.1524. We can copy it to the through hole, and to the SMD pins, we have SMD pins, we don't have test pins, we don't have wires, and yes, we have shape, that is board edge, and finally hole. Similarly for 5 volts, we will calculate. We have the calculator for 5 volt, so I'll put it 5 volt here and click on the calculate. So for 5 volt, yes, we have, that is 0.1, so we keep 0.1, or if you want you can increase also, that's not an issue. So for better performance we can increase, otherwise I'll keep it the minimum value. So the 5 volts, it is 0.1. so copy this and paste it wherever we have. So we don't have through test pin, we don't have through wire, blind wire, buried wire, test wire, and we have the shape, we'll keep it minimum value. We have the bond, sorry, we have the hole, we keep it minimum. For 24 volts we will see, we'll just put it 24 volts here and click on the calculate. So we still have the same here. If you want, you can increase, not an issue. So instead of 0.1, I'll keep it 0.2 for safer size. Just copy this and paste it. So we don't have this. 0.2 is not that too much, it is around 20 mils, that is 0.2, not that too much. Okay, for 24 also same, so we'll keep it, we'll increase it, it's 0.1 is the required standard, we increase it for the safety or for good efficient PCB. But 224 volts is also same, we can copy the same thing, it's 0.1, we are keeping 0.2. So we just leave it as it is, and we need for shape as well as, that's it. So we should go to analyze modes, and then we go to spacing, and we just make it all on, apply, and then click OK. The spacing is also applied, so tracing and spacing is also applied. Now we just remove this trace, just go to delete. So go to side in find option. So I just wanted to delete the C lines that refers to copper lines. So just delete this copper line and copper lines. Okay, so now we'll try to do the routing and check it out the spacing. Just click, I just wanted to 24 volts, just click it here. Now you can see that spacing is quite increased. Similarly, we can also use it for the low voltage. ground you can see. So ground, yes, it you can't see because ground will merge, so you can't see the spacing. So we'll take it the data which is more we have given. Okay, so that's 0.1. We have given 0.2. I think we'll go to constraints manager, and for 5 LED in 6 mils, and it is 10. Yeah, that's it. So because this is trace width is more, that's why we feel that it is less. This actually 0.2 spacing, and it is 0.1524. So this is all about trace spacing and trace width. So the next we will discuss in detail about the trace routing or PCB route. So to perform the routing operations, so first I would like to remove the existing routing here. So I'll just click on the delete button. Here we have the delete button. Click on the delete button and go to find option. I just wanted to select only the C lines. C lines refer to copper lines, that is our routing lines. So just click on the C lines only, make it all off and select only C lines, and you can double click on wherever the routing is there. So just done. Otherwise, if you want to remove everything, just select the entire area. If any routing is there, we can delete that. So as we discussed earlier, so we are going to route on the bottom layer, and in the top layer we kept the ground. So we just repeat that. If we have we have the two layer, and on the top layer we already have the ground planing. So any ground pins will merge or short on the top layer, and we will do the normal routing on the bottom layer. So if we have a signal on the bottom layer, that is ground signal, we just connect it to the nearest ground pin so that it will get the ground access from the bottom layer. For example, we have a component in bottom layer, and that the component has one pin which is any signal, and the second one is ground signal. So we need to find out the nearest ground connection in the bottom layer. For example, from the top to bottom we will be having a through hole component. So for example, if this is a through hole component, okay, so and there is a ground pin. If this is a ground pin, it will short on the top layer, and it is routed on the bottom layer, and we will also have the ground connection in the bottom layer. So we will find that, and the same ground pin is routed on the bottom layer and connected to the ground axis, so it will get the ground axis from bottom to top layer. So a normal all routing will be done in the bottom layer only, so all other signal routing will be done in the bottom layer. In our case, so as we decided, we will do routing, all the routing in the bottom, and only the ground planing kept on the top. So green signal, the green color, that means which is ground signal. See, the ground is already shorted here, so no need to get the ground routing. But you can see this particular component which is kept on the bottom side, and this particular ground we need the nearest ground connection. For example, if there is a nearest ground in the bottom, so if it is in the bottom, so we will route the nearest ground connection. So the nearest ground connection is here, and we can connect it to this particular ground connection. That's it. So from the top it is going to ground, and we have done the ground routing in the bottom. So this is how we make the closed circuit. So we plan now the bottom layer, we have the normal routing, and which is connected to the nearest ground connection, and the ground is done, and rest of that we will do the normal routing in the bottom layer. So now what we need to do is, so we need to select the bottom. So we'll go to visibility, and we just make all top off. We'll just make all top off. Now we only have the ground connections. So why means we have already all the components are through hole, so we have an access in bottom layer. So I just don't want to see the top layer because everything is in bottom, and this SMT component is also bottom side. So we have all the pin access in the bottom layer, so we can do the bottom routing. So before routing, what we need to do is, so we will go to the color options. We have a color option here. This is the color option, so click on the color option. So we make the proper signals as different colors. For example, what I'm going to do is click on the color, and we go to the net option here. So inside the net we go to X nets, that means all nets. So click on the all nets, or nets. Click on the nets, and here we have the different voltage range, that 24V, 24V DC. So we have already set the constraints, how much width and how much spacing is already mentioned. And we have the 5 VDC, which is low voltage, and we also have the ground and data signal, that is LED in signal. I'll make a different color for 24 voltage. I'll make it red as of now, and we will do the routing later. We'll change it for the different signals. We'll click on apply and then OK. So anything which is red in color now is a 24 VDC or 24. So you can go to display option here. You can show the rats and click on the net. So we will get the net connections. So we can go to find here. So in the visibility, we'll make it all. So we will click on the red color. So we will get the rats on here. So we'll go to visibility and make it off, and now you can see the rats are on for only this particular net. So this is the routing connections initially we need. So we have already set the width, and just go to route option, click on connect, and you can join it. So while routing, we have many other options. So I just selected routing. In the options, you go on active layer, which is bottom, because we are doing everything in this in bottom. So we make the active layer as bottom. So anything else if you want to apply, you can apply it here, like line width. If you want to increase like 0.7, 0.8, you can do it. The maximum is 1 mm. So beyond, if you go more than 1 mm, so it will give an error. So but I just wanted to use the default setups here. So now I'll just do normal routing, but here you can do the right click here, and we will use many options here. If you want to change the active layer, you can change it. If you want to make it, bring it up, you can use change the active layer to top. Or now we are in bottom, active layer is bottom. If you want to bring it to top, you can select the top. And then we have the neck mode. I will discuss about the neck mode later. So whenever we are entering into between the two pads, so we need to reduce. For example, here we have the sensitive area. So if you want to pass through this particular area, so this area is called neck, and inside the neck we will do the less routing width. For example, our minimum routing width is 0.3 mm, so we are using 0.6 mm, and I will route 0.6. So on the free space between the two pads, I will reduce it to 0.3. So that is what the neck mode. I will show you the neck mode now, because we just wanted to do the routing here. Right click, done. So we'll just go to the constraint manager. So we'll go to physical net all layer, and here we are doing it. We'll check the which signal which we are doing. So we are doing 24V signal. So 24V signal we should go. So this is the 24V signal, and here I will choose the neck mode. We can see here this is the neck mode. Inside the neck mode, so normally 0.6 we are using. So in between the two pads, either it is SMT pad or through hole pad, we just wanted to reduce it to 0.3. So outside it is 0.6. So inside we will reduce it to 0.3. So inside we will reduce it to 0.3. So this is what the neck mode is. So we'll go to apply, analyze mode, and click OK, close it. So now how to apply the neck mode? So go to route, so click here. If I wanted to get inside that area, click here and right click, choose the neck mode. Now it changes the width. It is the neck width mode, that is 0.3. So once you stop here, just click again, you come back with the come back and off the net mode, and it will come back to 0.6. So right click, done. So this way we can use the neck mode options. Of course it will come because our target is 0.6 to 0.6 to 1 mm, so we are reducing it. That is why the line width error is coming. Yes, you know this why this particular error is coming. So there is no issue here, that is only the error. So we can neglect that error, because we know the practically according to our calculation minimum is 0.3, and we are using minimum 0.6, and in between we are using 0.3, that is called the neck mode. So I hope you understood about the neck mode. Whenever you find the complications are between the two pins, if you want to route, like here, so here it is not allowed to route, but if you want to route between that, like this, if you want to route between this, make use of the neck mode and you can route it. So this is about the neck mode while routing. So go to connect, so click, so right click here, we have the target. So target option, that means while routing, if you want to route from the target, you don't have target, if you have a new target, you can use that. So we just you right click here, target, select the new target and just select the pin. So if you select the pin, automatically the routing will start and you can done it. So we'll do it again. So click on the route, so click on the first pin, right click here, go to target and new target, so double click here. So that is what the new target is all about. So this way you can do the routing also. If you want to rip off the routing, click on the delete button, C lines, if you go to find and C lines and double click on it. And otherwise, if you want to only this particular segment, if you want to delete, so you want to delete only this particular segment, so you can go to C line segment. So we have an option called C line segment, so we can choose the C line segment and only the part we can delete it. So you can, if you want to only delete this particular part, you can delete it. So if you delete this, the entire thing will be deleted. So if you want to delete completely, you can choose C lines. So this is about routing. So these are the basic functionalities in routing. So we have, if you want to route it from the other side, this is the other side, this is the other side. So we have the tool called a toggle. So if you select the tool called toggle, so it will come the other side. So you can see the bending side, it is 45-degree bending, 45-degree routing here. So right click, if you uncheck the toggle, it will come down bottom side. This means first toggle, it is normal toggle and this is the opposite of it. So this way we can do routing. So toggle options, you can see. So enhance pad entry, so you select the enhance pad entry and select it, directly it will join. So what if you have right enhance pad entry, so if I use this way, it is moving towards center only, you can observe it. This is enhance pad entry, so it is exactly going from the center. So I just don't want here, right click here, just uncheck the enhance pad entry, so you can do entry like this. So we can do like entry like this. Enhance pad entry means it will take it from the center. So this is not an enhanced pad entry, you can enter and exit wherever you want. So this is all about enhanced pad entry. So here you can see it is going from the center only. So this we will try the other way. See, this is 45-degree now. So normally if you take, it will go, see, it will not come straight line. So it is not coming straight this way. So it is giving it outside the pad itself, it is turning. It will allow only four directions and diagonal directions, this way and the diagonal directions this way. So if you don't have this enhanced pad entry, so you can enter anywhere. I hope you understood. So this is from the outside directly it is going and it is bending here inside the pad. You can see this is how it looks like. So it is not exactly on the center. So this is the advantage of enhanced pad entry. So we can choose C lines to remove everything at a time, double click, so everything will be removed. So this way we have the routing functionalities. So while routing, you can choose whichever you feel right, whichever you feel good, you can do, and you can do the routing. And there is another option, go to route and slide option. So click on the slide to slide the routing. So click on the route and slide. So click on the segment, and if you want to do this way, bring it right, don't drag it, just click and move the mouse pointer. This is one way of normal pad entry and exit. So this is the other side. So this way you can slide your routing. So that is what the slide option is. Okay, fine, now we'll go with the normal routing. So if you have a custom smooth also, so custom smooth will find out the nearest path or the shortest path. Select the custom smooth, click on the routing which you have done. So this is what the shortest path it is asking. So this is the shortest path, our custom smooth we have done. So if you want to change it, go on slide and slide it, so either this side or the other side. So you can also do this way. So I just recommend you to don't use that too much turnings. One or two turnings is enough. This is enough. One turning, that is more than enough. So this way we can do the routing. So we can select route, connect, and click here. Right click, you can observe all these things. So now in the target section, if you don't have any target, normal routing you can do it. If you have a route from the target, so you can select, it will come opposite direction. So initially what happened, I started routing from the this particular pad. If you want to route it from the other pad, right click here, go to target and go to the route from other. So you can route it from the other pad. So this is another option. While routing, you just right click and you can check it, any options you can. So we will do this. So if you don't want that particular segment to be directly connected here, so we go to route and slide and click on this segment and bring it outside. So this way also you can do the routing. So this is all about 24 VDC routing. So this routing is done, and we will go to color and remove the color. To remove the color, we'll click on clear all nets. Click on the clear all nets, click OK, and then click apply. So if you want to change it, go to nets, and now we need 5 VDC and LED. We'll both make it red and click apply. Now we can see some connections. Go to display, show rads and nets. So you can connect pin by pin. So this is one pin connection, which is bottom, and this is the other side. So we need to check it out how to make this particular routing. So we will plan this. So go to route here and connect. So this is in the bottom, we'll connect from the bottom. That's connection is done here, and we can come from the outside here. So we will connect this one first, so which is just look like a data, and we can connect it directly, and we can come this from the outside. You can also directly connect and you can take it. So we need it from this particular capacitor, and this one we will join somewhere here. Right click and done. Okay, so this is, we can do this arrangement. You can go to slide and we'll connect this way and -90°, which is not allowed. I'm just sliding it. So here 90°, which is not allowed, we'll take a short connect, and we will take the line from 45° this way, and we'll take a copy of the segment. Click on this and we will choose this particular segment. We will route connect. So we'll just click on this and take this segment. This segment will remove, this segment will also remove, and we will move this particular and rotate it. So rotate it to 45°. This way we will join it here. Right click and done. So we don't want like direct 90° bending, so we always make this way, smooth flow. So if you just adjust it properly, that's enough. So right click and done. Right click and done. That's it. So this is all about this particular routing, and we'll go to the other routing, connect, and so we can do this. Normal routing is already done. I click done, and we can use the slide option, so we can just make a slide this way we could keep it outside the signal. So this is in the bottom layer, so routing is almost done. This is a simple routing, so you can try like this, you can try any kind of routing. So we will just go to visibility and click on. So we have done all the routing in the bottom layer, so we will see how it looks like in the bottom. Just you have an option to 3D, just click on the 3D, and inside the 3D how it looks like we will see. Just click on save, click on the 3D. So now it looks like this in the top layer. We don't have any routing in the top layer, we just have the planing, that is copper planing. We go to view and camera, that is on the bottom. The bottom layer, yes, we have the routing, so which is kind of a normal flip routing. So we can see, because it is bottom side, whenever we turn your PCB it looks like this in the bottom side. So now you can see this routing, so to this particular pad which is normal, and here you can see this is what we have achieved. So we don't want to take 90-degree bending, always try to avoid this kind of routing and make the proper arrangement for smooth flow of the current voltage. So this is what the simple routing which we have discussed. So this is all about routing. So before routing, what we need to do is just make a route constraint setups. So how much width and how much spacing needed to be done, we can put it in the constraint setups, and then you can do the normal routing. So here in this particular project we chose bottom layer for normal connection routing, and the top layer for all the ground planing. So now we will go to put bottom layer also, we can put the ground planing, and we can check the spacing settings. So we'll go to uh, so shape and rectangle, so go to the edge and bottom layer. So in the bottom also we click on ground connections, and we put outside, just click, we'll make it bottom, this one. So just select it, right click and done. So now we will go and check in the bottom layer. Save this. I just want to hide the top. We'll go to visibility, we just hide the top, so we do not have any planing in the bottom. I hope it should come. So we will say, so we will go to 3D and check it in the bottom layer. So weave and go to bottom. Sorry, the bottom is not done yet. So we'll go to shape here, rectangular, and in visibility edge bottom. The dummy net, I believe, will go to ground net, and we'll keep the bottom, right click, done. So now in the visibility we just off the top, so you can see how it looks like in the bottom layer. This is how it looks like. I'll just remove the colors, so I'll just go to colors and clear all nets, say yes, and then click apply, and then click OK. So now you can see this is what the bottom layer. Yes, we have got some error because of the spacing. So there is a spacing error or line width error, we may get it. So as of now we'll neglect this. So we'll go to, this is the bottom layer, how it looks like. So we have the spacing also on the right and left hand side of the trace. Yes, we have the proper spacing is applied. So if you have any issues with the spacing, if the spacing is not applied, go to shapes and global dynamic parameters. You have the smooth or update all option, you can click on update all and update, and then click OK. So then you will get the proper spacing between the tracing as well as through pins. So we'll check that in 3D. So click on 3D. So this is the top layer, we don't have any routing in the top layer. We'll go to bottom copper. This is how it looks like when you put the ground planing in the bottom also. This is how each and every routing will have a proper isolation from the ground plane. That's it about routing. It's a simple routing, you can also try with a simple particular routing. So the next thing what we need to discuss is all about the artwork preparation. So artwork is a file, we will discuss about brief about the artwork. So artwork, so artwork are the files which is required for the manufacturer. So what are the minimum files that manufacturer required, we need to get it here. So first thing, we need the board shape, that how is the board shape looks like, and what is the area of that particular board shapes. So we can do that. So first thing is shape of the board we need to provide. So according to the shape they will cut the board, and if you are going for mass production, so they will cut it like 1000 2000 boards using this particular shape of the board, or board shape. We also call it as profile, in other words. So board profile also we call it as. So we need to create an artwork for board profile. So what the manufacturer do is they first need the top copper. So they first need the top copper, and then they need bottom copper. So to print the top and bottom copper, we will just look at the top and bottom copper. By default, whenever you choose the two-layer PCB, whenever we choose the two-layer PCB, so by default they have a top layer. We also know that we have the top copper layer as well as bottom copper layer. So we will see how it looks like top, bottom and top copper and bottom copper on the PCB. So this is entire PCB. So whatever you are seeing here is an entire PCB. How it looks like only the top copper. So in the top layer, how the copper print looks like, we will see. Just go to the manufacturer and you have the artwork options. So click on the artwork. Now we have the top copper layers. That is, first one is H, second one is pin, and third one is wire. See, in the entire board we only have the three things which is copper. The first thing is H top. H in the sense that is routing. So whatever routing be done, that is an H. And second thing is the planing. So we had put the ground planing. So that is what the H on the top layer. That is copper. So second is pin, or that is solder pads. Either it is SMD pad or it is THT pad, that is through hole pad. So RPTH, so or any BGA or any wires. So wire, the next class is wire class. This is all about the wire. So there are only three things. One is the normal routing from top. So how the routing is done. Second one is pin, that is SMD pin or through hole pin. This is SMD kind of pins, and this is through hole kind of pins. And then we have the wire class. Anywhere if you are having a wire, that wire class is also a copper print. Only these three are actual copper and others are not a copper. So this is on the top layer, and in the bottom layer also we have H bottom. H, that refers to routing and planing, and pin refers to solder pad, either it is SMD solder surface mount or through hole, and wire, which is also a wire class. If you have any wire, so wire pad also comes under copper. I'll just click OK here. Now you come back on the right hand side in the visibility. So we have the global visibility, and then we have the view option. So inside the view option, so you just click, we have the top and bottom. So I'll just click only the top, so we can see this is what the copper on the top layer. So it looks like this in the top copper. So this print, the manufacturer will take this film and they will use to etch the PCB, etch on the PCB on the top layer. Similarly, so we can go to bottom layer. So this is what inside the bottom, on the bottom, this print we will get it. So this is all about only copper. We are talking about only copper print on top and bottom. So here you are not finding any component, any seal screen, no assembly, nothing. We are just looking at particularly about copper layers only. So this is the two different layers that manufacturer needs. The next thing what the manufacturer needs is the other files, other films layer. So now you have the copper things, that is top copper we have, and then we have the bottom copper, and the next he immediately needs is the paste mask. If SMD components we have, they need the paste mask top as well as paste mask bottom. So these are the things that manufacturer needs. So we need to create the paste mask folder, and inside that we need to add the sub files for the paste mask. So that will be done inside the manufacturer artwork. And if you want to create a folder here, just right click on the folder. If you want to add some files inside this, you can right click and add some files. I wanted to create a folder. I'll right click on the folder, click add manual. So now what I need to do here is I wanted to create a paste mask top. So I will write completely this paste mask top. So I wrote completely. So you can also use the shortcut names like PST or solder paste also, we call it as solder paste also. So click OK. And what are the paste masks? So how, from where we have created the paste mask? I think you have remembered about the pad stack editor. Inside the pad stack editor, while creating the pad stack editor, we have created the paste mask. So we have created the paste mask top by default, so we can choose that pad stack editor. Here in the artwork, the pad stack means pins. The pad stack means pins, and the subfolder or the subclass will be paste mask top and paste mask bottom. So whenever it is top, we'll choose the top. Whenever it is bottom, we'll choose the bottom. Apart from that, we put the paste mask in package geometry also. In package geometry also, inside the package geometry, we can choose paste mask top. Paste mask top. So we will choose those particular files here. The first thing I will choose pin. Pin refers to pad stack editor here. While creating the pin or pad, we use paste mask top. I will choose the paste mask top. And then if you are not putting the paste mask inside the particular pad stack editor, we are putting that paste marks inside the package geometry. So we will choose that in package geometry paste mask top also. So these are the two files where we put the paste mask, and then click OK. Now you can see on the left hand side, so we are having paste mask top folder. So now right click, just click on this arrow mark and check it out how many files we have added. We have added 2 files. So the next thing what we need is paste mask bottom. So we'll put paste mask bottom. So here same files, but bottom layer we choose. So we have, by default, we have not done any paste mask bottom in pad stack editor. By default we create in top only, but if you mirror, automatically the files will change its subclass to bottom. Sorry, paste mask bottom. Similarly package geometry and then paste mask bottom. So click OK. So the two files were created, and I'll click OK, and then we will save this file and we will check out now here inside this file view, and we are getting 4 film layers. First film is top and bottom. By default we will be having. Then we created paste mask top and paste mask bottom. Let me check on the paste mask top. If we have a SMD components, we will be having the paste mask top. See, in the top layer we don't find anything, that means there is no paste mask on the top layer. So go to paste mask bottom. So we have only one paste mask, that is for this SMD pins, so we can witness that. So if you look at this is awkward, so you can also add the board geometry out here. So if you go to top, in the top we don't have the board geometry, but so we have the shape here, that is ground shape. That is why you can see that looks like a PCB board. So we will also add it to the paste mask. So we'll go to artwork, and inside the paste mask we will add some files. One file we will add, that is board geometry and design outline. So if you want, if you have an outline also, you can add outline. I'll just click OK. Similarly for paste top also we will add it. Right click, add board geometry and outline or design outline. So we don't know which one we have used. If you know perfectly, you can add that design outline. If you don't know, if you are not confirm which layer is added, you can add both. Any file which is applicable, it will be applicable to the particular artwork. So we'll go to board geometry for paste mask bottom. We will add outline and design outline for our reference. It is not for them. This is just for our reference. So we will add, right click, add file, go to board geometry, design outline and outline. So click OK, and then we will click on OK here, and then we can cross check. So I will choose the top now, so we can witness there is outside, there is a design outline, or outline is, we can see this is for our reference. Similarly for bottom also, we can see outside we can have the board details. And paste mask top, you can see the paste mask top, and we can go for paste mask bottom. So now here you can see there is a proper visibility here. So this is all about paste mask bottom. So now we will add solder mask top and solder mask bottom. We'll go to artwork, we'll create, right click here and add manual, and I will choose solder mask top. So we will choose solder solder mask top. So inside the solder mask top, first I'm going to add a reference files, that is design outline. Okay, so the next thing is solder mask will be done inside the pad stack editor, that I will choose the pin and solder mask top. And also we have done, sometimes we do that package geometry, that is while creating the footprint we create the solder mask top. In case if you miss or if you want any specific solder mask, we can also do it in board geometry. While creating the board design, we can also do the solder mask whenever is required. So these are the three files where we need the solder mask. We can choose the solder mask, click OK. Now the solder mask top layer is, our film layer is created. Likewise we'll create solder mask bottom, solder mask, that is bottom, click OK. So I will add reference file, that is design outline and outline, and we'll go to pin, that is pad stack editor, we have the solder mask bottom, and package geometry we have the solder mask bottom, and finally we have inside the board geometry we can do solder mask bottom. So these are the three files we will be having in the solder mask bottom area. So we'll click OK and then save this. So we will be having four files here, that is solder mask top and bottom. I'll choose solder mask top. For SMT and through hole, for both we'll get the solder mask. So if you want to cross check, click on the pin here in the visibility section. This is all about the visibility section. So if I want to see the pins on the top, I can choose here the pin here. You can click on this, so we can see the pad and solder mask. I'll zoom it. So this is the through hole pad stack. If I click on the pin visibility, so you can see the pin is smaller than the mask. That means the pin is hiding behind the mask. So once you colored, the mask will be removed. This is how in the bottom layer also. So this is what the solder mask in the top, and we'll go to bottom. We don't have component. Yes, through hole component, only one component, and all through hole component will be seen in the bottom side also. So now we have these two things, one is SMD and through hole. Yes, through hole we can see it in top and bottom. SMD we kept it in bottom, so we can only see in the bottom. So if you choose on the top, we can see this on the top. If you choose the bottom, we can see the bottom side mask also. So this is what about the solder mask top as well as solder mask bottom. If you want to on everything, click on the global visibility and on, so you can see each and every film layers. Okay, so the next artwork file will be, so we had the paste mask, we had the solder mask, and we will be having an assembly. Right click here, add manual. So go to assembly top. So click OK. So I will add the reference file, board geometry outline and design outline, and then we will go to, so we are not putting any assemblies in a pad stack editor, we are putting that in package geometry and then assembly top. Apart from the package geometry assembly top, we also have the reference designator and then assembly top. So that is R1, R star, C star, U star we put, that is the reference designator. Click OK. Similarly, we'll put right click, add manual, that is assembly bottom. So board geometry, design outline. So we'll go to down and package geometry, assembly bottom, and then a reference designator, then assembly bottom. I hope here I have kept assembly bottom only. We will change it. So go inside assembly top. Yeah, this is package geometry, assembly top, reference assembly top, and inside this, so we have, I'll just cut it and rename it, the name was wrong. So right click, add manual, so assembly bottom. So board geometry, design outline, and outline will go down, package geometry, that is assembly bottom, and then reference designator, assembly bottom. So click OK. So now we are having assembly top and bottom. So we just click OK and save the project, and come right side in the visibility view options. So we find assembly top. So yes, here we only have the assembly outlines. So that means this is actually component area. So if you look at the 3D package, the only assembly area we can see, this is what the assembly, that is size of the component. This is also size of the component. So we witness that things inside this. If you on the pin on the top layer, this is how the pins looks like. So assembly along with the pins. So in the bottom side also we have got the pins. But if you want to see the bottom assembly, just click on this view and go to the bottom assembly. We have only one component, and which is red color, that is assembly. Whenever we mirror the component, it will go to bottom side and it changes the color. And if you go to bottom side pins and you can on the pins and check it, this is how it looks like in the bottom layer. So this is all about assembly top and assembly bottom, that where we witness the component size on the PCB. The next thing and the last thing is around the silk screen top. Go to artwork. So silk screen is an ink print. I'll just right click here, add manual. We say silk screen top, and that is board geometry, design outline and outline. And we have package geometry. Then we go to silk screen top. So while creating the footprint, we have done these things, and then we also had the reference designator and silk screen top. And one special thing is inside the board design, while doing the board design, so you may write the name of your company on the board. If you can draw the logo of your company on the PCB using the silk screen, that time make sure it is board geometry and silk screen top. So I'll choose the board geometry silk screen top. If you are writing your company name, just click OK, and silk screen top is ready. So now go to right click and click on add manual. Silk screen bottom will put it. Silk screen bottom. So go to board geometry and design outline and an outline. So we'll go to package geometry and the silk screen bottom, and then reference designator and silk screen bottom. So come up and inside the board silk screen bottom we can choose. Click OK. So this is all about silk screen. So now we go to, we'll save that. Before that, go to visibility and we choose silk screen bottom top. So this is how silk screen look like. So this is only about the component area where we are putting the silk screen layers along with the name silk screen reference. So if you have any company name, so it will be designed here. I'll just write the company name. You can go to add text. So I will choose that on board geometry and I'll choose the silk screen top. So inside that I can write the company name. So I'll just write it here. So corner, just I will take company name. So right click, done. So I'll show you how to edit this text, how much width, how much height and all. We'll add one more thing, edit text. So we can put the company name and I'll just write company website. So this is how it looks like. So if you want to do the same thing in the bottom layer, yes, you can do that on the same side. So we can go to add and text. So here instead of silk screen top, we choose silk screen bottom. So now you can write it here. Company name, right click, done. So you can't see it because we are in silk screen top. So we can add text and here we can put company website. Company website. So right click, done. So we can't see because it is on the bottom layer. So now go to visibility and I'll choose silk screen bottom, so we can see these things on the bottom side. So this is how it looks like on the bottom. So if you want to mirror it, you can mirror it because you can't see the same thing. We'll go to check in the 3D. So in the top side we don't find the silk screen top because it is zero length. I'll show you once we do the fabrication editing. Just make it on. Okay, so this is all about creating silk screen top and silk screen bottom. So our artwork file is ready, so we can witness the artwork file. If you want to see only top layer, we can see the top layer. If you want to see only bottom layer, we can see bottom copper. So if you want to see this paste mask, you can see the paste mask. So these are the files the manufacturer required for the manufacturing. Each and every design separately needs. So accordingly, they are going to go for manufacturing files. So this is about solder mask top and solder mask bottom, then silk screen top and silk screen bottoms. So now we will work on text editing. So what will be the proper size of the text on PCB? Second, now we will discuss about the text setup first. So as you can see here, we have the random text which we have selected in the while creating the footprints. Now we will take the proper visible text. So I just click on the 3D and you can check it. You don't find the text on it because the text width is 0. That is the reason we don't find the text here. So before setting up the text, we will see what are the sizes of the text. So if you want to see the default sizes, you just go to setups here in the design parameters. So go to the texts, that is the third option here, the text option. So now here we can go to setup text sizes and click on this browse button. So we have many text size text blocks we have. So this is the text block, and then we have till 16. We will 16 text blocks we will be having, and after that 16. So we will find some manual text which we are providing, text blocks which we can create using the add buttons. So here in the mils, so we have set up the units in mils. If you choose the text block 1, so the width and height of the text will be according to this particular table, line width, line space and character spacing according to this. If you choose text block 2, it is 23, 31, like that we can take it. Just we will see that. So I will add some text here. I'll take add and text, and here I'll choose the text block 1. On the right side I can choose the text block 1 here. So I just draw any class and subclass just for our reference. So I choose the text block 1. So if I want to write here, it's very small size. I'll just let me zoom in. So this is about the text block 1. I just say A, B, C, D, and in the next line I will type E, F, G, H. So right click and done. So this is what the text block 1 is. We'll go to setup here, design parameter, and go to text. Here in the text block we'll see that width. We can see the width of the text is text block 1 we have chosen. The width of the text block is 16. That means, so this is the width of the text block which is 16. So this is the width of the text block, that is 16. So this is the width of the text block which is 16, and this is 25. That is the height of the text. Here the height of the text is 25 mils. The height of the text is 25 mils here. Each and every text height will be 25 mils. The line spacing, it says it is 31. So from this line to the second line, so which is around 31, that is the line spacing. Probably it is from the center of this particular alphabet to another center, which is 31. So that is the line spacing. To the next line it means. So the next thing is the photo width, which is 0. That is the reason we find this thickness. We don't find this particular thickness here. The thickness is 0 because the photo width is 0. So if you want to increase it, you can increase it and cross check. Similarly, character spacing, which is from one character to second character, which is 6 mils, which is the default, or the minimum line spacing between the two text, that is character spacing. So you can give your name, so you can identify while creating the ad. You can put that particular name also. We can use it for our reference. So this is the first one. So we'll add the text to here, add text, and I will choose in the inside the text box I will choose the second one here. So I'll click on the second, or you can click on arrow mark, or you can type manually 2. So we will see this, and this is, I'll just put A, B, C, D, E, F, G, H. So according to the second text setups, which is quite bigger if you compare with the text block 1. So we will compare that. Go to setup, design parameter, text, under the text. So under the table we have the text block 2, which is 23 width. The width is 23 compared to text block 1, which is quite bigger, and height is 31. and the line spacing from the center of this alphabet to another center, next line center, will be around 39 here. And the line photo width is 0. That is the reason we find the thin hairline width. And the character spacing is quite bigger here, 8 mils it is the character spacing. So that is the reason we find some extra spacing. If you compare with this A and B, this is 6 mil spacing, and this A and B, this is 8 mil spacing. So now we will add the text block 3 here. Go to add and text block. So we will increase it to 3. So now you can see the third text block is quite bigger, A B C D E F G H. So right click here, done, and now you can see. So this is the text block 1. The width and height of the component and line spacing and character spacing is quite normal, and this is quite bigger compared to text block 1. This is quite bigger compared to text block 1 and 2. This way, if you increase the text block, that is 3 4 5, this text size, text width, text height, line spacing, and that character spacing is getting increased. So which one is good for your PCB? We will see that the text block 1, if you take, it is very small, so it is compared to your board, which is very small here. So what we need to take, second one. We will check second one also looks small, so we'll go for a third one, which is quite fine size, we can visible it properly. Or otherwise you can also do the custom size, or you can add your own size. To add your own size, we'll go to design parameters. So we'll go to the setup text sizes, and you can add here. You can click on the add and click, and we get the 19th one. So using that, you can do that. So let's just restart, click OK, apply, and we'll go back again. Okay, click on add here, the 19 size. So you can put your own. For example, I will put like around 35 width and 50 60 height, and line spacing accordingly we need to put it. So we'll keep it around 70. If it is more, we will reduce it. So I'll put 6 mils line width, that the character width, and the character spacing is, I'll try to keep it 6 only. Click on OK. So now you can observe here the text 19, so which is created by us, which is 35 width, 60 height, and 70 line spacing, and 6 mils, that is the width, and 6 mils is a character spacing. So we'll see how it looks like whenever we apply that particular. So I think it is 19, so we'll go to add and text. So here the text block, we will make it 19. So we made here 19 in the text block. So now we will click and check it out, A B C D and E F G H. So right click and done. Now it looks quite thicker. If you compare, that is photo width, we increase it to 6 mils, and the size also is fine, 35, and 60 is height is 60. So we can use this if you are okay with that. And character spacing is quite very near if you compare the line spacing, because we have just taken compared to third only, we have taken it. So if you want to increase it, you can increase it. We have taken 70. If you want to increase it, you can increase it directly. Go to setups here. So that is 19. So I'll make it 80 mils, and photo width, will make it reduce the photo width to 4 mils. So click OK, and then click apply. OK, and zoom in, zoom out. Okay, that's fine. So now you can see the line width is 4 mils, line spacing is quite different, and character spacing is also fine. So it is proper readable, so you can use that. So you can also make your custom size, that is length into width, and the line spacing as well as character spacing. So now I'm going to use the third one, which looks quite good, and I'll just increase the photo width because it is thin hairline. So I'll increase the photo width. So go to setup here, design parameters. So go to text sizes. The third one, I feel it is good enough. So I'll click on the photo width. I'll take it around 6 mils, and line character spacing also, I'll take it 6 mils. Then click OK, apply, and then click OK. Now I'll delete this. So on the PCB, we will apply these settings. So I will go to the visibility, that I will take it assembly top first. So we have the assembly text here. So how to change now? So it is by default, we have taken the text. So we'll only select the text here. So now how to increase that? Go to edit and click on change. So inside the option we can choose the text block. I will choose the text block 3. So here I have chosen the text block 3 and click on this. Now you can see which is increasing. So similarly what I'm going to do is select the entire thing, because I have only selected the text here, so all the text getting increased here, because here in the find option I only took the text, so it will apply to the text. So likewise we'll go to assembly bottom 2, and here also we'll apply the same rules. So it is also increased the thickness. You can see that the thickness is not 0 now, which is 6 mils. Similarly we can go to silk screen top and silk screen bottom. Silk screen top, which is, sorry, it is solder mask, silk screen top. So we can increase this. So company name is increased, everything we increased, here also we increased. Now I can see that is proper visible text. We can see that. Likewise we can go to silk screen bottom too. We have got some text here. We'll select the entire bottom, right click and done. That's it. This is what we need to do about text editing. So we can always go to setups and design parameter. Inside the text, click on the setup text sizes. We can select your own or existing, also you can change it. So make sure so you have the proper visible width, visible text width, and the text size is selected properly. Now we will see how it looks like on the PCB. So we'll make it all on. So we'll go to the 3D. Okay, so you can see the proper text which is written on the PCB. So we'll go to view option and camera top. This is how it looks like. We can see that we can read the company name properly and company website properly. The thing is, U1 is overlapped with the silk, D1 is overlapped with the something on the through hole pad, C1 is also overlapped on. So we will arrange the text now. So go back to PCB. So I just wanted to arrange these text. So what I'm going to do is I'll just go to move and go to find and only select the text options. So here I'll just off the top and off the bottom. I can only see the silk screen text. So we have got that only two directions we need to do is one is towards the right and one more is towards up. So for example, if you have a register that is R1, either you need to put the text towards the right or you need to put the text towards up. So these are the only two are allowed as per the standards, towards right and towards up, not towards left, not towards bottom. So make sure that you should not have your text this way or you should not have a text the other way. So that is rotated way. Okay, so we will just click on the move button and we'll select the text. So right click here, rotate. So you can rotate this way one way, otherwise the other way. So these are the two options we have. So I'll just take this is J1. So make sure it should not come on the route. On top layer we don't have routing, so I just keep it on top or bottom. That's left to you. So I'll just keep it here, right click here and then rotate and just overlap silk and assembly. So I'll just keep it both at one side. So this is J1. I'll just make it near to this, because don't overlap on the silk screen. That is enough. This is quite enough, so that is fine. And here also D1 we will keep it on top. You can keep it between, but make sure people can read it properly after placement also. So this is also fine. C1 will keep it on the right or left or top or bottom, so wherever you're comfortable, you can read it properly, we can put it. So I'll just keep it on top. I'll prefer keeping it on top of the component. So and then next R1 I'll keep it here on top of the component. So here also I'll keep it. You can keep it here center, but I'll prefer on top. So this is C2. I'll keep it here. If you find that is confusing, you can keep it here on top of the capacitor here also. So this one we will keep it on top here, and this one also we will keep it on top here. Write it. Now D2 will, that is fine. D2 is sitting quite normal. J2 is also fine. Okay, that's fine. So now we have arranged, and also this text we don't keep like half outside and half inside the restriction area, just keep it normal so that we can read it properly. So this two is fine, and this two quite will bring it inside, and this is also fine. So this is bottom side, however. So do right click and done. So bottom and top both we have done. So just click on the 3D and cross check. I'll just make it visibility all on and save it, and just look it in the 3D how it looks like. That's fine. So we can view and read the text properly on top of the PCB. So now no cell keys overlapped, no pads are on text are not on the pads. So properly it is placed on this, and we can read it. Assembler can read it properly. So this is all about text setup. So now we are going to discuss about Gerber release. So to release the Gerber, what we need to do is, we have already done the artwork under the manufacturer and artwork. So this is what the film controls we have. So but before that we will put some drill lessons. So we must know about the drill details about this particular PCB. So go to the manufacturer NC drill lesson and just click OK, and you will get the drill chart. I'll just keep it right side and top side or bottom side if you have. So I will keep it somewhere on the right side. That's okay. So right click here, done, and this is what the drill chart from top to bottom. So units are in all mils, not in millimeters. Okay, so here you can see this 30 mils. We got around two 30 mils plated holes, and 31 we got two 31.654. We got two. So this is all about one non-plated, which is 118.11 mils. If you read this particular data in millimeters, then you will understand quite. So I'll just remove this. We'll just remove this and we'll put that in millimeters. So we'll go to setup here, design parameter, we keep it in millimeters, and click apply, and then click OK. So now we'll try to manufacturing NC and drill legend. So that's the output unit in millimeters here. By default it will come once we set up inside the millimeters. So otherwise, so you can change it here also, no problem. If you want mils, you can select in mils. If you want inches, you can select here. So click OK, and then I will put the chart just next to the PCB and right click and done. Now you can see all units are in millimeters. Now you can see 0.762, there are 2.784, there are 2, 0.8 is again two plated, 1 mm4 we have. So 1.27 we got 3, and 3 that is non-plated, that is the screw or NPTH. There are 4 drills. So this is all about drill. So next we are gonna release the Gerber. So once everything is fine, we need to release the Gerber. So go to release the Gerber, go to our manufacturer artwork, and so we have already the Gerber files. If any extra files if you want, you can choose it. So I wanted the profile, that I just right click here and add manual. So I just wanted the board profile. So we will take the board profile, click OK. So for inside the board profile, I'll prefer design outline and outline. So anything else if you want, you can put it. That is more than enough. So board profile will check how it looks like. So click OK. So save the file, and so go to visibility and check it out, the board profile here. So this is what the board shape. So we can cut that particular board here. Okay, fine. So we'll go to global visibility on and click on the zoom to fit. So go to manufacturer and then click on artwork. So here inside the artwork, we need to select each and every files which is required by the manufacturer. So I will choose all the files here. I have never created any placement file, or I have not created any other footprint or top and bottom placement. We just have the minimum required for manufacturer. We select the files for manufacturing, click on create artwork. So I just click on create artwork. So do you want to continue, just click say yes, and that's it. So we have got the artwork files were created. So we just have to go to the board location. So wherever your board location is there, so you just have to go and see for the artwork files. So we have that on the desktop. So inside the desktop we have got the board files. Inside the board files you can observe we have got the ART files. So these are the art files we have here till here. So all the artwork files were created, that is top artwork file, and that is bottom artwork file, and that is solder mask top, solder mask bottom, seal screen top, seal screen bottom, paste mask top, paste mask bottom, and board profile, assembly top and assembly bottom. So each and every files we just have to select and cut it. All artwork file, make sure any artwork file is missing. If it is missing, recreate it. I'll just cut this for portion and go to the Gerber folder, put it inside the Gerber folder, and that's all. You just send this particular files to the manufacturer so that they can process with the manufacturing files. So this is all about how to create an artwork and how to release Gerber file for the manufacturing.